Hey, Bill, how's it going?
Pretty good. How about yourself?
Good, good.
Hello, Bill. Nice to see you.
And you?
New look.
Yeah, I like the beard.
Yeah.
It's
I don't know,
A
maybe
product of laziness more than anything.
No.
Looks
Once,
good.
yeah, once it's there, don't go back. Looks good. As long as your face stops itching, then you're fine.
I mean, the real
am,
limiting factor is actually making sure that my beard hair doesn't go up my wife's nose. That ends up often being the death knell of the beard.
You got a while before it starts turning white like me, so you're in good shape.
I used to have a beard early in grad school, but I got rid of it. Coincidentally, that's when I met Janelle. I mean, I think they're closely related, but I've been noticing lately, I was at a workshop and I had the face mask on because it's inside, but I started stroking my face mask like I did when I used to stroke my beard. Old habits die hard, I guess.
Yes.
Hi, Emma. Good evening.
Hello,
Good night.
everybody. Great to see you.
Thanks for coming.
Hello, can you hear me?
Yes.
Yeah, good.
Does anyone need to test their slides and check that they can connect without an issue?
You want me to just test mine that has the welcome? Maybe I
Yeah.
should do that just briefly here.
Yeah, just in case.
Because I've got multiple monitors and sometimes it doesn't work like you'd think. So hold on one sec. Okay. Thank you, Zoom. All right, let's see.
Yes, we're
Share
live in YouTube.
Hello everybody. Okay, so here, and did that, just tell me if that went well, it's still working. Tell me if that went full screen or if that's just a,
That's
is that
full screen.
Yeah.
Yes.
That's full screen, yeah.
all right, perfect, great. Then I will stop sharing. Boy, this thing is just slow as molasses. All right, stop share, thanks. There we go. Nope, it didn't stop. Now it stopped. So anybody else need to test?
I will test mine because my webcam doesn't work.
Right.
Let's see. Oh, I can't because I'm a participant, so it doesn't work.
Oh, it doesn't allow you to
Yeah.
share.
And
I
of
see.
course, it's only. I mean, I have only a couple of slides so to go through, so
Right,
it isn't
can
really
we,
necessary.
Yeah, I
right,
think
but
we-
can we, do we either have Eric's or can we turn that on for him?
Yes, we should.
Who has the magic wand here? Well, Bharat
No,
is the
but after
host,
we-
so I believe Bharat has to do it.
Yeah. After Bharat fix Eric, he needs to fix me because I'm organizing here, but I see that it's just me, no host, no co-host, nothing.
Oh, that's right. You're a participant along with everybody else.
Okay, I was demoted. Okay, thank you.
We're going to mute you, Carlos.
I know.
Let me fix the web page once. I'll make one of you hosts so that you have more. I'll just pick
Okay.
the host and you have more privileges, and I'll fix the web page. Just give me a couple of seconds.
Eric, while we're waiting, if you can hear me, my Finnish is so terrible that I cannot pronounce the name of your club, so I might defer to you for that.
Yeah, I understand.
Um,
Of course, the last part, of course, it should be.
That's okay, but
What
it's
is-
I'm going to mess the first part up. I know it.
Yeah.
So better for me to let you do that. Okay. And Bea, we're just a little after 2 p.m. too. So
Okay.
you let me know when you think we ought to start.
Did we check Eric's connection, that he's able to share?
Yeah, sure. I'm going to try it now.
Yes, if you could try that, then I think that would be what we need. Ah,
Oh, it's
there you go.
Perfect.
Perfect.
Yes.
Great.
Excellent.
Now we'll
That's-
just need to figure out how to stop this. Ah, there we go.
Yeah, the window floats somewhere. It can be a little difficult. Okay.
Very good.
All right. So how are we doing, Bea? We have, I count 24 people here.
Yes. That's probably a good number. We can probably start.
Shall we start? Sure.
Yeah.
All right. So I'm going to now share my slides just as a welcome. Hold on a second. Okay. And then I'll hit the button. Hold on a second. My machine is slow. There we go. So on behalf of the organizing committee, I'd really like to welcome you to the Steve workshop. Notice we've put 2021. As you'll hear, we intend to do this again if we can. So this is the first of what we hope will be a series. This deserves all the credit of the organizing committee, who you see on the screen there. Bea Gallardo-Gacourt from Goddard Space Flight, Gareth Perry from NJIT, Bharat Kunduri from Virginia Tech, and I have to give Bharat a special thanks for doing a lot of the technical legwork here and getting the webpage set up and getting the Zoom client and the YouTube and all sorts of other things. Carlos Martinez there from Boston University, and myself from MIT Haystack. And I also want to very much thank our student volunteers, Valerie Sfaldi, who's been working with Tomoko Matsuo at CU Boulder, and Binji Liu, who's working with Gareth at NJIT. Valerie and Binji have very graciously agreed to do some of the things that, like switch people in and out as they come into Zoom rooms and that kind of thing. So I very, very much appreciate their help. And we had, and also, and we'll hear from Alan Liu in a minute, a special thanks to the National Science Foundation of the United States for supporting this through the grant number that you see there on the screen. We deeply appreciate that. So let me, before we hear a few remarks from Alan, our funding program officer, actually, I just want to mention a couple of brief organizing items just to sort of start us off here. The workshop, you'll notice, was not advertised on things like larger mailing lists. We deliberately kept this first one small to encourage interactive discussions as we feel through this particular community that we've assembled and figure out what the best ways are for us to collaborate and work together and which projects we'd like to collaborate together on. So that's another reason why we've kept the Zoom list reasonably small, but we also have this streaming YouTube link for people who wish to sort of keep up with what's going on. We do intend more workshops in the future, and if Alan's listening, we will propose them. So you'll be hearing from us later. Discussion is our goal. So discussion is good. Questions are encouraged. We really want to keep this interactive and do a true workshop flavor. Through the web page, which you can see down there at the bottom, that's the one that's got the github.io in the back. Bharat's been keeping up stuff, and there is a glossary available, and I don't remember which link. It's on that web page somewhere. Bharat can tell me where it is, but that's a glossary that we tried to fill out before this because we know that we have a diverse community here, and we have to spend some time leveling the playing field. And so we put some common terms that you might hear going around as an ability to jargonize. We'll try to expand that in real time. I'll try to, and other people try to pay in some attention there. I mentioned Valerie and Binji will help with some of the logistics. And I just want to emphasize before we start, Steve is not a solved problem. If it was, we wouldn't all be here. This is really discovery research. We have a lot to learn as a community, and we think that this particular assemblage of people is very, very powerful, much more so than individually people hacking away on their own. And we're going to assemble knowledge as we go. So we're not really going to have a canonical list of this is what Steve does, because honestly, we're still trying to work on it. The tentative schedule down on there on the bottom, which is also on the web page, just to show you what the blocks are. Day one, which is today, is really devoted to kind of bring everybody up to speed on the observational capabilities. In the first block today, we'll be talking about some of the instruments like radars, imagers, satellites, and then after a break, we'll be talking about the citizen science observational capabilities. And hopefully at the end of this day, we'll have a good idea of sort of what's out there in terms of what observational assets are available. Day two tomorrow has the first block in essentially modeling efforts. What tools exist to be able to try to model the things that we observe about Steve, or the ideas we might have about how it gets formed and its dynamics. And then the last block, Bea, for example, has put together a list of campaign events. Often the way to sometimes make some progress is to gel around a particular interval where we know we have good coverage and where there are questions to answer. So we're going to have a block there discussing campaign events, both the ones we know about and ones that we might do in the future. Then finally, the day three, which is on Friday, is really just to try to pull the threads together from the first 2 days, summarize where we think the common threads are, pick some future direction. And then after the break, we decided to do a discovery session, which is the, what is that? We all have piles of, I don't know what that thing is, but we saw it when we were trying to observe something else, or Steve showed up and then this other thing showed up. So maybe we can make some discoveries happen here that we could follow up on too, and then we'll close. So that's sort of the general framework of the workshop. Again, we've left things open in a lot of places. We want to encourage discussion. And finally, we do have a couple of moderators for each block, and we'll let you know who those are at the beginning of the block that are just going to facilitate flow and discussion in the block, make sure that we watch the overall time, but still let things flow. For questions as things go along, there is this link to Slido. Slido is sort of a place where you can ask a question, and you can also upvote another question that people may have already asked that you say would like to hear about. There's a link to that in the Connect tab on the website, and we can go over that when we start in here. Maybe Bharat could do that very briefly after we get done with this introduction. And then there is a social gathering site. Again, thank you, Bharat, on GatherTown. And there's a little image there on the right-hand side. And again, you can see the link on the Connect tab to figure out how to go into that. And that's where you wander around with a little avatar, and you can have, you know, interactive discussions with people who you're near. It's kind of an interesting tool. Again, see the website for links to that. So at this point, I'm going to turn this off, and I'd like to turn the floor over for a minute or two to Alan Liu from National Science Foundation, who would like to, I think, welcome us on behalf of NSF, who is very graciously providing the funding support for this workshop. So Alan, I will turn it over to you.
Hey, thank you very much, Phil. Thank you for the invitation. Thank you for the organizers to put this workshop together. So maybe some of you know, I joined NSF in early 2020, and this actually was the first award that I made. This workshop, when I look at the proposal, it's very interesting, and the way that it brings you know, citizen science community and the researcher together is a great idea. So I'm really glad to see that you know, after all the COVID challenges, that the workshop finally is happening. And also, I'm glad to see that I heard there are international participants from several countries, and also I see students participate here. So this is all very great. I want to mention that you know, citizen science, you know, at NSF is something we are very interested in supporting. In addition to this workshop, you know, NSF is supporting many other citizen science related projects. You know, the science that we're dealing with have become more and more complex, and many of them have societal impacts. So involving the general public together with science has a lot of benefit. You know, I'm sure you actually all know that. So I know this workshop will involve observation and the modeling aspect. And I hope there will be, good outcomes come out of the workshop, that you have follow-up activities. Phil mentioned some additional workshop, and I really look forward to have follow-up activities, come out of the workshop. So I'm sure you will have a very engaging discussion, and I hope you have a successful workshop in the next few days. And I probably will drop in and out, depends on my schedule, but I'm very interested in hearing the presentations whenever I can. Yeah, so thank you very much.
Thank you very much, Alan. And again, we really appreciate the support, and we will try to capture all the stuff that's going on in the workshop on paper as well, so that we can inject that into other things. Lovely. Thank you very much. At this point, we wanted to do an Indigenous welcome, really because, of course, the first people to see the aurora were from First Peoples and other sort of original inhabitants. So, and as a way of doing that, I'd like to introduce. Let me switch the monitor here. If he's ready, I'd really like to introduce Eric Rutanen, who's a member of a Finnish amateur astronomical club whose name I will not attempt to pronounce by prior agreement, but he can do that much better than for us. And I think he's going to have a few words of welcome from that point of view. So, Eric, the floor is yours.
Yeah, thank you. The astronomical club's name is Jyväskylän Sirius. It's a local astronomical club here in Finland, and we have actually done quite a bit of research concerning Northern Lights, or at least provided that to them. So, but I will now try to share my screen, see if it will work. And can you see?
It's working on it, almost there.
Yep, okay. Let's see if now does it work?
Still trying.
Okay, since this time is short, I'm just going to talk then. So, sure. If Finland, of course, is located quite luckily in the northern region, so there are quite many tales concerning Northern Lights. For example, in the Lapland, there are the last remaining indigenous people of Europe, the Sami people, and they have, of course, a rich culture concerning Northern Lights. If I would say there's a small difference between the Sami people and the rest of Finland, or the Finnish people, in concerning the tales. For example, for Finnish people, the Northern Lights are more of revontulet, which roughly translate to foxfires. And the tale is that there was a fox in the forest, and when it run in the forest, its tail or fur, depending on the source of the tail, it of course it would hit snow and trees, and when it did so, it sometimes puffed up the snow to the air, or its fur, it would brush against the wood and would create sparks, and from these sparks the Northern Lights were born, or from the snow. And in the ancient times, this magical so-called firefox, it was considered as a prized prey of the huntsmen, so it would very much sought after, and also because of its magical fur. So, but in Lapland, Sami people, they had much more, how to say, livelier tales concerning the Northern Lights, and they even had some tales that that presented Northern Lights as a little bit dangerous. Of course, in Lapland, the Northern Lights can be seen very much brighter than here in a little bit southern Finland. So of course it could be quite overwhelming to see the Northern Lights so bright. So they had these tales that were if someone made fun of the Northern Lights, for example, whistled or just made fun out of them, then the Northern Lights could take revenge on those people who insulted them by sending down an emissary, a Siberian jay. It's a bird native in Lapland and a little bit in here in southern Finland, and the bird would carry an axe with it, and with that axe it would kill anyone who would make fun of those Northern Lights. Also, there are tales that the Northern Lights they could swoosh down and burn the people who have offended them. So there's a little bit of this more, how to say, exciting stories in there. But also in here in other parts of Finland, there's also tales concerning Northern Lights, and for some reason there's quite a bit of stories that the Northern Lights are created from fire. So there's a lot of deviations from that group or single theme. So that's I guess I would sum up the tales in Finland. There's a very much different kind of tales. So this one was only a small fraction.
Thank you,
Yes,
Eric.
yep.
Yeah, that's our conference may be a tad bit more gentle than some of the stories that you just told, we hope. At least I hope that doesn't happen to me after my presentation. No, thank you very much. I think that the committee was looking for exactly that kind of introduction, just to show that you know, we talk about discovering Steve, for example, but discovery is a word that is often depending on the author who is writing the discovery. And as is usual, if you go back far enough in time, you find people discovering things long, long ago. And so I think what you're mentioning is a very good example of attributes of these emissions that people took and poured into, for example, mythology, which means they were observing. And that's really what we're going to start out with here, is how to observe things. So I thank you. Those are really very, very good examples. And we will hear from other citizen scientists throughout this workshop who, again, have other traditions behind them of observing things. We just happen to do it with fancy cameras now. Okay, so I think with that, we're going to jump into the first block of the meeting. And if you'll suffer hearing from me from a little bit more now, I'm going to essentially try to do something a little challenging, but I hope you bear with me and ask questions when I've been missing something. We're going to try to level the playing field here and try to just give a brief introduction to Steve, okay? And along the way, I'll try to define certain things that we tend to use. This is a challenging field, no matter how you observe it, in that there is a lot of background knowledge and a lot of acronyms and a lot of shorthand that gets used. And part of our job within this community is to try to help each other sort of get to a level field. And I think that that's what we're going to try to do to begin with here. So let me share. And then, so the idea is I'm going to give you this brief introduction to Steve, and then I'm going to turn it over to Bea, who's then going to talk about a very brief summary of the campaign events that we're going to be concentrating on in the second half. Okay. And then we'll go into future blocks where we have various people talk about some observational techniques that will be used, and that will really occupy the most of the day. So let me stop introducing myself there and get on with it. Let me push the buttons here. Hold on a second. Okay. All right. Oh, that's the wrong share. Bear with me for a moment. We're all so used to this world that it is strange when you can't press the right button. Okay, that's the one. There we go. So let me make that full. Wait till my screen decides to. Can you all see that full screen? Yes?
Yes.
Great. Okay, so I'm going to give this, but I have to give Bea an enormous amount of credit for doing a ton of legwork in getting a lot of the very nice summary material that you have here that I'll be describing. So this is just, again, an attempt to sort of remind us of a few of the things that may have led us here to this workshop in the first place. So the fascinating thing about the whole coupled near-Earth space, for example, is that the charged part of either the upper atmosphere or out into particles for example, in the part that we call the magnetosphere, they all care where magnetic fields are. And they all have things like Coulomb forces that influence them that are different than just collisional pressure or, for example, gravity. And so for that case, the field is really challenging because the magnetosphere ionosphere system, as it says here, is highly coupled. A field line can go Earth radii worth and then connect back on itself and hook one set of the system to another part of the system. So it really means that you can't stay completely local. You have to be both local and regional and global at the same time. That's kind of what it makes it so fascinating. And you know, in the equatorial plane, this thing called the plasma sheet. So here we are looking way out, right? We're kind of outside, in fact, the magnetic bubble that's provided by the Earth's magnetic field that's kind of creating an obstacle that the solar wind must flow around. The plasma sheet is kind of in the equatorial plane of that particular thing. And the plasma sheet has material in it that actually ends up getting connected to field lines and dumping momentum and energy in those field lines that's connected to the auroral zone, for example. And there's these, but the aurora, which most people are more familiar with, there's another part of this system that Steve actually lives in. There's this transition region where the magnetic field lines are transitioning from a stretched configuration, which you might see, for example, as you approach the pole, to a more closed kind of dipolar situation. In that transition zone, hot things overlap cold things. More dense things overlap less dense things. And that's where energy and momentum transfers. And it's a very chaotic, in some sense, but in some sense, variable and dynamic region. That's where the subauroral region is located. And frankly, if you go through the literature, the subauroral region is less studied than the auroral region, but yet has no less interesting dynamics. And the cool thing is that Steve lands right in the heart of all of that. And so furthermore here, let me get this thing to change. There we go. You know, this is, for example, one of the Ovation Prime probably or something else driven predictions of aurora, all right? This is looking again above, you know, the continental United States and into Canada, and you can see the magnetic pole, and you can see that the aurora is forming kind of a ring around that. That's where particle access is coming in from field lines that are so open that they're connecting to large parts of the magnetosphere and sometimes even to the solar wind. You put the sun over here, okay? I think that's the sun, and there's the aurora borealis and aurora australis, of course, in northern and southern hemispheres, but the subauroral region is here. It's kind of in that boundary as we're approaching this dynamic region, but yet we're not there yet. We are still on field lines that are not completely open and flapping, for example, on the solar wind. How do we, this is a vast system, right? And frankly, it's still poorly sampled, but we can do some things. We can throw satellites into it, and that's what Bea has on the left-hand side of here. You can throw the Themis satellite. You can throw the DMSP satellite in low Earth orbit. You can throw the Van Allen probes, which are looking at the radiation belts. You can explore different regions of the magnetosphere, the part outside sort of the closed field lines with a lot of plasma on them. Some of them are way out in front and only measure the solar wind. Some are in that equatorial plane are measuring the plasma sheet, and other ones measure the radiation belts, very high energy charged particles. On the right-hand side, you can do things from the ground, because if these magnetic field lines are mapping to different parts of the magnetosphere, the ground view is literally a different fundamental view, and it's almost a screen on which you are seeing processes evolve that are tightly coupled to the overlying magnetosphere from an electrodynamic perspective, and sometimes from a particle perspective, a very direct material entering. How do you do that? You have these all sky cameras with different wavelengths. You can stitch them together like you see here in this Themis sort of all sky imager network. These reveal important magnetospheric dynamics by watching the response of the system. You can put magnetometers under them, which are measuring horizontal currents that are flowing about 100 kilometers. You can use a radar, like in the picture behind me, to reveal the motion and the background plasma dynamics. And you can use ionosondes for the first ionospheric radar, because they're less expensive. You can put more of them out there. You can study variations of Earth's ionosphere. So we have these tools. For Steve, like I mentioned, discovered in the modern era. You can go back and you can find references to this earlier. You know, by people in Alberta, some of whom we have on this call. Other, as I mentioned, earlier reports in the literature, it was a well-known phenomenon among amateur auroral photographers like the Alberta Aurora Chasers, but it really has, it's a completely new focus for the scientific community, although in retrospect, maybe we should have been looking there. The emission is fascinating. It's a purple structure, certainly to cameras there, located in the subaraural region, like I can animate, whoops, if I click on this, I think. No, it's not allowing me to do that, rats. Anyways, it's in the subaraural region, like I mentioned, lower than the latitude that auroras are observed. It's different from other subaraural emissions that you'll hear later in this conference. And there's this other thing like the picket fence, which is at least visible in that screenshot there. It's got some very, very interesting detailed structure. And also you'll find out in a moment that the emission can also be very, very broadband in color. It can also be nearly white. And we should remind people that the name Steve, it has a backronym now, and that someone has actually made an acronym that spells Steve, but originally that came from the photographers. It was an acronym without necessarily a physical meaning attached to it. Anybody who's seen the movie Over the Hedge, there's a critter named Steve in there. And so unlike a lot of things in our field where the acronym is picked first, knowing what the physical process is, here the acronym showed up and then someone said we should make it mean something in this case. And I'm sorry, Robert Downey, that this movie isn't working right now. So for the broadband emission, okay, if you take this very nice spectrograph, and we'll hear about, I think, from Megan, perhaps from the University of Calgary, coming up in this block, and you look at this plot here, which is essentially wavelength in nanometers, and versus intensity, really, and you take that spectrum, okay, and you in fact image this spectrograph at different places within this particular picket fence emission, the structured green emission. And for example, the green trace is the background emission without the picket fence poleward of where it occurs. The red is the emission equatorward of where it occurs, and the blue is the picket fence. And if you look right here, you'll notice that the picket fence spectrum, where is the blue line peaking up? Really, there are some minor details, but mostly it's in the green line. And that's about 2 kilorayleigh. And Wikipedia is your friend if you want to know what a Rayleigh is, right? I mean, the typical night sky is about 250 Rayleighs. This thing is 2 kilorayleighs. A really bright aurora you can almost read a book by, and that's up to 1,000 kilorayleighs. So this is still a faint, relatively faint emission, but it's certainly going to be brighter than the background. And that special 5577 angstrom or 55.7 nanometer emission is in the green. And that's a line, that's a photon that gets emitted by oxygen when it gets excited. So you're starting to figure out things. If you look at the background emission, and again, the blue is where Steve is, where the green and the red are kind of polar and equatorward. This is fascinating. It seems to be fairly continuous. The background is being lifted across almost all wavelengths. It's slightly elevated at another well-known line at 630 nanometers. That's a red line. Again, that's oxygen. If you dump some energy into the oxygen, you heat it thermally, you're going to get those photons. So that tells us there's some heating going on. And here the intensity is 6 kilorayleighs greater than the surrounding background emission. So the green line was a little fainter. Remember, your eyes are tuned to green. So sometimes in these photographs, the green might stand out to you compared to the background emission. But certainly, again, for reference, still something you can view. So we know a few things. What else do we know? Bill Archer, who again is here at the conference, which is great, actually then did image triangulation. So you actually do the geometry, you look at it with more than one camera, and you try to localize it in altitude, because if you're looking under it, sometimes that's a little difficult to do. And what he determined was the picket fence and the broader Steve emission were at different altitudes. The picket fence is extending between 95 and 150 kilometers altitude and is very highly aligned with the geomagnetic field. At those latitudes, the field has quite a tilt to it, and that's where those things line up, as you can see these particular marked 1 through 8 arrows here. But Steve is a more broad altitude spread between 130 and 270 kilometers up here. And that was corroborated by another triangulation study using more optical instruments. So this isn't, this was confirmed. Now, the interesting thing is, where is that? Well, the upper plot is the thermosphere. That's the structure of neutrals, which in this case, we're organizing by temperature. So you go up from where we live in the troposphere. Temperature goes up in the stratosphere and then turns around and goes down in the mesosphere. Coldest part in the atmosphere is located about here at the mesopause. And then things get hot again up in the thermosphere. Remember that the density is falling off. So Steve is occurring in the lower thermosphere, all right? The continuous emission overlaps the F region of the ionosphere, which is where the electron density peak occurs in Earth's ionosphere. And that's a place where electrons and ions are not collisional. They're moving together, okay, in response to things like electric fields. But the picket fence down here in this sort of 100-kilometer region, that's a very special place, because that is the place where electrons are still highly magnetized, but the ions are now colliding enough with the neutrals, they can move across field lines. On a lot of current, you get horizontal currents in there, but remember that in darkness, the E region disappears shortly after sunset. So we know it's low conductivity, but it's kind of interesting that picket fence is occurring at this very, very special place, a relatively thin place in the upper atmosphere. So that's another thing that we can add on to what we have known. We then need to sort of think about where this is in relation to the whole Earth's electric current system. And it turns out Christian Birkeland, probably more than a century ago now, had worked out that there are electric currents that are being connected into the upper atmosphere from the generator that is proposed when the solar wind blows across a magnetic field, which is sticking out of the planet. That V cross B generates a potential drop. And that potential drop drives currents. And there are region 1 currents and region 2 currents. The region 1 currents are the ones, you'll notice they're in different directions. The region 2 current is going into the planet, and then essentially kind of like a impedance connecting through the lower atmosphere, again, near that 100-kilometer range, and then exiting out, okay? The region 1 currents are going in opposite directions. This is dawn over here, and this is dusk over here. So the point is, there are these current systems that we know about in the planet. This region 1 is a much more intense current system, field aligned, than the region 2. The region 2 is spread out over a larger range, but it's flowing at subaurora latitudes, again, where Steve is occurring. And the interesting thing, though, is that because when they defined current, they defined it not as the motion of electrons, but the motion of positive charges. Remember, a downward current is upward electrons. So if you look over here in dusk, you will see that the region 2 current, the current is flowing down. That means the electrons aren't going down and hitting the atmosphere. They're actually flowing up. So this and a couple of other studies led to people that said, no, Steve is not driven by sort of impact precipitation of the kind that we're used to with a normal aurora. It must be due to something else. So that's another sort of thing to remember where Steve is in this connected system. And so then you get the work of Brian Harding in 2020. It says, well, how is the broadband emission being generated? And really, what you're getting is collisions between those ions that are moving and the background neutral density, like N2. And there's a little, inorganic sort of pathway here. Eventually, you dump energy into NO. NO reacts with oxygen, and you get NO2, and you get a photon coming out. But from chemistry, know that you got to dump in 3 electron volts of initial energy. That means that if you're doing it by kinetic energy, something slamming into there, you work out 1/2 mv squared. You got to have something moving a few kilometers per second. Remember that low Earth orbiting satellites move at 7 kilometers per second. This is a good fraction of a normal orbital velocity. This is really fast stuff. It turns out that we knew about something that was moving that fast, something called an SAID. These have been discovered by not only low Earth orbiting satellites like the DMSP cluster, which is pretty far up there at 840 kilometers. They've also been seen magnetically connected to things like the Akabono satellites, which are out at 10,000 kilometers, and are seeing the same electric field structure that what it's driving is a very fast moving channel, very narrow, less than a degree wide, but really, really fast, like a few kilometers per second. At severe storm times, you can actually get these very intense narrow channels happening. This is a classic signature of extreme magnetosphere-ionosphere coupling at subaraural altitudes. We've known about this for a long time. It drives another instability that we actually see very brightly in things like the UHF radar behind me. So we knew about SAIDs, but the interesting thing is that the research was able to connect those to the emission of Steve. So this particular track here is another satellite swarm. The swarm series of satellites run by the European Space Agency are about 500 kilometers approximately altitude. It's a little lower than DMSP. But if you look at the luminosity, which is this top plot where Steve is occurring, so you've got this Steve signature. Here's latitude, so it's reasonably narrow in latitude, degree or a little bit less. What do we see in the westward ion flow velocity? That's, by the way, a northward electric field. If any of you have forgotten your right-hand rule, you can borrow mine. Look at the velocity. It's a few kilometers per second. It's good enough to excite that emission. There's a small current associated with it, but look at the electron temperature, way over the background, 6,000 Kelvin. It's also located at a very sharp boundary. Electron density gradients are the source of energy in this system. Whenever you have one of those, instabilities like to live on the edge because there's a bunch of instabilities that feed off that gradient. But as I mentioned, because of Bea's work and Toshi's work and other people, we don't associate it with the particle precipitation. We know, so it's not really an aurora in the traditional sense. But we know these other facts about it. And I think we're going to learn about more facts as we go here in this conference. It's also been seen, not only that all sky camera, you zoom in, there's Swarm's track and there's Steve. So I've tried to do satellite conjunctions, and this is like hitting a home run. This is amazing that such a narrow feature, you actually ran the satellite footprint right through it, but it happened, which is really fantastic. Is that normal? Was this only one event? You always have to ask that. But Bill went further and essentially compared SAIDs that were measured for Steve with ones that still occurred but were not associated with Steve, and found out a bunch of things. For these few events, Steve had faster flow velocity, so these were more intense SAIDs with lower electron densities, meaning the conductivity down there, the resistor, if you will, shorting it out or not, was lower, and the temperatures were higher. So that Steve is not only going to happen whenever you see an SAID, it's really got to happen in the most extreme SAIDs. And I think part of the mystery that we can explore this week is which ones and how often and what is that population? And is there anything else characteristic about it that we will notice that will tell us more about this physics? And just again to de-jargon, you'll hear the subaraural polarization stream, or SAPS, mentioned. This is another bright subaraural feature. It's essentially something that's broader than an SAID. And this particular plot here this is longitude on the bottom, this is latitude, and this is the subaraural polarization stream from Millstone Hill, the radar behind me, scanning across this field. The yellow is nearly 1 kilometer per second. So this one is broader, not as fast as an SAID. This will last for hours in the dusk or evening sector, again at subaraural latitudes. SAPS can get up to 1,500 meters per second. SAIDs have been seen sometimes within the SAPS as fingers of very, very fast flow on top of this broader signature. There's multiple theories to explain this, and I'm not going to get into that right now. We might get into that discussion a little bit later, all of which are linked to this tight magnetosphere-ionosphere coupling. And the only thing to say here is that SAPS as a flow channel and as broader than SID is important because it actually overlaps the edge of the plasmasphere. And when it does that, it actually rips electron density off the edge of this cold dense part and makes a river of plasma that actually feeds backwards all the way up to noontime, where it ends up flying out of the planet and populating the magnetosphere. So even SAPS that SAID and Steve are working within, for example, sometimes, is a very important way for getting oxygen out of this planet and out into the magnetosphere, where it profoundly affects mass and energy flow in the entire coupled Earth-Sun system. Steve is occurring all within this dynamic region. Finally, you're going to hear me mention TEC, which is total electron content. I will go over that in a little bit, but just to tell you, that's kind of the number of electrons in a column above a particular location. Kind of think of it as the thickness of the ionosphere. And this diagram is not meant to scare you. It's just to conclude to say, all of this is occurring in the subaraural region. It's just as complicated and fascinating a place as the auroral region. Understanding Steve, whatever we can understand about Steve, will help us tease apart which of the various arrows in this box are happening at which time. And it really drills into the whole coupled system, which I think is really fascinating and very exciting, considering how many extra observational resources we can now bring to bear in this community. So I'm going to stop there. I'm going to turn it to Bea. Bea, you can just kind of put up your campaign summary.
Sure. Thank you, Phil. That was great. Any questions from anyone? Please feel free to unmute yourself while we're changing slides.
Yeah, I threw a lot of jargon in there.
Okay, so I have a naive question. So I think this is one of the things that hopefully this workshop give me clarification, but there's a lot of chicken and eggs question that popped up in my head. There's a Steve, there's a SAID, and there's a SAP, and then there's substorms. And then, you know, so I think this graph, maybe the one that you're showing, what's going on, is the one that,
sorry, there.
But like I guess that's where things stands, right? I mean, well, we don't, so what is actually bigger, what is denominator for this, all of this? And then what has to happen first?
So this is the, so Tomoko, the problem is, I think that we are literally just at the beginning of even understanding how many boxes are on this diagram, right?
Yeah.
And then, you know, and in our field, people love to be reductionist, right? I'm only going to vary that thing. And we all know that everything is happening at once. The question is, under which conditions are which drivers more important as opposed to another one?
Mm-hmm.
And what you're also referring to is the preconditioning. Mm-hmm. How much do the background conditions coming in make a difference?
Mm-hmm.
Is this thing totally chaotic? No, probably isn't. Like, okay, you know, we just can't predict anything. No, there's probably still some principles there. But Bea, you know, you've done much more work on this than I have. But I think for Steve, I think we're just at the beginning of even understanding the general picture. It's like we've poked at a couple of small things here.
Absolutely,
so
yeah.
Work in progress.
Okay.
Evgeny, hello.
Oh, hi, Phil. Yeah, it's concerning the happening at once. It depends on the time scale, okay?
Yep,
Thank you. Now we know that first SAD occurs during at least individual substorms. And after that, when substorm current wedge or westward traveling surge is formed, then SAPS appears on the dusk side. So it's a time difference about 10-15 minutes between that. And basically, during recovery phase, and Steve is definitely the recovery phase phenomenon, then, you know, you have really multiple events occurring at once. But basically, the characteristic of Steve, the typical characteristic of Steve you just reviewed, are of course set, not set.
Right. No, absolutely. I just wanted to point out that there is this other broad feature that's occurring.
Oh yeah.
But
yeah,
and this is the tricky part that we have to watch. We have to make sure that we keep everybody up to date. Is that it's very easy to, when we hear a new term, to think, oh, well, that is also a factor. But you're right. Different things occur at different times, and the real question is, does an earlier thing occurring precondition the system differently, for example, so that maybe you get a different fine scale response? That
Yeah.
very well could be.
No, absolutely. For example, if you are during multiple storm time substorms, right? Then of course conditions are changed, and so you have, for example, injections hitting not near midnight but more to dusk side. So you have kind of mixed of events. So.
I agree with Evgeny, and when we think about commonalities, as Tomoko was saying, in my head, between SAPs, enhancements, SAIDs, and Steve, if I think in something that is a common thing that occurs for all of them is substorm. The timing might change, but substorm is always there. And this is an important question for the workshop itself, because I know when we talk about preconditioning, hopefully Lindsay Goodwin will be showing us some results that she has been obtaining from incoherent scatter radars before Steve is observed. So those are still very much open questions.
Yep. And the last thing we should tie in here is that the citizen science observations here, you just heard the word timing. How many times did we just say timing? That ability to time when things are happening at different locations is really critical and is not something that we necessarily are doing just by default with the instruments we have. So I think we have a large role to play here. Bea, okay, I'm going to stop here sharing because I can find the button, and then, or you can just take it from me, I think, if you want.
Yeah, continue.
Oh, there's my cursor. Perfect.
Can you see the presentation mode?
Yes.
Perfect. So as Phil mentioned at the beginning, the main objective of the workshop is discussion. And we have selected 2 campaign events. I know 2 events are not really representative of everything that is going on in Steve and in the magnetosphere and in the ionosphere. But as also Phil said at the beginning, this is just the first workshop and we're planning to keep adding more events. In the emails that we sent, we told you that we will be analyzing 2 events. Yes, 2 events. And this is the first event. Sorry, I cannot see my title there. It's covered by the Zoom. But the first event is a very interesting event happening in 2008 March from the 26th to the 28th. And Steve is observed intermittently in 3 different locations. So for the first interval, Steve was observed in 2008, March 26, between 7:20 to 9 UT in the Alaska sector. It was visible by the Themis all sky imagers at Gakona, Whitehorse, and McGrath, and is in this area over here, marked with number 1. The second interval was observed in 2008, March 27, between 3 to 4 UT, also by the Themis all sky imagers in Pinawa, so roughly in this location over here. Interesting for the interval number 2, this is early in the Themis ASI era. So unfortunately, the high resolution Pinawa data is lost, and all what we have is the kilogram and the summary snapshots. Eric Donovan is positive that we could take those images and still map them to their respective location and work with them. So I'm positive about that. And in the third interval is 2008, March 28 from 2 to 3 UT. And this is again observed by the Themis ASI at Kapuskasing, and this is in Ontario, Canada, over here. The reason we have selected this event is because especially for March 26 and March 28, there is a very large amount of research that has been done. And I know Tomoko and Valerie and Liam have been looking at March 26, and they also have very interesting results with the AmGeo data. The idea is that everyone that has done something for any of these events could show some results on tomorrow in the second session. So when we look at the first interval for this event, I quickly look at all the conjunction with satellites that we had for this one. So this is the one occurring on March 26th. And for this one, we had the stations are over here. So this is McGrath, Gacona, and Whitehorse. We had Themis ASI crossing close to that location. Ghost 13 and Ghost 10 and Ghost 12 too were relatively close eastward located. And then NOAA 18 was also in the eastern portion, sorry. In addition, the MSP 13 was passing, but in the southern hemisphere. That's why the line here is thinner. On top of that, I know that Toshi Nishimura in 2020 published this paper where he observed for the same event, the MSP 16 and 17 data, and hopefully we can discuss some of the results that Toshi obtained in this research. He also had SuperDAN data at that time together with the All Sky Imagers. For the second interval, as I told you, this data is partially lost, but still usable. When we look at the conjunctions, we had NOAA 17 passing right through Pinawa here. So this is the station. We have the SAMPEX satellite passing westward. FAST is also westward, but I'm going to burst everyone's bubble here because I checked with Bob Strangeway for FAST data, and the data is not available for FAST at that time. So unfortunately, we have it, but we don't have it. We also have passing westward the MSP 13 and NOAA 15 satellite. When we look at GOES and Themis, we also have them located relatively close to where this event happens. Finally, for the last interval for March 28, we have, when we look at the satellites, we have NOAA 17 passing right by Kapuscasing, and this is the data that we published with the post-17 satellite and the precipitation relationship that we can look again back at the data. The MSP 15 is westward of Kapuscasing. FAST is again there but not there, and the MSP 17 and 14 are also available westward. Personally, I always like to look at the westward satellites when we observe Steve, because since we know that the structure moves from east to west, it's always interesting to see if we can see the SAID feature in the DMSP data. On top of that, we also have some of the Themis and the GOES satellite located forward of Kapuscasing. The last event is a very interesting event. This is 2016, September 3rd, and this is an event that is driven by citizen scientist data. And this event was captured by 3 people. Chris Ratzlaff is the photograph is from Chris Ratzlaff, the one that we have in the left. In the center, we have a contribution from Neil Seller, and Mike Hanako has in his database that is very comprehensive a report from this observer that is called Bob Consimius, and he's at Itasca County in Minnesota. So when I look at all of these 2 are coming from Alberta, and this is from Minnesota. This Steve event roughly covered this sector over here. Unfortunately for this event, we do not have Themis or Rego ASI data, so this is going to be slightly more challenging, but we have, many of us have worked with citizen scientist data before, and some people in this workshop today are expert on that. So when we look at potential conjunction with satellites, we have Cassiope here in the west. So this is, when we look at, to locate you a little bit better, so this was from Minnesota to Alberta. So roughly, the stations that we were looking at was between Pinawa and Athabasca over here. So it's slightly eastward of Pinawa, just as a reference. So we have Cassiope a little bit east, carrying the EPOP instrument. I'm curious to know if Gareth can see data from that satellite. We also have DMSP. Let me see, no, this is Firebird. I cannot see the names. Give me 1 second here. This is Firebird 3 and 4 eastward of the observation. We have time passing very close by, and then we have the MSP 17 and 18 westward of the observation. In addition to that, we have the MSP 19 and 18 in the Southern Hemisphere. And we also have MMS, that is this cluster over here, and some of the GHOST satellite located over of these observations. So hopefully all of that, we can come through all of that data and take a look collectively, and this will drive discussions. Do you have any question?
I have a quick question about Firebird. What's the payload that measuring BDM parameter?
I'm not sure about that. I can get back to you after I check. I have never worked with Firebird.
Isn't it IR? Like it's a Earth science mission, isn't it?
I think so, yeah.
I think they're measuring IR. No.
Could be.
Infrared.
Yeah, Tomoko, I don't have anything.
Oh, okay.
I don't have any coverage of that either, but now we have we should follow up on that. Yep.
Yeah. And then when you're showing goals, and then those are basically what's you try to connect the dots that what's happening in a plasma soil radiation belt.
Yes.
Okay.
So the idea is to also look at the magnetosphere and analyze the state of the magnetosphere prior, during, and after Steve.
Okay, thank you.
Anything else for the moment?
Yeah, this is Gareth. Just to answer to Bea's comment about EPOP on this particular day. EPOP was active with the ion mass spectrometer and the MAG instrument, starting at 5:42 at 47 degrees. So in the vicinity, but probably
A little later than the block that you've got there. Yeah. Okay.
Yeah. So, which is better than most. So.
Do you think we could look at the data tomorrow in the second session?
We could try. I can download the quick look plots. Whether or not I could decipher them in time is another question, but we can try.
Perfect.
Anything else? Okay, I think Bea, I'm going to move along. I'm going to try to save a little time here and shorten up so the order here is that the next 4 blocks here are brief summaries, again, to try to level the playing field for sort of professional, I'm not going to call them professional, I'm just going to call them observing networks that, for example, have been funded by agencies, for example. And there's a diversity of techniques here. And so we wanted to sort of give people a chance to just lay out what is a typical output from this instrument and what is it measuring. So I'm going to start that off with a kind of a kind of grab bag of a couple of different things. I'm going to turn that over to Bharat and Gareth and Lindsay, I don't know who's presenting, to talk about a little more radar measurements of ionospheric motions. And then Megan Gillies is going to talk about like the T-Rex spectrometer and the other things that University of Calgary has been doing to look at optical stuff. And then I think, Carlos, you're going to lead just a discussion on all sky cameras and other things that the Boston University group is doing. And then after that, we will just walk into a couple of contributed things and interleave with the discussion for the remainder of our time. So just an idea of what's coming up. All right, let me find the right window here. And I'm just going to sort of attempt to normalize you on a couple of things here. Again, as briefly as I can manage. Okay, push the right button, Phil. All right, this one. Okay, and let me hit the button here and go like that. Okay, so I'm going to cover a couple of different things here. So for those of you who aren't familiar with that, you may see the word TEC, total electron content. And just very briefly, we're not going to go into this technique in detail, but this is an offshoot of the Global Navigation Satellite System. Used to be only GPS, now it's GPS, GLONASS, Beidou, Compass, Beidou/Compass, EGNOS. There's a bunch of them up there. And the idea is they're navigating, like when you're driving your car or you have your phone, you're receiving a signal which leaves those particular satellites at a precise time, and those are all atomic clocks that are maintained by the government agency running the satellite. They propagate through the ionosphere, and then the delay between the satellite and you forms one leg of a navigation solution. If you have 4 or more of them, you can determine where you are on the planet. However, the receivers, if you have a receiver that receives on 2 different frequencies at the same time, the ionosphere produces a delay in that signal that you actually have to take out. Otherwise, you would make a slight navigation error. Rather than throwing that data away, you can actually use that then to determine the total number of electrons along the line of sight between you and the satellite. So you can actually generate a ionospheric product. It's an integrated one. So it's the integral of all the electrons along that line of sight. And it's really taken place because there's all of this billions and billions of dollars of investment in the navigation cluster that we can kind of leverage to do that. And so our community for the last 25 years has been using this as a wide scale product on the structure of the ionosphere. For example, this is just the spots that, whoops, that particular plot on the right-hand side are the spots you get from the network of about 6,000 worldwide science quality geodetic receivers that are really designed for earthquake research. That's in one 5-minute period. So you can see how many places you get this measurement. And then you boil that data down. You might bin it all up to be in vertical pixels, for example, above given spots. Obviously, the coverage is not great over the oceans where nobody lives. And there are still parts of the planet like the northern Asian continent into Siberia and the upper part of what used to be the Soviet Union that are still relatively little instrumented, but you'll notice the coverage over Europe, and you'll also notice the coverage over the United States. It's really good. And those are the subaurora regions where, for example, Alberta aurora chasers are imaging Steve, for example. The data comes across initially as this. For example, the simplest product is to take it and bin it vertically. You take all the ray paths and you assign a place where they pierce the ionosphere and you put them in a bin. And that's that lower right-hand plot there, which is essentially this pixelated measurement of the total electron content. And that's in these things called TEC units. That's 10 to the 16th electrons in a column, a meter on a side, meter circular, meter with a meter radius. So, sometimes you'll see TEC plots with this kind of representation, and there are occasionally sometimes that people do some further filtering. Those of you who are familiar with image processing, that's kind of like running a blurring kernel over this map to reduce some of the noise. So you'll see kind of both flavors. But when you hear TEC and you look at TEC maps, you can see these are wide scale measurements, relatively coarse compared to, say, a individual radar or a satellite going through, but they help you set the crucial boundaries. Where is the boundary where those field lines are starting to get turbulent in the subauroral region? These things, as this evolves over time, can help you answer that. So we have these TEC products available to us. So that's one thing you're going to hear. Another thing you're going to hear, if I can click on the right thing here, TEC often has structures in it. And in fact, in particular in the subauroral region, you'll see this word SED, which stands for storm enhanced density. As I'll talk about in a minute, when that SAPS, when those SAPS, maybe more of those SAPS broader channels overlap the edge of this dense plasma that's occurring as you go to mid and lower latitudes, density times velocity, you get a mass flow. And so what you get are these plumes, or we call them, or places where the electron density is enhanced across subauroral regions, because this is now going through the subauroral region. Look at the sharp gradients on either side. And again, nature doesn't like gradients and generates a lot of instabilities and other action at the edges of this. So when these structures show up, and sometimes they do during storm conditions, especially extreme ones, for example, where Steve might show up, or what effect does this have on Steve? I don't know. All right, but the point is that we've been studying these SED plumes on their own for a number of years now, and that is another thing that happens at subauroral latitudes that shows up most easily in these TEC maps. We mentioned DMSP, so I'm going to switch over to one example of an in situ satellite, and Bea showed you the ground footprints, for example, of these magnetically following the field line down from where they are. DMSP is a series of satellites that is maintained by the US government, essentially by the Air Force. They're fairly far up there. They're at 840 kilometers altitude, but the interesting thing is they have a full plasma sensor suite. So they really are making fundamental plasma measurements in this environment, the top plot shows you electron density. Notice that suddenly there's, for example, a very large cavity in electron density. This plot, for example, goes from the South Pole towards south mid-latitude. So this top number is the latitude. So here's approaching the south polar cap, way down here, and then this is south mid-latitudes. The middle plot here is velocity. It has a velocity meter. So it's measuring the velocity of the ions and electrons moving together. The horizontal velocity, which is what we were talking about when we talk about SAID or we talk about SAPS, that's a horizontal velocity. That's in blue. In this case, it also happens to be accompanied by a large vertical velocity. That's in red. DMSP measures both of those. The satellite carries a magnetometer, which again, if you do your right-hand rule, will tell you something about flowing currents. Remember, I mentioned those Birkeland region 1 and region 2 current systems. There can be finer scale currents embedded in here. And DMSP also has particle meters. So they're looking at electrons and ions, and they're measuring the flux of particles as a function of energy. That's this axis here, up to 30 keV, and ions also up to 30 keV. And a magic thing that you will also find is if you look at the equatorward boundary going from the pole of where the electrons stop precipitating, that's a marker of kind of the auroral boundary. Many people use that. But you can see what comes out of a DMSP plot here. So this is in low Earth orbit. And this, for example, is a plot of all the DMSP orbits in a particular day. It's a polar orbit. It's going around. It repeats with about a 102-minute period. And remember, it's moving about 7 kilometers per second as it does this. The times here on this plot, for example, on this day, which, by the way, is one of the campaign events that Bea mentioned, are the equatorial crossing points of those particular orbits. So you can see that, for example, this orbit, which goes over subaraural in the eastern Canadian Maritimes, the next orbit is in Saskatchewan or in the middle of the prairies, and the next orbit is getting to the point where you're going through the western part of Canada and the western subaraural region. And remember, it's going to take 100 minutes to get from here to here to here. These satellites are at fixed local time. So the local time underneath the satellite, it's really either like dusk or it's dawn, for example, usually like 18 UT, 18 local time or 6 local time. So they give one view, all right? There's usually 4 of them operating at one time. In 4 orbital planes, although they like to sort of collect them into a couple. Unfortunately, DMSP, the last satellite was built 15 years ago, and this constellation is gradually disappearing. And within the next decade, we will not have any DMSP satellites up there. Right now, I think there are 3, if I remember operating correctly. But if you go back to some of the data that Bea was showing you in campaign events, you probably will have 4, sometimes even 5. This is just another example. It's another way to plot. Now this is a path that goes over the pole. So you start, for example, in the northern hemisphere, mid-latitude, you go through subaraural, you go over the polar cap, and now you're on the other side of the planet. So where here it was 18 local time underneath the satellite, now it's like 9 local time on that other side because it doesn't quite go exactly over the pole. The electrons are up here and the ions are up here, and you can very clearly see the auroral boundary. See how sharply that precipitation cuts off right here. If you have good eyes, you'll see that down here, there's a horizontal velocity. That, for example, is a extended subaraural polarization stream right there, probably right in there. It's in a place where the electron density is falling off with all sorts of structure. So these are the sorts of things that you get out, for example, a DMSP. This is an example of in situ data, data that's being taken by the spacecraft as it's moving. There's a very I'm going to conclude here with a very powerful technique that gets used from the ground. It's something called incoherent scatter radar. Other communities know this as collective Thomson scatter. This is essentially where you're scattering off the free electrons in the upper atmosphere, in the ionosphere specifically, but you don't get information just about those electrons. They're bound by Coulomb forces to the big, heavy, pokey ions near them. And so you can learn things about the ions as well as the electrons. And because this is such a weak scattering cross section, the best it ever gets is about, minus 60 dB over lower, 6 orders of magnitude lower than a square meter, which really means it's like a BB. Okay, that weak scatter means I can do the entire ionospheric profile, rather than an integrated measurement or a measurement only at a particular altitude. However, it's complex. You need a megawatt class transmitter. You need a tens of meter or diameter antenna like the ones behind me to do this, mainly because the scattering is so weak. But beginning in the late 50s, people worked this out. And that's the size of the two antennas we're talking about. So these are not everywhere in the world. They are now as ubiquitous as ionosons. They're relatively expensive instruments, but the technique is reasonably well developed. For the purposes of this workshop, there are many things you can measure by measuring sort of the spectral broadening of the radar echo that you get when you send a pulse up. You can measure things like the electron to ion temperature ratio of the background plasma. You can measure the electron density. You can measure the line of sight velocity by watching this thing move back and forth. So there's lots of things that a analysis code can get. For people who are doing the science work, this is all under the hood, right? You get things like this. So this is a plot of electron density on a log scale from over 1 day in the life of the subaraural ionosphere, because this is pointing straight up from here, mid-latitudes. This is altitude from about 150 kilometers to 700 kilometers, and or 800 kilometers for reference. Where's the space station? About here, down here. So you're getting into the F region and beyond. You can see the topside part. This down here is a blow up of the bottom part, which is the E region, where that picket fence was overlapping. And look at the altitude scale. It's only from 100 to 200 kilometers. We use a different technique here to get much finer scale kilometer level resolution in altitude, which is up here, it might be 30, 40 kilometers. You get electron density, full profile out of that. You get electron temperature. Can we tell where the sun turned on? Well, right about there, right there, sunrise. And this is the E region. You can get ion temperature, which, by the way, you'll notice is not the same as electron temperature, because the electrons and the ions have different thermodynamics. And finally, you can get line of sight velocity. So you can actually not only measure if the ionosphere is going up and down, but if you take that steerable antenna right over there and you tilt it in a particular direction, you can start to derive vectors, okay? There aren't that many incoherent scatter radars. For our purposes here, there are some at mid-latitudes. Millstone Hill here has a fairly wide coverage view, okay? There were radars in the UK and France, which we have historical data for, but probably not during the period where Steve events might occur. And there are other ones in the former Soviet Union. There's the Kharkov system in Ukraine, and there's Irkutsk in Russia, Siberia, excuse me. And so, in the future, collaborating on mid-latitudes with those other facilities is something we can think about. This is the power of this technique. If I take my steerable antenna and I put it flat down nearly 0 degrees elevation, I can point it about 4 degrees, and I rotate it in a circle from south to north, I get tremendously wide coverage, and I can start to identify regions. There's where the SAPs and SAIDs live. This is where the boundary layer is, where that cold plasma is being overlapped by hot tenuous plasma. And then we're getting into high latitude regions here. So this is a different perspective from the ground, but another thing we can put on the table. You've seen this already. This was generated using incoherent scatter down here, all right? Just to mention that there's this SAPS flow, and as Evgeny said, maybe SAIDs develop first and then SAPS follows. It's a complicated dance. But this storm enhanced density plot, which I'm showing you down here in a fairly classic figure of, this is total electron content. What are the effects on Steve dynamics? Just to put it on the table, that if you take that radar data and replot it, kind of like a satellite would, where you have invariant latitude, that's magnetic latitude going from lower to higher, you can see the subaraural polarization stream here. You can see the auroral oval. You can use DMSP to mark where the boundary is, where those field lines are becoming open, where precipitation is taking place. And you can measure electron density with the radar. So you can kind of create different views here with different characteristics. And in this red region here, where you've got the edge of that flow channel moving westward, overlapping the higher density, you can generate one of these SED plumes. So that's where I'm going to stop. And because you've heard enough of me right there, and just make sure that there aren't any large questions before I turn it over to Bharat and company. And I'll be around.
Thank you, Phil. This was great.
All right, I think we should move on. So is it, Gareth, are you presenting? Is Bharat presenting? Who's presenting
You
here?
know what? We haven't decided, so I will just go ahead and drive for
Awesome.
all of us here. How about
Awesome.
that? Let me share. Everybody seeing this?
Yes.
Yes.
All right. Lindsay, did you want to take it away? Your slides are up first.
Yeah, sure. So yeah, my name is Lindsay Goodwin, and I'm going to start off this presentation, but I'm only going to be really presenting 3 slides. So I'm going to be here quickly and then disappear quickly. So if you want to go to, oh, there we go. I'm looking at the wrong screen, which isn't very helpful. There we go. Phil, he gave an amazing introduction into inquiry and scatter radars. I love inquiry and scatter radars. I've taken the Millstone Hill tour of ISRs like 4 or 5 times. I love them so much. But I want to add on a little bit more to what Phil said. So yeah, like ISRs are the powerful technique, these powerful instruments that are able to look at multiple different plasma parameters, like ion temperature, electron temperature, plasma density, as well as the line of sight ion velocity as a function of like range and time. But there's also like 2 different kinds of ISRs that you can talk about. There's the one that's pictured behind Phil right now, which is like a steerable dish that do these very powerful scans. There's also these ones called advanced modular inquiry and scatter radars, which like don't look like they're still pretty cool, but they don't look quite as cool. And you can see a picture of that over on the left, which it's generally, it's just like a giant panel that has all these antennae that phase in and out of each other. But what's important about that is that by phasing and creating these radiation patterns, you're actually able to look in multiple directions nearly simultaneously. So you can see over on the bottom left, there's a picture of like the antenna. If you zoom in on one of these instruments, in the middle, you can see the field of view of the 3A misers that we have at high latitudes. And over on the right, you can see an example of like beam patterns. So you'll like that picture that's from Forsyth and Markovich, 2018, it has all these different like look directions associated with it. So inquiry and scatter radars, yeah, they're very powerful and they're able to look at like a whole bunch of different ranges and times and stuff like that. One thing that like satellites have an advantage over ISRs in general is that they're able to move around and look in different places, but ISRs, unlike a satellite, are able to look at like multiple ranges and get profiles. And like really start to dissect like the mechanisms that are occurring around specific events. So if you go to the next slide. For some reason it cut off one of my little things, but anyways, so yeah, one of the things I've been looking at is ISR observations of Steve, more specifically the March 26, 2008 event, where here we have like a Steve event. Actually, Gareth, do you mind playing it? If it'll play. Oh
no. No, this is the PowerPoint. It's not the Google slides, so we'll have to maybe share the Google link.
Yeah, well, everyone can just trust me that there is in fact a Steve that is going on here, and there's an A-miser beam pattern that's projected over top of what we can see there is all sky imager data. This is in white light and like a Steve event occurs. But what we can do is we can take a cut of the ISR parameters as well as the luminosity that we see and start to compare ISR to optical data, which is what I'm trying to show over on the left here. So these 3 panels, the top panel is plasma density between 200 and 250 kilometers overlay over top of that optical pattern that we see over top of that optical data along that blue line that we have in the ASI. The next panel down is the electron temperature, and the next panel down is just the luminosity in a different color scale so people can see. And what we can see is that like during this event, the plasma density is very structured. There's this huge plasma density wall that's occurring. And also we can see at like lower latitudes in that one sliver just below, like about just above like 65 degrees, there's this huge plasma density depletion that's occurring, which is consistent with stuff like Archer et al. And other like swarm observations of Steve. Additionally, looking at the plot below that, we see that the electron temperature has like a bump as well associated with that. And then my final slide, if you go to the next slide, is just showing the power of ISRs and looking at these events. So here we're looking at a Steve event, or rather the precursor, as well as like just a portion of Steve. If you play the movie later, you can see that. But basically, we can see in beam 1, beam 13, and beam 5, Steve as it evolves from its beginning to its end. The purple dashed line in all those beams indicate when we start to see Steve in our ASI data, in our white light imager data. And like things I want to point out, and I'll point out briefly because I only have like 3 minutes, is that you'll see from beam 1 and beam 5 that before the Steve event, there is in beam 1, there's a strong positive line of sight velocity, which is the third panel down in each of those. In beam 5, however, it's strong negative. These are both indicating a westward flow that's associated with the Steve event. Additionally, we can see in beam 13 that there's this huge plasma density cut that isn't as apparent in beam 1 or beam 5 or really any of the other beams, which indicates just how structured this is. Additionally, it's kind of hard to see in here, but there is an ion temperature spike, which is one of my personal investments in that because this relates to some work that I did with my master's thesis in looking at ion temperature spikes and plasma density depletions. We can see an ion temperature spike associated with that, which indicates a very strong and very quick, fast flow, and is most apparent in beam 13 that we have in here. But yeah, that's all the quick points I wanted to give about ISR and stuff like that. If someone from SuperDarn wants to take it away, go for it.
Gareth, I think you're muted, sorry.
Yeah, I was, sorry. Go ahead.
Can I share the screen with Google Slides, or is this the Google Slides?
You want to go share it? Sure.
Yeah, sure, thanks, sorry. So, hi everyone, my name is Bharat Kunduri. I'm research faculty at Virginia Tech. I'll talk about a different type of radars. These are called SuperDarn radars, and we measure coherent backscatter, unlike what Phil mentioned a talk ago. So SuperDarn stands for Super Dual Auroral Radar Network. We are an international network of high frequency space weather radars. And the principal backscatter targets in our case are plasma irregularities or density structures with decameter scale spatial lengths. And we are different from the other set of radars that Phil has mentioned. We operate in the high frequency range between 9 and 18 megahertz typically. We transmit much less power, it's about 10 kilowatts. And we have a phased array steering that looks into 16 or more beam directions and has a typical spatial resolution of about 45 kilometers. And we complete an entire scan in about 1 to 2 minutes. And the main advantage of SuperDarn network is that it's a group of radars or a network of radars, and we produce identical data products that are routinely combined to produce hemispherical space weather maps of ionospheric plasma motion. I'll talk about them a little more over the next few slides. So this basically shows the fields of view of different SuperDarn radars. Actually, there's about 30 or so operating at any given time over the last few years. The left panel is corresponding to the northern hemisphere, and the right panel shows radars in the southern hemisphere. Originally, the set of radars constructed were constrained to the high latitude region, which is about 60 degrees or so. And then at around 2010, in the last 10 to 15 years, we expanded down to the mid latitude region, making us ideally located for making observations of the subarauroral dynamics, and also expanded into the polar cap. So the biggest thing about SuperDarn is we are a collaboration. It was founded in the early 1990s, and the first radar was constructed back in 1983. I think the first collaboration was between the US and UK. And there are several research groups which now operate about 30 radars, and funding for these radars is provided by several different national agencies. And owing to the low cost of operations, the radars function around the clock 24/7. And the operation of all these radars are coordinated to maximize scientific potential, and we share data, software, and expertise between different groups. And the US collaboration is funded by the National Science Foundation, and it's comprised of Virginia Tech, Dartmouth College, Johns Hopkins, and Penn State. So this shows an example of the radar side. This is taken from Fort Hays in Kansas. There are two radars here. One is pointing in the northeast direction and one in the northwest direction. You can see two sets of radars here. This is the main array, and this is the interferometer array. So HF radar operates in a slightly different manner compared to other radars. This is because of the density gradients in the ionosphere. Several people have mentioned that the ionosphere has electrons and free electrons and ions. So in this frequency range, the main feature is that the rays bend or refract, and as a result, in some under certain suitable conditions, they become perpendicular to the irregularities or density structures that are aligned across along the magnetic field lines. And as a result, we get backscatter or reflections from these irregularities, and we can measure motion of these irregularities. However, there is another mode of operation where the radar rays can bend when the ionosphere is very dense, and it bends to the extent that we get reflections off of the ground. And this is basically a measurement of the ground scatter. And we can make certain other we can infer certain other useful parameters about the ionosphere using the ground scatter too. But this is called the one-hop mode, and usually the backscatter we get from the plasma irregularities in the ionosphere comes from the half-hop mode or 1.5-hop mode. In the 1.5-hop mode, the ground scatter reflections further move forward and get reflected from the ionosphere way in front of them. So I'll quickly move on to the data products. So we have 3 primary data products, at least considering the line of, when you consider the line of sight velocities. These are power, Doppler velocity, and spectral width. And for the sake of the analysis of SAPs or other features, most of the people are interested in Doppler velocity or Doppler line of sight velocities. This shows an example of all these 3 different parameters, and you can see the half-hop ionospheric scatter here, which is ranging into a few hundreds of meters per second. And ground scatter, as you can expect, is much lower in velocities. And there is another 1.5-hop scatter mode that's occurring beyond the one-hop ground scatter mode. Basically, you have range in the vertical axis and time in the horizontal axis here for this plot. And this is a single beam analysis. So this shows a full scan of the radar. This is about 1 minute, and it shows the 3 different modes that I just mentioned. In the half-hop mode, you can see higher velocities coming from the ionospheric backscatter. There are significantly higher velocities coming from the 1.5-hop ionospheric scatter mode, and there is ground scatter where the velocities are really low. We are making measurements of line of sight velocities. So blue here corresponds to velocities towards the radar, and red or yellow correspond to velocities away from the radar. These are indicated by negative velocities. Usually when analyzing events like SAPs, you assume that the direction of the background flow remains constant across a certain local time region, and you can combine line of sight velocities from all these different beams to estimate the 2-dimensional velocity vector. So, but that was just an example from a single radar. Here I'm showing what we usually put out as a data product. This is basically combining data from all the different radars that were available at a different given point in time. These are again line of sight velocity vectors, and they're median filtered, and these only correspond to ionospheric plasma reflections from the ionospheric plasma irregularities. This is again a 2-minute scan from all the different radars that are combined, and a spherical harmonic fitting is applied to determine the direction and flow of magnitude of the flow of these vectors. And using the data product, you can then get an estimate of large-scale convection in the high latitude and the subarauroral region. So now, as I mentioned before, we don't just operate in the northern hemisphere, we also operate in the southern hemisphere. So we can make 2 maps like this, and this can give you a really good opportunity to make or study both the hemispheres simultaneously. And it's especially useful in interhemispheric conjugacy related studies. So I'll quickly talk about mid-latitude superdown radars because that's the focus of this workshop. So the main motivation initially for the mid-latitude superdown radars was that during disturbed conditions or storm time conditions, the auroral oval expands much equatoward of the 60 degrees chain, and we wanted to make measurements of auroral dynamics or plasma convection in the auroral region, in addition to several other interesting features that happen in the region. So that's why the first mid-latitude radar was constructed in Wallops Island in Virginia, and later it's it was expanded to cover the entire continental United States. Right now, there are about 6 radars operating, 2 in Virginia, 2 in Fort Hays, and 2 more radars in Christmas Valley in Oregon. Those are operated by Dartmouth College. So this was one of the first SuperDARN papers. In fact, this is the first SuperDARN paper that spoke about SAPS. So this was published by Shelmar Oksavik back in 2006 using data from Wallops radar. So the plot on the left shows 3 different things. One is ultraviolet imager from timed GUVI satellite, and this shows that this shows the location of the auroral oval. The outline here shows the field of view of the Wallops radar, and the blue vectors, or the blue background, shows the velocities measured by the Wallops SuperDARN radar. And the velocity vectors in this here correspond to DMSP F15 satellite, and they are in good agreement with what SuperDARN measures. Basically, what this plot shows is that there are a significant amount of flows equatorward of the auroral oval, and these correspond to the subauroral polarization stream. And another important feature that this paper discussed about is the high velocity narrow latitudinal width stream embedded inside a broader channel of low velocity SAPS-like flows. Sorry, the high velocity stream is usually referred to as SAIDs that Bill talked about, and the broader low velocity, slightly lower velocity, latitudinally wider stream is usually called subauroral polarization stream, SAPS. So we conducted a study of SAPS and classified it under different geomagnetic conditions, starting from really disturbed stormy type conditions to really quiet time conditions. And what we realized using SuperDARN data was that SAPS are not just observed during disturbed geomagnetic conditions, and they could also be observed when things are relatively quiet. But the probability of seeing SAPS during really disturbed conditions is much higher compared to the probability of seeing SAPS during quiet conditions. So to summarize, the first generation of these radars were constructed at the auroral latitudes, but we now expanded to the mid-latitude region, and we make extensive observations of features like SAPS and SAIDs. And in addition to that, we also make other interesting measurements at the mid-latitudes. A key factor of SuperDARN radars is that we operate 24/7 mostly, and we cover a wide set of magnetic local time and latitudinal regions. So we provide a slightly different set of measurements compared to the other radars. So with that, I will stop and let Gareth continue. Please let me know if you have any questions. Or
actually, Brad, I'll let you keep driving. May as well keep
okay.
the fun going. Yep, thanks, Brad. Should we do questions now, or do we want to keep going?
We can just keep going, and maybe we can do questions after the talk.
Yeah, okay. So hi, everybody. My name is Gareth Perry from NGIT. My name's up there, but this is some work, some product of some collaborations I've had with some of the people here at the conference, Bea, Simon Shepard, Ashton Reimer, who's not here, I don't think right now, but Megan Gillies as well, and Bill Archer. So it's not just me, but more towards the Steve and SuperDARN related observations. Obviously, as Bharat has shown, SuperDARN is, especially the mid-latitude radars, are well situated to study the subauroral zone. And indeed, as he showed, as Bharat showed on that Shelmar Oksavik 06 paper, I think it's the Wallops Island radar shows some really nice flows, and SuperDARN has measured these narrow and fast plasma flows in that region for essentially as long as the radars have been operating in the region. So on the far right, kind of in the blue box, is another figure from that Shelmar Oksavik showing on the bottom panel there at 528 UT, that kind of cutout of SuperDARN Wallops Island field of view with the Doppler flow showing showing a SAPS flow, but embedded within it even smaller, faster flow. So, you know, SuperDARN has likely been observing fast flows related to Steve for some time. Unfortunately, we don't have that very many observations of Steve optically and SuperDARN flows at the same time. There is one that has been published, Toshi Nishimura, that's the center figure here, shows very nice observation of the optical data from Themis on the third panel there, showing Steve showing up And at the same time, we have some Super Darn radar Doppler measurements from the I think that's King Salmon radar, showing a nice, very narrow, fast flow in there. As it turns out, it tends to be very difficult to study Steve with Super Darn because we need that optical verification that we're in fact seeing Steve to kind of do it. So the objective is to kind of go back and look through some of the Super Darn data to see if we can see some signatures of what we think is Steve. So occasionally we get those events that line up with radar data and optical data. So if you go to the next slide, Bharat.
Yeah.
These are two dates that were given to me by Bea a few years ago. So again, my long-suffering collaborators have been waiting patiently for me to kind of move this along. But what is the summary of is two Steve events that were easily observed with an all-sky imager at Lucky Lake in Saskatchewan. And before I go further, I always need to give a shout out to Lucky Lake. My wife was born in a suburb of Lucky Lake, Saskatchewan, called Bursay. And for those from the prairies, that's a joke because Lucky Lake has a population of about 200 and Bursay is about 50. Anyways, I'll keep going. So we see in the 4 panels, what's plotted, you see Steve show up in both. But Super Darn was operating at the same time, same frequencies, and they had different characteristics. On the left, the top panel you see is all sky imager data. We have the vertical axis is magnetic latitude, and we have UT along the horizontal. And then the second, third, fourth, and fifth panels are all the scatter overlaid from Fort Hayes West, Saskatoon Super Darn radars, Christmas Valley East, and Christmas Valley West. So Fort Hayes, Christmas Valley, those are mid-latitude, and Saskatoon is an auroral radar. And as you can see, when Steve shows up, as indicated by these yellow arrows, on this left panel, all the echoes concentrate on the mid-latitude radars. They focus on Steve and they stick with Steve. And in fact, they're essentially the only echoes in town. Everything just kind of collapses to Steve except for some of the closer range echoes. However, on the second date, which is July 29, 2016, Steve is it's faint, but it's there. And you can see kind of indicated by the yellow arrows. The radar echoes do something different. They essentially disappear. They stop showing up. And we checked, everything's transmitting at the same. It's not like an instrumental effect. So this makes it difficult to study Steve with Super Darn because on one hand, we get echoes with one Steve. On the other hand, we don't get echoes. Okay, let's just Jill chiming in. So really the study that we've been working on is to try and distinguish, to kind of even get our foot in the door. Why is Super Darn acting different from these two distinct events? So one tack we took, if you go to the next slide, Bharat, is to just kind of go ahead and model the HF. These are the rays coming from the radars, and model how they propagate through the ionosphere up to where we think Steve is happening, and to see if how they their characteristics with respect to radar backscatter. So to get echoes with Super Darn, you need two conditions. You need irregularities to exist in the plasma, and then you need the rays that you're probing with to be about right angles to the magnetic field line. And so if you don't get one of those, you don't get scatter. And what we're suspecting is the first one with the propagation conditions is not being satisfied. So we took some swarm data that was prepped for us by Bill Archer, and we modeled an ionosphere with that structuring that was given to us by the swarm data. And we ran some simulations for tracing those radio waves. And sure enough, shown here on the bottom left, where these red diamonds are is where we expect to see echoes if we assume irregularities are there. And on the right is when we have our Steve event. And you can see we don't have as many essentially red diamonds at the area where Steve is telling us that perhaps our propagation conditions are not satisfactory to receive the scatter. That's one conclusion. The other side of the coin is we have to go, and we're still investigating whether or not the physics has changed to inhibit irregularity production, that other side of that coin for that backscatter. Because Steve is such an extreme event that the conditions for irregularity production may have changed. And so I'm actively with my co-authors and collaborators kind of trying to figure out whether or not that is contributing to this lack of echoes. So I think that's really what we wanted to say in terms of Super Darn, in terms of kind of like a science highlight for Super Darn, and that studying Steve, it's a very dynamic event, but studying with the mid-latitude radars, especially SuperDARN and HF, it's very well located, and they're very well located. We just got to figure out, first off, and we're still trying to figure out what we're in fact looking at. And the hope is that if we can characterize it in SuperDARN radar data, then perhaps we can backtrack through decades of SuperDARN radar data, as Bharat has said, has been operating since the mid-90s, or even a little bit younger than that, to try and study the magnetospheric signatures as well. And I think that's all I have to say about that.
This is great. Thank you, guys. Are there any questions for Lindsay, Bharat, or Gareth?
Can I ask a question to Gareth?
Yes,
this is Toshi. Gareth, if you can put the slide back for the September 27 events. I guess that was the second from the last slide. So I had some discussion with Carlos about this event, so he may have the same question. But so this event is not unusually long. Like the emission is there for like 3 hours. It looks a little thicker than the usual. This bear studied typical steep thickness like 20 kilometers, but this looks like 100 kilometers or so. I'm wondering whether this is absolutely steep, or this could be a SAR instead. Is there a way to know whether this is not certainly steep emission?
I believe yes, that's a good point. I know Carlos has been brought that notion up, the fact that sometimes we're seeing steep and sometimes we're seeing a SAR, maybe perhaps even seeing a SAR arc. So whether or not, I don't think we have any swarm measurements for the September event like we do for the July event. So that would certainly help us make that determination. Otherwise, I would it looks like a steep from that perspective. I would probably consult with Carlos actually and you whether or not they think it's a SAR arc or not.
In fact, later I will show some data related to this event that includes satellite data, so we can continue the discussion there.
Okay, that sounds good. Another, yeah, go ahead.
I was going to say this is still something that Carlos and I have debating for a long time. I say, of course, this is, yes, that's a good question. This is Steve, and Carlos says it's a SAR arc. But Carlos, can you tell us something? Can you see it in the Milson Hill camera?
Yes, and in fact, the characteristics are different. So another hypothesis, it might be that in that longitude sector, Lucky Lake, it could be a steep, but what is happening in Milson Hill is a different structure, even though they share the same L-shell value. So
Bill Archer is asking a good question. If we have citizen scientists photographs for this event, and that would be something that I would like to bounce to the citizen scientists. Can you guys show us if you have Steve observations for the 2017 September 27?
You don't have to do it like instantly here, but if you could like sort of sort through and maybe at some point talk about it, that would be great. Carlos, you just used a piece of jargon that we got to L shell. We should probably define that, right?
Yeah.
I mean, there's this guy Carl McElwain in the early 60s came up with how do we label magnetic field lines, because everything is so well organized along them. And what he did was, if it's a field line that's closed, it starts in one hemisphere, goes across the equator and goes to the other hemisphere. We follow the field line until it gets to the equator, and then we figure out how far out it is. And we measure it in terms of Earth radii, where an L of 1 would be a field line that was literally going right along the ground. So if Carlos says that thing was at an L of 3, that means that it went out and it touched, when it got to the equator, it was at 3 minus 1 or 2 Earth radii, or about like 12,000 kilometers. It's really just a labeling that we make, but it makes the assumption that the field is a dipole, which sometimes isn't a great assumption in places during storms. But anyways, I just heard that and I thought we should define that.
Yeah, thanks.
I just added it to the glossary. Any more questions for any of the three speakers? I know there was a question in Slido for Lindsay.
I think most of this got answered. Yeah.
Yeah, as long as the answer makes sense there. Yeah.
I have just a quick question, and we could discuss this later, but so I've been looking at SuperDAM data, but not in a way that details, but the way that suggested, but I'm just like the ray tracing study that has shown now suggests that echoes may not be there when Steve is occurring. But then I think if we could track that SAID or a fast flow movement, global movement, isn't that really helpful for this study? Or I just, we could talk about this later, but like, I guess I just want to know that how we can best use for global sort of study, how we could best use SuperDAM data. So it's sort of, it's not the question, I guess it's probably we should think about maybe tomorrow when I'll appreciate if you could give feedback to the study like we are doing using assimilated mapping, because you know, we could go to each beams like you guys doing, but on the other hand, I want to get that global pictures. I think that's how we can contribute. So anyhow, so that's something that on my mind. So you could help us how best to use SuperDAM data or how to support this campaign.
Okay, that sounds good.
Mm-hmm.
Actually, I'm really surprised that you can see any effect of SAID, on SuperDAM, because it's really very difficult. You have a very deep and very narrow, relatively narrow trough, okay, surrounded by, normal dense plasma. So the trajectories, the radar, the echoes are very difficult. The aspect angle is not easy to calculate, etc., etc. And of course, irregularities in such trough, given the strong electric fields, etc., they are basically should be always there. The gradient drift and thermal gradient drift instabilities. So they produce the necessary irregularities. So the question is, I think, just observing observational conditions. And it should be, I think, carefully calculated.
Yeah, it's a good point. One of the things that I wonder is as you say, like the conditions for regularity should be there. So if we, how is it that is the trough that is presented with, Bill Archer's shown those excellent swarm plasma density measurements that show these really obscene plasma density gradients, and really it's what does that HF ray, what does the aspect angle condition look like after it hits one of those gradients, and perhaps are we not modeling it sufficiently enough? Is the model that we're using not really contributing to that? So perhaps it doesn't have the sufficient refraction for the first 95% of the path up to the ionosphere, but in those last 5%, that's where the refraction happens because it's such a steep gradient. That's one of the questions that I have about that.
Yeah, that's basically the fundamental question for such kind of observation. And of course, you have during time, the channel is basically azimuthal, along longitude, right, and narrow latitude. So you can, arrange that, and it changed this time because basically it's the source is already over. The plasmasphere, and the SAD supports itself due to feedback. Ionospheric feedback, because density due to chemistry, right? chemistry induced trough, and it changes with time because the temperature recedes, etc., etc. So it's not that easy to follow from the beginning.
Yeah, Evgeny has a great point in that you can sometimes get these instabilities started and they're going to kind of run on their own internal engine for a while, right? Supported by the conditions that are around them. And so they couldn't have different lifetimes. You know, it's kind of like you shut off the initial seed and you know, you can have things full flywheel for a while. So that's another thing we don't really understand.
Basically, this time you should expect kind of upflowing of the region where this irregularities are most intense.
Right.
So that
And
you know.
And you'll also notice that the one DMSP plot that I showed when I was just trying to give an example of DMSP, there was a very strong upward flow pretty close to that area too. So, you know, that would make some physical sense.
Yeah, that's typical for.
Yep.
There is one more question by Brian Harding that I think Megan could easily answer while she's transitioning to her slides.
Yeah, Brian, so you were asking whether or not Rigo has any background channels, and no, it doesn't. So it's just a single filtered imager with a coating on the lens that has a approximately 3 nanometer bandpass that lets certain amount of emissions through. So there's no background channel subtracted. So it does pick up everything it sees in the field of view. How we tend to subtract off the background is we just sort of, we would take a dark count from the corners and subtract off that as like a dark current subtraction. If you wanted to subtract off other things, you would have to take images over the course of an hour, find averages off of what you're looking for, and apply that sort of technique to it. So yeah. Does that help?
Yeah, yeah, thanks. I mean, I was just wondering if there was any other, Themis or any green line cameras might be able to determine whether it's just the red line, like you'd expect for star arc or frictional heating, or whether there really is the steep mechanism going on.
Yeah, so actually with the Themis, there's a new paper out by Christine Gabriels, which actually takes MSP data and Themis and actually does an incredible job of backing out energies and intensities and applying it to data. So I strongly encourage you to look it up. I can find the reference for it and send it to you. It's an amazing paper. I don't believe we have any green line cameras at the moment, but we do have the RGB, which I can discuss now and then see if that answers any of your questions.
Thanks.
Would that help?
Yeah, great.
Okay. Bea, would you mind if I shared my screen?
Sure. Do you need the permission?
Oh, maybe. Hang on. Oh, no, apparently I do not. Okay. So, all right. Can everyone see my screen? I have 2 beautiful images up right now.
Yes.
Yes.
Awesome. So on the left, I have one of our Aurora Max images. This is what I would consider more traditional photography, which is similar to the beautiful images we get from all the citizen scientists. And traditionally, this is what people would have used to study the aurora. It gives you a very qualitative estimations of auroral things. Like you can study morphologies, you can study colors, you can study motion. But what we tend to use at the U of C is what we call all sky imagers. And I just wanted to show what the difference between traditional photography and what we can get from the all sky imagers. Now on the right is an all sky imager. It's a wide angle view where you basically look straight up. And this gives you the advantage of horizon to horizon coverage of the night sky. With these type of optical instruments, we get to be able to have a more quantitative study of what we're looking at. We can actually see things like we map these images into a geographic reference frame, so we can measure things like speeds, locations, widths. We can get from some of our cameras, we can get intensities of the emissions, and we can model this in time. I just wanted to know, we've seen a lot of these kilograms that people have been showing, and I just wanted to make a quick sort of discussion on what a kilogram was for people who weren't entirely sure. This particular image here is aligned north to south. And what a kilogram does, it takes just one single slice through the middle of one of these frames, and then it stacks it in time. And that sort of gives people sort of an overall summary of what's happening in the aurora or whatever phenomenon you are looking at during a time period. And it's a great estimator. So Bea was kind enough to ask me to talk about some of the instruments that we use to look at optical phenomena such as the aurora and Steve that we have here at the U of C. And yeah, so I'm going to talk about all the optical instruments that we have running and some of our legacy work. And what's really cool at the end is I'd like to just spend a couple minutes talking about something called Aurora X, which is an amazing platform that lets us actually quickly see what data we have and gives us brief sort of analysis tools, but I'll get there later. Upper top right corner here, I'm not sure if you can see my mouse, but this is one of the original Themis all sky imagers. So just a little camera in a little dome, taking images of the sky and making north. Now, for all sky images that are operating out of the U of Calgary at this time, we have the Themis, which is a panchromatic white light imager. We have the Red Line Emission Geospace Observatory one. So this is a similar all sky imager camera, so that full field of view, and it is filtered specifically to 630 nanometers. We have the RGB cameras, which are a true color 3-channel imager. The NIR, so the near infrared, which is filtered specifically to 844.6 nanometers, and our blue lines, which are measuring the blue line generally optical emissions at 424. We also operate some Meridian style imagers. So instead of having a 2-dimensional view of the night sky, we just have a narrow slit. We run in conjunction with Martin Conrad run one of the FISOs out to Athabasca, and that's a scanning one, I believe. No, it's a yeah. And then we have one of our spectrographs, which again just takes a narrow slit at the north-south sky and creates a spectrographic image of whatever we're looking at. We have a variety of data analysis platforms available, and this is where Aurora X comes in and Swarm Aurora, which is part of Aurora X, I believe. Oops, I've done that twice, sorry. We have discovery platforms, so this is where IDEAL libraries come in, Python, they're working on API. And then we have our legacy systems. So there's a couple of systems that have aged out over time. The contracts are done, the projects are finished. And those some of the original ASI from the Canopus array, POCA, we had the rainbow imagers, which were the original predecessors sort of to the RGBs, NorthStar, Dense Array, and then we have the MSP system, which is now no longer running. So what's the Themis imagers? So I showed that little tiny wonderful camera in the little dome up there. So we currently have 21 imagers located across the entire Canadian North and some of Alaska. It does produce a panchromatic color, so basically a grayscale version of whatever is seen in the sky. Traditionally, you haven't been able to calibrate it for any sort of quantitative data with respect to energies. However, Christine is incredible and she is pioneering some stuff with people doing that. It's a wide field of view, so you enable basically that horizon to horizon coverage. It's a network, so you'll be able to stitch them all together. I'll show you a video in a second. The resolution is just a 256 by 256 pixel, and it operates at a 3-second cadence. So it has a 1-second exposure, and then it iterates every 3 seconds. It's been operational since about 2005 through now. It's nearly continuous. It does shut off in the summer months when there's not enough nighttime to do this. During operation, the cameras do image from dusk to dawn. And we have raw images available. We have sky maps at various altitudes so that you can take your raw images and convert them into a geospatial reference frame for quantitative analysis. We provide summary keyograms, you can make them on your own, and we also have real-time mosaics. The mosaics I have right here, I have one of these videos running from 2008, it's February, just sort of gives you the idea of the immense scale that the Themis array covers and just what you can get from these imagers. Beautiful arcs. You'll see onsets here. Steve was hanging out at the bottom. You kind of see him sneaking through. Not in this one. I don't think he's here, but it's here. And some pulsations, and it is quite impressive because it gives you an incredible overall view of something where normally we would just have isolated information, which doesn't give you the full picture. And this sort of helps promote stories along and gives us more of an idea of what's going on. So as Brian was asking, the Regos are one of the next generations of the Themis imagers. Now these ones, there's 9 imagers and they're located all across Canada. They are specifically red line monochromatic imagers, and they actually have a narrow band 630 nanometer filter. So they are a little bit higher spatial resolution than the Themis. They are 512 by 512 pixel CCD. And they have a longer exposure length due to the red line emissions. So they actually have a 2-second exposure, and then they're still integrated every 3 seconds so that it fits in with the real-time imaging of Themis array. They have been operational from November 2014 to the present, and they are capable of being calibrated. This is one of the neat things about the Regos, is that we can actually obtain a Rayleigh estimate of the luminosities of the objects that we're looking at. They had generally a flat field, a dark count, a dark frame subtracted, and then you apply BandRIN, and then you can get images that you can use quantitatively for science. This top right corner here is one of these images that has been calibrated into Rayleighs. And we can see this is a keyogram where we've got geodetic latitude and we have time. And then we have beautiful stunning aurora as a function of Rayleigh. Right now, the data we have available is we have our raw images, we have sky maps of various latitudes so that you can convert these into a reference frame. And then if you wanted to further do it into geomagnetic, you could, of course, apply an AAC gem correction or to map it into different, whichever frame you want. And then we have the summary diagrams. In the bottom right-hand corner, you can see that they have a slightly, this is a field of view. So one of those Themis imagers would give you a field of view that would cover this sort of area. There's all of Canada here, we have Alaska over here. And the Regos, because of their higher altitude, cover quite a large range, and that enables quite a lot of coverage from fewer instruments. So T-REX is one of the newer initiatives at the University of Calgary, and it actually focuses on that transition region that Bill was talking about earlier, where that's the long dipole stretching of the tail kind of stretches back into the near-Earth environment. And this project was geared specifically to kind of answer some questions on that. And this red outline here actually is where all the Rego field of views are. So this is those red lines. And then in here we have the blue line and the near infrared that I'll quickly talk about now. So these imagers here are part of the T-REX imaging sort of suite, I guess. We have over here, we have our blue line imagers, so that 427.8. We have the near infrared, the 844.6. Beautiful RGB cameras. So this is those true color cameras. And then we have the Rego, which I've just labeled red, but this is one of the Rego images. They have various resolutions and they have various special things attached to them. So here is one night of data at 4 different wavelengths. Well, 3 different wavelengths and then a true color mapping. So here we have that blue line. So this is one of those keyograms and it expands probably about, I'm not sure the time frame, but a couple hours of data here. We have the blue line here, NIR here, then we have the true color imager here, and the red line. So this keyogram again is made up if you take one of these slices and then you stack them in time. So these images were taken along this particular site. You can see the beautiful arc going through here, and you can see it through Ortega. And this gives an incredible suggestion of how we can actually use this data to actually see what's happening in multiple wavelengths all at the same time. So the blue line and the NIR cameras, they operate similar to the other ones, except they're a little bit different. So the blue line cameras, there's 6 cameras to be deployed at key sites within that transition region within Canada. They are specifically filtered, again, similar to the red line. They don't actually have any other background filters applied to them. They're calibrated. They operate at a cadence of a 2.99 second exposure, and that last little remaining time is a rig over to match to fit in with the Themis and the Rego imaging. One of the really neat things about the blue line is it is capable of something called burst mode. So if you need a high temporal resolution of something, we can actually increase the frame rate so that you're up to 10 hertz imaging during one of these campaign modes, which will actually give you high spatial and temporal resolution. They are currently deployed in Gillam and Rabbit Lake. They will be deployed in Pinawa, Athabasca, Lucky Lake, and Fort Smith, I apologize, really soon by the end of the year. Unfortunately, with the environment, travel has been restricted a little bit in the last couple of years, so deployment had to wait, but we are getting back into it. The NIR cameras are, there's 6 cameras again. They are being deployed at similar sites to the Regos and the blue line. And they are filtered specifically for that near infrared emission. Similar to the other ones, one single filter sees everything above. They currently operate at a 5-second exposure with a 6-second cadence, again, to fit into the other sort of things. And they are currently deployed in Gillam and Rabbit Lake Two others have shipped out to their new homes, and then the other two will be done again for the end of hopefully 2021. Data is available for some of these. RGBs, I love the RGBs. These are fantastic. So the RGBs are these, again, it's an all sky imager. It's a highly sensitive full color imager. It's designed to capture the true color images of aurora and airglow. There are six images are going to be available again in these key sites, and they have a 3-second exposure with a 3-second duty cycle. So that means the entirety is spent on imaging. There's not a lot of downtime between the images. They are high spatial resolution. They are 558 by 480 pixel, and they are true color. So they contain the 3 channels, red, green, blue. Now, these images, again, can be sky mapped backwards into a geographic reference frame, which allows us to get all sorts of lovely information. And they can be separated into 3 separate channels to isolate green, isolate blue, and isolate red. And they have been in operation since about 2019. On the left here is one of the studies we did with Steve, because I figured this was a good place to show this one. In the top left panel, we have, as a function of magnetic latitude and longitude on the x-axis, the pickets from Steve. You can see them for those lovely green striations. And that's the true color imager. And on the right, we've got out, top right, we've separated out the red channel. Bottom left, we've separated out the green channel. And the bottom right, we've separated out the blue channel. And as you can, well, hoping you can see from this, that it's really helpful to be able to pick out different features based upon different channels. To see what something like Steve would look like in these, oh, okay. This is actually that similar mosaic from before, except now with the RGB cameras. This is actually from February 19th, 2020. It's about an hour's worth of data. And it's incredible to see these. I'm not sure if you guys can actually see this, but there's something peeking out on this date. Someone may or may not be making an appearance. I have not delved into this, but I thought that was kind of interesting how the most beautiful day that I found to make a mosaic with this happens to have something hanging out where Steve likes to be. So this would be interesting. And I just to show just how wonderful this optical system is, it's lovely. So,
Megan?
Oh yeah, sorry.
There is a Steve event happening that day, actually. It's in the data, in the other data. Yeah. So yeah.
And isn't it lovely? It was just happenstance I made this, and then I was making it for something different just because it was the only non-cloud event. And then I kind of looked, I'm like, what's happening in Pinwell? I was like, there he is. Oh, it's just lovely. So anyway, so you can see how wonderful this sort of time resolution and the true color can be. It produces some incredible images. That event I showed earlier. So this is actually Steve and the picket fence. So here we have actually some of the picket fence behavior, and then we have kind of Steve showing up a little bit later. This one was from 2019 too. This was August 31st, 67 UT, and both Steve and the picket fence were seen in the RGB camera, at the same time. I hope you guys can see that. I'll just quickly move on. So this is where having something with a 3-channel true color imagers is really helpful to look at Steve, because we can break these apart into the channels. And that's what we did in one of our studies. So this is actually, we focused purely on the picket fence. We actually pulled out just the green channel only, and it allowed us to basically track the motion of Steve and get some really interesting quantitative parameters out of it. Like for this, it showed the periodic column emissions, but also let us see the percentages in our particular camera, how green it actually was from this versus how it did in the other channels. We were able to figure out how fast they were going, and we were able to see some interesting features. And then we did the same thing for the Steve structure that we saw. And in order to kind of eliminate anything from the green pickets, we would just pick out the blue and the red channels, and we did some analysis on them. And we were able to study just motion along Steve with respect to the colors associated not with the picket fence. And we're able to get some interesting results from that. At the UC, we also have some meridian style images. So these are no longer these all sky horizon to horizons. What they are is they are just sort of like a narrow slit version of a north to south swath of the sky. We have the MSPs and the T-Rex spectrograph for this. And these are some pretty images. So now it's a legacy program or project because they are no longer operational. The contract is done. But the meridian scanning photometers are incredible, actually, system of imagers, and they are 4 cameras. They cover multiple latitudes, basically a vertical section straight through Canada and then off to the side. They have a 30-second cadence, so they're a little bit slower because they are sequentially scanning through different altitudes from north to south. They are calibrated, so they actually provide 4 wavelengths worth of information. So they are calibrated to the green line. So they are the H Vega, the blue line, or a different blue line than our blue lines are, but you can infer from one to the other. And then the red line. They've been operational since 1997. That's like over 20, I guess it's over 20 years Vega now. And that's like almost like it's a solar cycle. It's amazing, right? And we have this data if anyone's interested in long-term studies. The resolution is a little bit hard to pick out Steve. However, if you have Steve in one of these co-located ASIs, you can always hop over to the MSP if there is one and do a comparison study. Once you know what you're looking for, it's a little easier to see in the lower resolution. TRX spectrograph. This is one of my favorite instruments currently here. I love this instrument. Okay, so this is a high sensitive imaging spectrograph, and it's designed to capture emissions between 400 and 800 nanometers. It has a spectral scale of, or particularly the Lucky Lake one has a spectral scale of about 0.4 nanometers per pixel and a spatial scale of 1 degree of elevation per pixel along that north to south slit. So the spectral and spatial resolutions, they do vary along the imaging field. It operates at a 15-second cadence with a 13-second exposure time, and the rest of that time is used to download data and sync in with the Themis and the Rigos and all that. It's oriented along the spectrograph is oriented to the slit samples along the geographic meridian. This is a summary plot that we have made to basically mimic the MSP behavior. So we pulled out the H Vega, which is at gray, we pulled out blue, we pulled out green, and then we pulled out red. So again, the typical auroral emissions of 577 or 5577 and such. What I like about this is it enables some certain analysis that we don't normally do. We tend to filter the cameras and such to the typical auroral emission wavelengths. So this is that day. And what we're going to do is we're just going to take this full time period and we're just going to take a look at it in the real data where we haven't binned it by certain wavelength passes. So this is actually I just overlaid a whole bunch of elevations. And this is just a typical auroral structure. And we have variety of what we would consider typical lineal bands up here. We have the green, we have that lovely doublet at red. So this is 630, this should be 33 or something. And then we have the blue H Vega, alpha. And this gives us so much more information than we would typically get. And using them in conjunction with something like an all-sky imager, once you've identified the location and space of what you're looking for, kind of hop over to something like the spectrograph and actually get way more information at multiple wavelengths. To get the image on before, we would take this and we apply like a filter that would be similar to what Rigo would do and integrate over that wavelength and then produce our images. Now for something like Steve, this is actually really neat and handy where this is the same picture that Bill was nice enough to show earlier. And this actually gave us a lot of information that we totally would have missed, I think, if we didn't have something like a spectrograph like this. And this is that image that he talked about where we have an image to Steve. And normally when we would apply a background, we take data off the shoulders and we would subtract it appropriately from the image. We couldn't do that with Steve because Steve has this continuum emission. It's why it didn't seem to show up in the proton aurora, is because when you have a value and you've taken an average off, it kind of goes to zero, but really it's sort of visible. It's just continuous across, so it goes away. Now, so this is that same plot where we have the blue is right in the middle of Steve, and then we do a different type of background where we've taken images above and below Steve or north and south of Steve to see what the background behavior is doing when you're not in the thing that you're looking at. And it showed this really kind of cool continuum, a slight enhancement of that blue line and some other stuff. And it was a really neat sort of result. We did the same thing for those pickets. And again, we have this lovely sort of bright green spike and very little else that doesn't seem to be background except for when you get up to the higher wavelengths. And this is one of the beautiful things about the spectrograph is that it gives you so much more information and lets us kind of take a look outside the normal range of where we are. This is also really cool. I'll zoom through this. So this is Aurora X. I guess a phenomenal way to look at data. Normally, I just on the next video have a little sort of demo clip where I just screenshot of myself looking through this. It would literally, it's 2 minutes long, but you would take like an hour just to even breach the surface of this machine. And it actually lets you do some of the stuff really quickly, like what satellites are in my region, what cameras are operational, what data can I have? And I'm just gonna flip over to the next screen to start. So we have things like the Swarm Aurora conjunction tool. And this nicely lets you kind of look up conjunctions with, right now it's more the Canadian images. So this is where we have lists of kiograms. You can do quick look summary plots. You can find conjunctions between satellites and data. And then any sort of data is like sort of available on the bottom. Let's see, I think I went over to the conjunction search, and this lets you put in the ground instrument you want, space instrument you want, and find conjunctions. So I randomly picked a day. I wanted specifically to look at the red line, and then I wanted swarm because I work with swarm sometimes. And then I said, hey, anything that's 5 kilometers in conjunction, look at North Trace footprint. Search comes up really quickly with a whole bunch of conjunctions, and then you can open them up in Swarm Aurora and see if there was actually data. This one was cloudy. What I kind of forgot when I was doing this, is that you can actually open up all of those events and go through them all really quickly. There's a virtual observatory. This is amazing. There's something called Kiograms, which actually takes Kiograms from the movies that get sent back from each of the sites, but it lets you work with them in your own sort of space. And the snipping tool is awesome. You can like cut the movies where you want. So if you want to do a presentation the night before and you're like, I need this feature, you would do this. You can like narrow down the movie. You can change the speed of the movie to enhance certain features and stuff like that. And then eventually, I think in the next iteration, you're going to be able to download the clip and put it into your presentation. And that's amazing as a quick look feature. And I think it's just going to change how I do presentations for sure. There is an incredible citizen science sort of area where we have the Aurora Zone, which lets citizen scientists sort of classify things. There's going to be a place where photographs are uploaded for use. We're just developing that right now. There's Satellite Finder. They got data information. Any of the instruments I used, all of their funders will be located on this site. And there is so much to play with. So I strongly encourage anyone who's interested to check out Aurora X. It's aurorax.space. And yeah, that's all I have for you guys. But it's awesome.
Thank you, Megan. This is fantastic. Are there questions from the participants? I have a bunch of them, but I'll let everyone go first.
This is Phil. I just have one question for Megan. Who funded that? That's an enormous amount of software work. I mean, I'm pretty staggered by how much must be in the back end there.
Yeah, it's a lot. But yeah, go to the site, let's see your funding. I'm not actively involved in that project, so I don't want to say the wrong thing. But yeah, it's incredible. I used to, when I look for conjunctions, I'd go to Swarm, I'd download their tracks, I'd go to here, I'd see where they crossed, I would upload the next thing, and then I'd have to go and see if there was any data, and then I have to go see if any data is good. This lets me do all that work like immediately. And I know, like, right when I clicked on that random data, it was like, Enrico sees clouds at Fort Smith. Okay, moving on. And you don't have to spend so much time to get to that point to find useful events. Like for some of these where it's like, is there EPOP data? We have, for some of the Canadian instruments, we have quick look summary plots of the EPOP data. You'll be able to see immediately if there was data available, if the satellite was turned on, and if the data is anything that you would like to use. And then you kind of have to go elsewhere and get stuff. But as a quick look tool and sort of a one-stop shop it's so handy.
Let me maybe make a comment. The comment, may I share the screen? I want to show some data. You know, it's with regards to your 3 sigma distance from Steve,
yeah,
poleward and equator. Let me show you maybe tomorrow. Basically, It's published. There is when you look at the data, I mean, Van Allen probes, in situ data, CRESS, whatever satellites you have in the plasma sphere during said events, at the beginning and to the end, with different time scales. So what you see the fine structure of the electron distribution, which creates aurora and creates, you know, suprathermal electrons, which precipitate also and create emissions in the ionosphere. You see that at the beginning, the region, the plasma pause is the critical. It's a separatrix between auroral and subaraural region, basically, all the time. So you can see on the auroral region, at the edge of the plasma sheet, you see very nice fine structure of the plasma sheet layer. And that creates a lot of plasma turbulence, actually, in the plasma sheet at the edge and inside the plasma sphere, where ions penetrate and create a source of plasma turbulence as well. So you see this, we call it plasma turbulence boundary layer, turbulent plasma sphere boundary layer. And this is just like you can separate them, whether it's auroral or subaraural. The turbulence is there, and the supraswarmal electrons are there. And also precipitation from the edge of the plasma sheet. So you have very sharp auroral region in terms of energetic electrons, like keV and higher. However, supraswarmal electrons are everywhere in this region. Then, you know, the substorm, say, stops. I mean, expansion phase stops, and recovery phase goes on. What you see some separation. However, the same volume is filled by supraswarmal electrons. So when you look at and the region, basically, spatial scale is about the same. You see the SAD, which is about, say, normally, say, 1,000 kilometers in the plasma sphere, L5, say. So that's 100 kilometers in the E region, in the ionosphere. And the same scale is at the edge of the plasma sheet. And also the same, this turbulence region is limited from the inward by the pressure of ions. So basically that creates SAD. And so it's very difficult to set. I believe that 3 sigma is too low, too small. So basically what you see as a background is actually enhanced emissions due to supraswarmal electrons from poleward and equator as well.
Interesting. So we chose 3.
If I can share the screen, I would show you the real data. You know, we basically
tomorrow
published a chapter recently.
Yeah.
Now it's in a review, in different reviews. But anyway, it's very robust feature. What I'm saying, it's not just one set of observations, but if you look at the events when satellites are in right place on the right time, you see the signatures very clear. So that maybe it's worth, you know, to expand your.
So yeah, this is the thing where we chose that 3 sigma because it was close enough to that feature to not be in other features or in a different area of the sky. It was nearly at the zenith. So when I mentioned earlier that the spatial scale gets larger and larger and larger, the closer you get to the horizon, this applies again to the spectrograph too. So 3 sigma could be quite a big distance depending on where you're looking. But yeah, again, this was our first approach with the big data. It was sort of the first thing we did with the spectrograph because we happened to have it working when Steve showed up. And it's definitely something to think about as we move forward, because it was a different way to take the background. Normally you would just take shoulders to subtract your background from these set wavelengths, but we couldn't do that with Steve and actually show what was Steve and what was actually just ambient. So it's definitely something, yeah, to work and look forward or move forward when we start doing more with the instrument. And I will definitely take a look at your work there, because it's yeah, this is important. This is a new instrument. You know, Don Hampton's had them running at Poker Flats for a while, and it's always good, right? So I would love to read that, and I guess see it tomorrow. Here, discussion, right?
Okay.
Thanks, Megan. There is a quick question by someone in Slido. What's the width of the 630 nanometer filter in Rego?
I beg your pardon?
Oh,
the
width
is 3 nanometers.
Yes.
Yeah. So
Okay.
it's actually there's a paper by Jin Liang that actually has the passband of the Rego filter. If you look up redline pulsation emissions, I believe you can see just in Google. Actually, if you Google redline pulsations, one of the first things that pops up on the images is actually the passband of the Rego filter. So it's just centered at 630 plus or minus about 1.5 nanometers on either side. So yeah, you can take the spectrograph and approximate what we are doing with the Regos as well. If you
Hey, this is Jun here.
Oh,
Just
hi, Jun.
hi Megan. Yeah, just have a kind of actually, yeah. But the first is that we do have kind of MSP to continuing with the Phasor. Phasor is kind of a new generation of the MSP, but it's focused on proton aurora. The Phasor is actually stands for 4861, which is the proton aurora bands. And besides that, we do have a background channel for Phasor. We don't have background channel for Rego, as you already mentioned, but we do have background channel for Phasor. The background channel is 480 nanometer. This background channel is designed there's no aurora, non-aurora that emission at that band. So this is a good band to check the continuum, the continuum spectrum. I use that for my sleep studies. They were published 2 years ago. And I just have a quick look at the data. We do have the Phasor data as a Lucky Lake for the September 27 events. So probably that could be useful to check out the continuous spectrum, the continuum. So yeah, just quickly mention that. And that's one. And the second thing is I just want to quickly echo the emissions, the comments here. Yes. So we repeatedly saw that the Steve is immersed in a very weak, but not none kind of the diffuse aurora the background. I think early in last year, there's a paper published and that using the Athabasca, the high sensitivity to the camera data. So yeah, so as I always to try to correct people, one thing I want to correct people is that we know that the Steve is not caused by the luminosity is not caused by electron precipitation, but that doesn't mean Steve is entirely without the precipitation. In my opinion, there's some kind of the very weak precipitation going on with Steve, and without that, probably it's difficult to understand some kind of the characteristic of Steve. So yeah, we have the observational evidence of that, but I'm not going to expand that in details. Yeah, thanks.
Thank you, Jun. I also added a link to Jun's paper for the Rego instrument in the chat. I do have a question, Megan. You were showing the RGB data. Is that RGB data the picket fence, the same picket fence that you were showing later, because you show the composite and then the different channels?
Yeah.
Is it my idea, or I saw the picket fence also in red?
So that has to do with the response of the camera. So with the RGB cameras, some of them actually will have a component of the red emission overlapping the 630 in the red channel, or the green, sorry, in the red channel. So that's not actually the pickets having red, it's the overlapping of the green band channel that extends into the 630. Yeah, so it's one of those things where it's like, it's not red. It just has to do with the
yeah,
camera that we are using.
Some of the red color may come from the N2-1PG emissions. We come from the N2-1PG. But we don't see blue. That's the key point there. We don't see blue emissions. Yeah. We see mostly green and some red, but we don't see blue.
I'm going to pull Carlos here because that's interesting regarding the event that we are analyzing with Ian. So we should definitely talk. Sorry about that. Any more questions? Thank you, Megan. We can go to the next talk then. So the next talk is by Carlos Martinez.
Oh, that's me. Okay. Let's see. Wrong one, this one. Can you see the slide?
Yes.
Yes.
Okay. So I will go quickly with some of the instruments that we have here at VIEW and some of the results described by me, and then some of the work done by Toshi and Josh. So just Megan gave a very nice introduction or description of imaging systems. So I will get a bit more onto the instrument itself. But basically, a typical configuration involves a front lens that could be an all-sky, a narrow lens. In the middle, an optical system that composes lenses and filters. And at the bottom, this comes from an old slide that I presented in which we include detectors. So from the beginning of the observations, when we had TV, then film, and now CCD CCD detectors. So this is a nice picture of a system we have now in equatorial regions with the filter wheel, the optical system, the fisheye lens, and then the CCD camera at the bottom. And this is a more recent instrument that we built here at VIEW, basically the same configuration. And to the left, the wavelengths that we typically use. Going from the red line, green line, 777 there's an oxygen line measure TEC, the sodium filter, infrared, and then background filters. That's very important information we need if we want to calibrate the data. In addition to all sky imagers, we currently have one imaging spectrometer or spectrograph at Milston Hill that basically the characteristics are here. This is an old system that covers from 5,400 angstroms to 7,400 angstroms. An example is shown here. To the left is north, to the south, to the left north, and to the right south. And you can see an enhancement in the red line corresponding to a SAR arc that was moving to the south of zenith of the instrument. And this is the cut that you get if you take a pixel wide line that shows that enhancement. We have plans to build 2 more spectrographs that will be installed in northern Maine and the conjugate location in Antarctica. And in this case, the design will be such that we will be able to sample all the way down to 4,000 angstroms, not 5,400 we had before, and 7,500 angstroms. This will be a nice way to study STIVs and SAR arcs. Because basically, you see here the map of all our all-sky imagers. We have distributed them all over the world. And for interest of this workshop is the region that is shown here in number 3 of purple, that we call the Savarola ionosphere. And the processes that we study here, when I did this slide, was SAR arcs only. But because we were looking at SAR arcs and then STIV appeared, I should update this slide and include stable red arcs and STIVs. Because in these regions, imager here in New Zealand, in Antarctica, Rothera, Milston Hill, and here in Europe, we see STIVs. And we should be able to see also, we see SAR arcs and we should also be able to see STIVs. Some of the results here to the left is an event that we studied in October 2013. The interesting thing in this event is that this was a typical SAR arc that during a brief period of time showed a series of beads or enhanced patches of emission in 300 that were moving along, moving left and right. Now, this is a very clear example. And this was not the only interesting thing in the red line, because when we look at the green line, we could also see those patches or those beaded structures that seem to coincide with the location of those red patches. Not shown here is like we have the conjugate site of Rothera in Antarctica, and we also saw these beaded red patches. So this is an ongoing study that is investigating how well conjugate are those structures. Something that I will show later here in this plot is the result of comparing with TC data, as Phil had mentioned. And here, these two zoom-in regions is hard to see, but this is a path of one satellite. In this case, is number 24, that this is noted with the star. And here is the TC values in this star, that when the piercing point is outside the beaded or the enhanced patches of air glow, there is no signature of any enhancement in TC. But a time later, when the ionospheric path is going very close to one of these enhanced patches, you see there is an enhancement in TC. This gave us a reason to think that these patches were due to some kind of ionization or precipitation due to soft electrons. And basically, this event is just to show that we can see a typical SAR arc that has some structure superimposed, and that brings a very interesting way to model these physical conditions. To the right, just quickly, an example of a SAR arc that is observed simultaneously at Northern Hemisphere at Miston Hill, this left panel. You see the arc there, and then to the north, you see the aurora activity. And then the Southern Hemisphere in Antarctic Peninsula to the right, again, aurora, and you see the arc. So we found very good coincidence regarding the location of these arcs, but there were differences like brightness also, and some of the characteristics of the edges of the SAR arc that we investigated and presented results in this paper. So just getting our hands into STEEP, this is a result from a paper that basically took data from Alberta citizen scientists and images from an OSCA imager that doesn't belong to the BU network, but belongs to the SRI network. And I just give here a quick advertisement. This is ASTIBAT's network that has several instruments that can also be used for SAR arcs and STEEP studies. So in this case, you see this very nice SAR arc. And these are the images on the hour and a half from Bridger that is very close to Alberta. This is Montana. And you can see to the top the brightness that is related to auroral activity. And it's very hard to see, but there is a very weak arc that we identify as a SAR arc. 15 minutes later, there are glimpses of that arc, and then it seems that there is another arc that is detaching from the main auroral activity, and this is the one that we identify as STEEP. Here is more clear, but after 25 minutes from this image, we see that there is no bright arc, but the weak arc that was observed earlier starts to appear again. So basically, we are seeing initially a SAR arc, then a SAR arc and a STEEP, and then STEEP disappears, was very brief, and then you have the SAR arc at the end. So we took the images, and this is a good way, as was explained, to determine the height of the structure by superposing the two fields of view, and we play with different heights. And you can see here Alberta to the north, Bridger in the middle, and the superimposed fields of view with traces just to indicate how well they were matching. And we found that the height of a better correlation, or the two arcs were observed in the same locations, was between 250 and 275 kilometers. So these are, I'm just showing two panels here. There were no satellite passes over in the Northern Hemisphere, but there were satellite passes in the Southern Hemisphere. So what we did is we took the passes, in this case, Swarm Satellite C, that was in the Southern Hemisphere, and we mapped it into the Northern Hemisphere at the time that we had observed a SAR arc. The SAR arc is here, very, very glimpsed, hardly you can see it. But the signatures from the satellite are showing a depleted structure in electron density and increasing temperature. This line corresponds to the trajectory marked through the width of the SAR arc. And interestingly, there is another feature that shows a much deeper decrease in electron density with an enhancement in electron temperature. In that paper, we are saying that this could be the indication of the precursor of a STEEV that will be observed later, as shown here in this panel C. Now we have the DMSP 17. We have the SAR arc, again, in the red, and the STEEV in the blue. And to the right, similar things, electron density, temperature, and now we have velocity from the DMSP. And here, these lines represent different heights of unwarped altitude, just to see where the satellite signatures from the plasma measurements would coincide or not with the optical images. And we found, or we verified, that for the SAR arc, going from 200 to 400 kilometers, the best altitude, or the matching altitudes, around 300 kilometers. In the blue line for STEEV, going from 200 to 400 kilometers, the best is between 200 and 250 kilometers. So the conclusion was that from these observations, optical, the two systems, and the optical and the satellite, that STEEV was more closely between 225, 250 kilometers, up to maybe 275 kilometers. So the interesting part, again, is in the top panel showing that there were some plasma signatures that they were not, didn't have a correlated optical signature. And we think this is interesting just to investigate if there's some kind of time delay with the plasma enhancements that it could be manifested in optical images. And I think, yes, this is a piece of work done by Josh. I think Josh is here, so he will talk about it. Are you here, Josh?
I am. You said that you could play the movie?
Yes, I can.
Okay. Well, yeah. Go ahead and start it. Let me just. It's getting late. I know. I may not get the stage again, so I'll just mention a few things here. That the I would challenge everybody at this meeting to be very careful about bringing preconceived notions about this phenomenon, into the discussion, because after all, what we have is, in imagery, what we have in terms of observations are the space, the time, and the wavelength dimension. And when one goes back to the initial question, why was this phenomenon sort of missed for years? And it was because we had the wrong mixture, the wrong recipe of those three dimensions, right? So a sensitive RGB camera gives us three broad spectral bands of discrimination, and that's enough to see this phenomenon. That's enough to separate the purple part from the green part. And the sample rates are fast with an RGB camera. So you're able to see bizarre things like this fine structure in this Neil Zeller movie. And so the citizen scientists who were on this paper, Neil, Alexei Chernenkov, Alan Dyer contributed, even though he may not know it, to this manuscript as well. And, if you look over on the left-hand image, you see something that looks like what we've been calling a picket fence, but it's also mixed with other features that seem to have the exact same spectral content that we don't understand at all. And sometimes it's important to understand the outliers in order to understand the core of the phenomenon you're looking at. And so there's really good new science to be done by really focusing on these, kind of artistic grade, if you will, images of the STEEV phenomenon in collaboration with the careful spectral analyses that Megan's doing in Bea. And so this is, just keep an open mind, because I actually think that we understand very little about how the ionosphere system should respond to ion jets of these velocities. And then, I'll pass it over to Toshi, I think.
But before we do that, this is Phil. Carlos, you didn't really define what a SAR arc was. Can you just very briefly do that?
Yes, that's right. Yeah. So SAR stands for Stable Aurora Red Arc. Stable comes from the first observation done like 60 or 50 years ago, which was a picture, and compared to the auroral structures that were observed, no wavy moving here and there, SAR arc show those structures were moving along the arc. So the SAR arc is the result, the theory. I think you lost my voice for a moment, sorry. The theory says that the emission comes from the result of interactions that are happening in the inner magnetosphere. As a result of those interactions, there is some heat flux that moves from that region down into the ionosphere along the field lines, reaching the subaurora region around 400 kilometers. That heat conduction is by soft electrons that interact with the molecules or the atoms that are in the upper atmosphere. Those are energized, and as a resulting grounding or going back to the ground state, there is emission, and that emission is the red line. And that's why we think that the SAR arc is not related to local processes or energy sources located in the subaurora region, but at higher altitude, in the equatorial plane, interaction from the inner magnetosphere with thermal particles. Very different from the potential theories or interpretations of Steve, but interestingly, they are occurring at the same location, and we will see later some cases in which they seem to be one evolving from the other one, or they seem to merge, different flavors of interactions.
Thanks. I just wanted to, and that also resonates while Toshi is getting ready. That just resonates with what Josh just said, is that when you see a phenomenon, you immediately try to connect it to things that you think you already know. But in this case, maybe not.
Yeah. Yeah.
All right, so let's move on. So just briefly, I'd like to mention the science activities that we do at BU, in addition to what Carlos and Josh mentioned. So we also combine a bunch of instruments to understand MI coupling states associated with Steve. So this is one example of the Steve events. So in the middle, we see the beautiful Steve image in the optical wavelengths. And on the right, we see on the same event from DMSP SUSY data. This is ultraviolet perspective of Steve. So by comparing these two, we can easily see that the Steve spreads over pretty wide wavelengths, even into UV. And this DMSP measurement was taken in the southern hemisphere. So we found that the Steve can happen in both hemispheres at the same time. On the left is a DMSP in situ observations from the same satellite. So the typical thing we see is the trough in the top panel. So the depletion of plasma density, enhancement of plasma flow in the middle panel. So those are SAID, those we discussed quite a bit. And the red line is an upward flow. So, that was also discussed earlier. So there's pretty strong, fast flows, both in horizontal and vertical direction within this trough Steve region. The third panel shows strong electron heating in the blue dots. So those are the extremely large heating associated with Steve. The fourth panel is enhanced Federer current. So this is generally the region of downward currents from the magnetosphere, but when Steve and SAID happens, the currents become more intense and gets narrower, and sometimes there are some localized upward currents associated with it. So that's a characteristic feature, and they're consistent with the emergence of fast SAID flows. The last one was an interesting one. So sometimes there are some precipitations associated with Steve. So that's the stuff that Jun Liang was mentioning earlier. So it's not always there, but sometimes in Steve events, we see some low energy and high energy diffuse like precipitation or arsenic precipitation coming. And Matt Zerogren later in this meeting will talk about the impact of such precipitation in controlling the steep dynamics. And in this event, we fortunately had the Themis satellite in the magnetosphere along the same field line, but on the equatorial plane. So this one told us that the magnetospheric signature of Steve. The briefly said that's the fast flow going in the same direction as the ionospheric flow, but they're very confined in radial distance, located right outside the plasma pulse, which is shown as sharp density gradient at the bottom panel. So what we found was that there was a really strong plasma flow in the localized area in the magnetosphere. And we'll discuss later that that's related to strong electron injection. That's unusually strong injection that confined area of strong flow into these narrow radial locations. Then let's go to the next slide, which is the last slide. If Carlos can.
Should be there now.
Yes, thanks. Yeah, so one question that we have been discussing was that the Steve is known to occur during substorms. Bayer has done a statistical study about it, but not all substorms have Steve. So Steve is very rare compared to the frequent occurrence of substorms. So we've been asking why only some substorms can have Steve and what's going on for other substorms. The quick summary of that work is that, so this is the comparison of the ultraviolet imaging from the MSP for events with Steve on the left and without Steve on the right. So basically the magnetospheric condition is very different. On the left, we see strong auroral emission above 65 degrees in latitude, and that's the center of the strong activity is highly shifted away from the midnights. So strong activity can extend almost to the dusk meridian, so like 19-hour local time. And that's far more dusk compared to the normal substorm situation. On the right, what we have is the same strength of the substorm, but aurora, as usual, is peaked at pre-midnight, close to midnight, but extending to like 20-hour local time. 21-hour local time probably. Yeah, so that's a usual state, but for some reason, the particle injections, reconnections, strong electric fields are all shifted toward the dusk, and that's the meridian where Steve is happening. So we'll discuss later in this meeting that the particle dynamics in the magnetosphere is quite a bit different in these two situations. So the electrons are accessing to the strong flow region, so that's probably changing the latitude region where the strong SAID flow can happen, and a controlled area of strong heating. Also waves are coming there, so if get emission, that's the study those things as well. So the way how the energy comes in is different, quite localized to the 21-hour local time, and that seems to be the condition for creating Steve for certain type of substorms. I look forward to discussing more on this later in this workshop. Thank you.
Thank you, Carlos, Toshi, and Josh. Other questions for any of the speakers?
Actually, Toshi, I forgot. What kind of difference, because in the electric or the loss drift speed of SAID Steve, SAID without Steve, is it kind of the same as Bill Archer reported? I mean, in the substorm you studied, you looked at.
Oh, well, in terms of the occurrence of SAID, yeah, SAID tends to occur when Steve is occurring, and such intense SAID is not there for events without Steve. So so far, there is no exception. Strong SAID is there when Steve is happening. So the question, I've been thinking was why strong SAID is happening for certain substorm, but not all substorm. So that comes to the area where you studied, how the substorm current wedge forms, injections, take place and bring high energy plasma to the inner magnetosphere. The particle trajectory is not always the same, so that changes the region of strong flows and waves in the inner magnetosphere.
If you look at because we came to the relation between the strength of the electric field for SAD and the pressure of hot ions. So basically, when comparing, say, electric fields in the plasmasphere, like 10 millivolt per meter, which gives you 100 in the ionosphere, and say 40 millivolt per meter events, which gives you, that depends on L shell, of course. So anyway, it's really the gradient of the hot ion pressure penetrating into the plasmasphere gives you this electric fields. If you could look at the data, would be interesting, because there was not too many events to compare with.
Yeah, so I have one slide to present later, so I hope we can discuss that specific topic. But the short answer I have is that interestingly, the ion pressure for intense SAID and other SAPS events are not too different. I can show you, how the data looks like. The one big difference we saw was the electron flux, which determines where the sharp conductance gradient forms relative to the downward region 2 ferroni current. The separation between ions and electrons are very different for these two types of events. So even if you have the same level of ion pressure gradients, the latitudinal extent of the low conductance in the downward region 2 ferroni current area is quite different. And that changes the strength of plasma flow, because you only have small area of low conductance where you can drive strong flows if the electron injection is really strong. But if electron injection is weak, you can have the broader SAPS flows.
The electrons should stop at the plasma pores.
Yeah, electrons stop there, ions goes forward. So there is always the separation, just the separation distance is changing depending on how the electron or how both ions and electron injections are coming. And that seems to be the difference we see based on the oral imaging. The injection location is different for Steve events.
Okay, sure.
Right. Bea, I think we were going to, go ahead and.
So we're running very close to the break. Thank you so much to everyone that have contributed to this talk. This has been fantastic. I want to check that we have a couple of contributed talk by Toshi, Josh, and Carlos, if I remember correctly. I want to check if you guys are able to join the session starting at 6:02%.
I can.
Great.
Thank you. So
yeah, let's see, I can join until 10 minutes to 7.
Perfect.
Okay,
Thank you.
That works.
Yes, that's fine with me.
So we're going to go on a quick break for everyone to eat, relax. And if you have time and energy, join the Gather Town to catch up with people and have more discussions. So we'll see everyone in an hour. So 6 p.m. Eastern time.
Perfect. Yeah.
Thanks very much. We'll see you then.
Those in Europe taking up.
Hey, Eric.
Hi, Bea.
How
Say
are
hi.
you? Yeah, we're so happy you joined. Are you going to be able to stay for the second session?
I'm going to stay for the second session for a bit and then go home and then sign back in.
Okay.
I have to get dinner for Sean, and Emma's taking off because she's got Nathan and Owen.
That's awesome. We're running a little bit late. There has been like a lot of good questions and good presentations.
So you're on a break right now. I see.
We're in a break for an hour. Yes.
Oh, I'm gonna be in the background. You can't see me.
Yeah, now I can see you.
No. I have to. No, it doesn't.
Oh, you just materialized. Yeah.
I'll just sit in the background.
Yeah. So how are you, Bea?
It's been good. Yeah, busy. How was your class?
Really good for some of them. Really frustrating for others. So, I'm doing my job.
Someone was asking how much, I think it was Phil the other day, how much importance the departments get to the evaluations that the students give to the professors in the different pages. How is it in Calgary?
So it's really interesting because Bea just asked how important, are the student evaluations for the department. And the answer is that right now, because of the teachers, because of the academic union, the department doesn't get our evaluations.
They will this year. I think they will this year.
Okay.
Well, everybody knows evaluations are totally flawed anyway. Seriously, they are.
Yeah.
Right? Like statistics show that male professors get better reviews than female professors.
Well, I don't know. Is that inherently flawed?
I'm just saying.
Okay.
It's like a thing.
Taller profs do better than shorter profs?
I probably.
I'm not liking that department either. So that's really bad for me.
And Gareth's just there thinking, well, I've got tenure.
It's all evaluations. It's like, anyway, the process by which students provide feedback needs to be modified. It's like IT, right? You only complain. You never praise IT.
Yeah, that's a good point. Yeah.
So it's right. So I misdid the timing. So it's 3 hours starting at 6 your time. So I'm going to take off soon and go. I'm going to walk out with them. I'm going to go home, and then I won't have to sign them off during the session. How was the earlier session?
It was good. It was at the beginning it was quiet. I was hoping people would make more comments, but I feel like always at the beginning of a workshop everyone is more quiet, right? So hopefully in the second session they're going to be more participate more. People are afraid of unmuting themselves.
How was Megan's talk?
It was great. She
Good.
got very good questions and she covered exactly what we needed her to cover. So it was great.
Good. Yeah, no, I liked that. Yeah, she did a good job on putting it together. So
Phil asked who was funding the Aurora X. If I'm correct, it's CFI, right?
it's CFI. It's a mixture of CFI, CSA, the province, East European Space Agency through Danish Technical University, and with $100,000 thrown in from the university.
Wow.
Yeah. So it's working. It's working out. I think it's working out really well. I think it's going to be a really cool tool for the community.
Definitely, yeah. She was showing a quick demo of finding conjunctions with satellites.
Yeah.
And that worked great.
Yeah, and then you can also put in now that I want it when there's amorphous pulsating aurora in the field of view of the camera and stuff like this, right? And
is it included already in Aurora X?
Yeah, I mean, like we're on a break. I keep thinking of Rachel when I say we're on a break. Can I share my screen?
I think so.
Yeah.
Let me check.
Yeah, I can.
Okay.
Yeah, just for a second. So if I go to Aurora X, you can see this, right? Bea?
Yes.
In your chats and everything. You want to just
What chats?
So stop sharing. 1 second. So you're gonna get an email. comes up, and then people are going to see student marks and stuff.
Oh, that's okay. It's okay. So we go to conjunction search. And if you say, okay, I want to look at 2018, January 1st through February 28th, apply. And then say I'm interested in conjunctions between Themis ASI, Swarm, and I'm interested, and then I can look at the metadata filters for Themis ASI. And I can say classified as amorphous pulsating aurora. Okay. And we're gonna be doing a lot more of this as time goes on. But if when I do my search, it looks for conjunctions, but only the set of conjunctions where our algorithm thinks there's amorphous pulsating aurora in the field of view of the camera.
Oh, that's awesome.
And then we've the Lasse Clausen. So we've classified the entire Themis ASI data set with his algorithm. And so you can specify, I'm interested in conjunctions when Lasse's algorithm says there's arcs, or I'm interested in conjunctions when Lasse's algorithm says there's discrete aurora, right? And then we also have a cloud, no cloud thing. So you can just say, I want conjunctions when we think it's clear. And then we're hoping to build that up over the next 5 years to have that be really like, and then like Nora Pardemes is going to be putting her data in, and the old Miracle data. A lot of the old Miracle data is actually been manually classified.
Wow.
And
should I go fire, Darren?
why? Because it's slow?
Yeah.
Sometimes it's slow. I mean, like our
I'm okay to go fire.
go fire him. Why don't you go grab him?
You know you and I, right?
You gotta put your mouth.
Yeah. There we are. And so now I could put this is a list, right? Which has, 107 entries in 2 months, right?
Wow.
And then I can just open all results in Swarm Aurora. And so this puts me in Swarm Aurora,
It was slow.
right? And so there's a conjunction that happens to be the swarms in the Southern Hemisphere, but that's amorphous pulsating aurora. And then I can just skip through the events. That's amorphous pulsating aurora.
Ooh, that's
Yeah,
great.
this is cloud. That's cloud. There's some things that fool. That's amorphous
Yeah,
pulsating
that's
aurora.
pretty.
That's amorphous pulsating aurora, as is that, as is that. And so you can kind of say, like, if you want to look at, say, have a student look at that, for instance, you can say, okay, I want you to just run this search engine on 5 years of that data. And then you'll come up with like thousands of conjunctions, and most of them will be amorphous pulsating aurora. And it takes, that would take hours to run if you did that in 5 years of data, or an hour at least to run. But what's the big deal? I mean, you just walk away, have lunch, and come back, right? And so
Better
I
than
really,
what we did earlier.
yeah. So I love this feature here. I really love this. And then the other thing that I'm liking a lot in Aurora X is in Kiagrammist. If I yes, well, I can go back to 2010 and use mine, and so if I go to 2018, September 1st to so and so you've got these kiagrams, and then you can sort of launch into what we call the snipping tool. Okay, and so when you look at this Aurora here, the idea here is to allow people to grab 10-minute, 5-minute, whatever segments of video automatic, like just so you say, okay, well, I want a video of southward moving arcs, right? And so that looks good. So what I'm going to do is mark that as the clip start, and then I'll go to here and mark that as the clip end, and then I'll play my movie, and it's just playing that section, right? And then I can play around with the playback speed because I want to embed this in a talk, or maybe I want this to be super fast, maybe I want it to be super slow, right? And then once I sort of settle, okay, this is what I want, then I go download clip, and then it's going to give me a link. And this last part will be working within about a week, but this last part is working.
Well, it's getting there.
And so your clip will be here. I'm not sure which one that is.
So
that's not it. And so, but anyway, the idea is that it's, you know, and then we're going to have like lists, lists of field line resonances, lists of substorm onsets, lists of arcs, lists of that. And so you can say, okay, I want a video of a substorm onset, and then you'll see like a list of 20 or 30 really good substorm onsets seen in Aurora Max and in the RGB, for instance, right? And then you can just say, you know.
Any chance to include the list of Steve that we have?
You give us a list and
yeah, sure.
100%.
yeah, because we started also this. If you go back to Swarm Aurora, we started, and I go to the conjunction finder, we started custom import, and so this is Toshi's substorm list, and so. Is that, yeah, so this is Toshi's substorm list. So now I'm cruising through Toshi's substorm list, right? And, you know, and then we're going to put Megan's FLR list in here, and I've got a list of torches and omega bands from Mackenzie Ratzlaff. I'm putting that in there. And so the idea is to just have people be able to find interesting things fast, right? But yeah, of course, we'll put the Steve list in.
Oh yeah, absolutely.
Yeah.
Sure. Where do I send it? I have it. I can send it today, or maybe Friday.
Send it to Darren. Send it to Darren.
Thank you, Darren.
So okay, I'm gonna get going, Bay. I'm gonna go home and I'll log back on. Okay.
Perfect. Great to see you all.
Yeah, good to see you. I'll be there. I'll be there in less than an hour. Okay.
Awesome. Thank you.
Awesome.
Bye.
Okay, bye.
See ya.
Well, folks, we'll start back in a few seconds here, a few minutes. We're just kind of shuffling the schedule here. Now we're going on to a session. We're going to be starting soon a session for the citizen science, or we're calling observations 2. Now, Emma and Michael, is it all right if we switch the order a bit to accommodate some schedules? So the plan is to have Josh Semter to go first, right off the bat at 6, and then Michael and Emma go right after that. Does that work with your time frame?
Perfectly fine.
Okay, great.
Wake
And then,
me up.
yeah, and then after that we'll go Toshi, Carlos, and let it go from there. Okay. All right then. All right. I'll just mute for a second here. Suppose we should just wait for Josh to join us so he can go first.
Here he is.
Yeah, he has just connected.
Perfect. 6 o'clock.
Okay, so it's just a bit after 6 here. My name is Gareth Perry, so Bharat and I will be moderating it. I have a co-moderator next to me who's just under 3 years old, so I'm showing him the ropes. So first up, most of you heard we're just switching the order a bit for to accommodate some folks' schedule. So Josh, if you'd like to go first, take it away.
Yeah, that would be great. Can I share my screen?
You should be able to. Let me double check.
All right, let's do that. Second here. All righty. So I was told I can have about 5 minutes, and I thought I'd really try to keep the workshop vibe going, just throw out some data that hopefully some people find is interesting. I assume a lot of people are already kind of aware of it. This is a great picture from Edwina Podemski, one of the many citizen scientists that I've been in contact with, and Liz McDonald and others have worked with, obtaining our combination of art and data from the community that's just passionate about looking at the night sky and finding cool stuff. And so this, this is your supersonic ion drift that we've been discussing, or, sort of 2 to 3 times the ion sound speed. We're moving ions through this coupled plasma neutral system. So one could look at it from that perspective, I guess, and just say, what should happen as we, reach certain critical thresholds in that kind of a system. And that's really fun to us who have been looking at multi-scale structure for years and years. The continuum spectrum, we've had a lot of discussion about that. I put some names up here, and it's not meant to be comprehensive, just figured I'd give a shout out to a few people whose papers I've been studying. There's other layers that are sort of like the continuum spectrum, but maybe not, maybe a mixture of different balances of spectral content that Carlos talked about. And then we have, we've done some investigation of this oxygen green line emission. We call it a picket fence, but sometimes I wonder if that's just a question of what they call patternicity, that it kind of looks like a picket fence in a certain projection. In other words, if you just decide to illuminate random structure in a narrow band that's right next to the Steve arc, then maybe it comes out looking a little like a picket fence. And maybe sometimes it comes out looking very coherent. And maybe we have a bias towards thinking about things in terms of things that look coherent. And, I just raising that question, it's not an accusation or anything. Like I said, I think we should keep a very wide open mind when we look at this phenomena as we go through this workshop, and hopefully many future workshops to come. I decided to make my first foray into this field by just highlighting some features that have very little to do or are difficult to find connections to the geomagnetic field. And, so what we see is these horizontal sausage-shaped streaks that are about a few hundred meters wide that go zipping around underneath the so-called picket fence. And sometimes I think it's interesting to look at those weird cases if you're trying to understand what's happening with the phenomena as a whole. And so let me just say, I guess everybody's kind of initiated here, but when you put an image like that one side by side with typical images of the aurora, it becomes very apparent that we're looking at different phenomena. And Steve Mendy, figured that out right away. I remember talking to him about this. He looked at color images of the aurora and said, no, that's not aurora. That's way too green. And had a hell of a time pushing his paper through reviewers because there was no real spectroscopy at the time. But if you look at poleward boundary phenomena here, in the upper right, you also see a mixture of red and green, but of course it's got the N2 first positive group, N2 first negative group, and so forth that gives it this broad grayish emission. And then you got a much more spectrally pure 630 nanometer red line above it. And some other images are shown here as well that really highlight that fact, right? That it's pretty easy to pick out that we're looking at something different. And the point I made before the break, I think is something to really think about, right? We missed this because we were looking with the wrong instrument. What you really needed was an instrument that had just broad, in this case, 3 broad spectral ranges, i.e. a DSLR camera, and could take images at high cadence and high spatial resolution, and bang, the phenomenon appears. So there's this kind of mixture of space, time, and wavelength that was fortuitous, that allowed us to open this whole field of research. And I think that's really important. And that came from the citizens and didn't come from us ivory tower scientists. So here I'm just going to quickly show a couple movies to illustrate some things. This one's from Matthew Wheeler, who I've been having a lot of interactions with recently up in the Calgary area. He lives underneath Steve, tells me that whenever Steve appears, it's not on the horizon, it's right over his head. So there's a statistical study embedded in there somewhere that might build upon Bea's work. But as you saw in this this frame that I just showed you here, this gives you an idea of how things can look field aligned on the horizon. We know this from the aurora as well. And then when they get overhead, you realize what you're looking at is probably more like undulations in space. This also highlights the fact that the green emission is not relegated to the picket fence. It can appear in different contexts inside Steve. Let's see, this is another one from Matthew Wheeler. This one's really fun. Little green tornadoes that appear as vorticity. One thing I would challenge you to point out the magnetic field line orientation in an image like this. It's a real challenge, as Liz and I have discussed when we were putting the paper together, that we're at midish latitudes with strange perspectives into the magnetic field, and also phenomena that they have an organization, but they're not organized like in ways that we're used to seeing in the aurora. Let's see, this is a real-time video by what Sony should call the Steve Cam. I mean, this is a camera. This is the what is it? The Sony A7 II. This is with an f1.4 lens, Karasava Bogdan, and this is the kind of data we want to start thinking about. Okay, and you can see that this combination of green and mauve emission is really difficult to interpret in terms of the language we may be tempted to use. There are these kind of, this looks like a Christmas candy or candy cane or something like that, the way the green and the red work together in an image like this. And, what's nice is we have locations and clear star fields, and we can do a lot in terms of establishing the geometry and the velocities and so forth in imagery like this that comes from these citizen scientists. So it's more about the space-time structure, those two dimensions of observation, than it is about detailed spectral analysis. Okay, so this is one of those. This is a movie by citizen scientist Alexei Chernenkov, whose work we featured. Michael Hunikul, maybe he's still on the call. He did terrific work analyzing this in detail from two locations. I mean, he took citizen science imagery, which had camera uncertainties in the order of minutes, matched things to features on the horizon and stars in the sky, and showed the world how you can extract very quantitative information from beautiful imagery with very uncertain geolocation and timing. And so we were looking here at the trajectory, the formation and trajectory of these weird little features underneath the green emissions. And you can kind of read about the extensive detail of his stereography technique in this advances paper that came out in 2020. And so finally, let me just mention Neil Zeller. He's got some famous movies out there. This is one of the ones we used in our paper. Again, the whole idea of challenging you to orient this with a magnetic field topology is out there. I did things like, all right, so we can do the star field fit. We can put it in a horizontal coordinate system. We can do things like this. We can take a IGRF model and an assumed altitude and start projecting little poles that represent the magnetic field. And the magnetic field is in these images. This is so much fun, right? The magnetic field is here. It's these little streaks that grow up the field line. And that was one of the main points of this paper, is that, we have initial suggestions that blobs forming at 100 kilometers altitude, okay, in the kind of the collisional, the Farley-Buneman altitudes, our instability altitudes at 100, 105 kilometers, sort of can streak across the field line, but also grow up the field line. And I do not know if this is the initiation mechanism or what it has to do with the initiation mechanism of the standard picket fence, but it may have something important to do with it, because we observe lots of these cases where we see connections between field-aligned structures above and horizontal motion below. So we're still working on all this. I've been working with Mears Oppenheim at BU and with Toshi and with Matt Zettergren. We have, I have to say, I feel so fortunate to have this really complementary group of scientists at BU that we're able to put together some really interesting discussions around this topic. And looking forward to collaborating with anybody who's willing on these things. So I'll just leave it at that.
Thanks, Charles. Those are some excellent movies. Mesmerizing.
Yeah, good screensaver stuff.
That's for sure. Any questions? Comments?
Yeah, I want to comment. Josh, we just, Anatoly and I just submitted a book to Elsevier. It should be published in a couple of months. And in the chapter, final chapter regarding subaraural arcs as a mysterious streak, I pointed to this paper and took a couple of pictures, plots from your article.
Oh, that's great.
I think I have some, no, at least for me, it's feasible or plausible mechanism for explaining both the green color in this fence and in motion for your streak. How you pronounce it? Streaks? Streaks. No,
Yeah.
anyway, I'll
don't
mention it tomorrow.
Okay, that sounds good. Looking forward to it. Yeah, I've been meaning to talk to you about this. I mean, it was a few years ago at this point that you visited BU. I guess it's been a little while, but yeah.
It has to do with instability of field-aligned currents.
Yeah.
Combined with the creation of the hole in the region of downward currents, small-scale current. And that's combined effect might explain, might at least give you some hints to explain that.
Yeah.
Okay, we'll talk tomorrow.
Yeah, that's terrific. And anybody who's using data recorded by these citizen scientists, here's one little provocative thing. I certainly encourage you to put them on the author list, because we usually do that, right? If somebody spends their life creating a system that provides us with data, then they belong on the author list, whether it be a NASA mission PI or a passionate citizen scientist who gets the call saying, oh, there's a substorm, everybody go outside, and they rush outside in the Arctic and take images for us. So
absolutely agree.
Yes. And we have asked the citizen scientists to also tell us a little bit more about what are the best practices that they think are important to highlight to the scientific community.
Yep.
Yeah.
So I just wanted to say, Josh, the structure, I really like how you're talking about, trying to keep an open mind and not, put these things in such, clear boxes and categories. And, sort of along those sentiments, some of these beautiful pictures that, I worked with for some of the stuff that's been shown here by Robert Downey from that very, very distant, horizontal perspective. And, we were looking at some of those in Calgary, probably forever ago. And I think it was Megan Gillies was one of the first person who said, like, is that at the very beginning of the event, it's like, is Steve itself like lined along pickets? And absolutely, near the beginning of the event, it is structured at that same spatial cadence and moving in the same sort of way, just when it's most faint. So there's something about a larger time, like a spatial scale there that is true all the way up, at multiple altitudes in between both Steve and the picket fence there. And so that, there's more information, in that event. There's so much information in that event. And,
maybe I can get Matt Zettergren to show, as part of his talk, he has a Gemini 3D simulation run of GDI. And if you take a cut, just sort of take one horizontal cut through that and just plot the density there, it looks just like a picket fence. And the point being that maybe this is, it's like the flashlight, it's turned on where the electric field is huge. In other words, we reach some threshold whereby we can excite an emission that tells us that it's happening. And that's why it looks that way, right? So that's a possibility. Anyway, yeah, I appreciate your comments, and we should just make a big we should make a big database of these little snippets. The problem is this is not synoptic images, right? It's just kind of sporadic here and there. We were looking, for instance, like I saw that Michael Hunekul went out looking for the September 2017 to see if there's any citizen scientist data available. I mean, if we had a real convenient way to just dump all of the stuff we find that we scrape off the internet that has a date and time and location and put it somewhere, right? I mean, maybe that's a kind of a light lift, if you will, in terms of putting together a more extensive database of small scale structure in Steve.
Josh, that was a fantastic talk in images. I'm just wondering if you applied this analysis to sort of bound like lifetimes of the green emission. Have you tried to do anything with small scale features in the continuum emission to maybe upper bound the lifetime?
Yeah, we're looking, well, I can tell you that, like there's a currently qualitative impression that you get, like when we look at the movies that we see this like weird green stuff form. It forms in a burst after you see some kind of a phase structure go trucking through at 6 kilometers per second in the red emission. I swear. So it really looks like a tip vortex or something. So we focused on this just because there was sort of room to make a publication, you know what I'm saying? But I absolutely, the small scale. So we have lots of cases. I don't know if Michael Hirsch is on the call today. He's been really instrumental in doing these precision star field fits. And that's just really exciting. As soon as we can get all the citizen scientists to data to represent a really accurate geolocation date and time, we can really start putting constraints on the size and the lifetimes, locations and so forth of the red emission as well. Yeah, I mean, the one thing I want to say about the red emission is that it's I think it's just incredibly deceptive. And Matt Zettergren is going to show some of this tomorrow. Actually, I think he's dealing with family issues at this part of our workshop. But he's been looking at KHI development and looking at projections through it and sort of comparing it to what we see in these time, 1 second time sequences of the red channel. And so it's hard to know what we're looking at, right? I don't know, maybe you have an idea, Brian, but when you're looking at an undulating feature pass through, are you looking at the phase structure of a wave, or are you looking at the actual motion?
Yeah, it's impossible to know. Yeah, the reason I brought it up is because this NO2, this vibrational nitrogen hypothesis that I suggested, Phil said very confidently. I'm much less confident about it, and if you can show that the upper bound of a lifetime is low enough, you might be able to rule that out, because we know that NO should have a really long.
Have you looked, Brian, at the earlier papers of Space Shuttle Glow? Because they were.
Yes, it's fascinating.
Yeah. That stuff, they were speculating NO2 and NO.
So I think they decided, or they convinced themselves that it was NO, because there was this interesting, there was like an accidental release of NO from some space shuttle something payload, and then the brightness they saw just enhanced.
Yeah.
So they think it was the NO2 continuum, although they still don't know where all that NO came from. And I think there's really a nice analogy there.
Yeah, that raises an important general issue, is that what other geospace contexts do we have cases of sort of 6 to 8 kilometer per second ion drifts? And of course that's one of them. And then there's the other one is the shape charge releases, at least the initial phase. We have those as well. I just started looking into some of those old experiments. I think it would be fantastic if we could reinvigorate that field and those are just fantastic plasma physics experiments. And and they haven't been conducted since Gene Westcott and so forth in the early 70s. And the stereography they were doing was with, of course, wet film cameras and all. I mean, with modern systems, imagine setting up an active Steve experiment. That's what this group can do, right? We'll propose to NASA. We'll set up 5 of the high-tech cameras, right? And we'll do 3-dimensional triangulation of this thing, and we'll actually and we'll see if we can create the. I don't think they know the spectroscopy of those emissions really. I guess it was all barium back then. Anyway, so there's other cases to look into. I think the HARP heating experiments might be relevant as well. I mean, if you're talking about producing extreme tails on electron distribution functions and so forth, we should probably look at that literature again.
Yeah, and it's a good point, not just to interpret interesting experiments we can do, but like you mentioned, these flows don't just happen in Steve. We can see what's going on because there's not all the auroral stuff getting in the way, but those types of flows happen elsewhere. And what we're studying is not just what's happening in Steve and trying to explain Steve, but something very interesting is happening with the neutral atmosphere here in Steve and elsewhere.
The shuttle stuff, I remember that I was actually just reading, it was the 1991 Nature paper on it. They were mentioning that, they thought there was a 680 nanometer peak or something in the spectrum. I don't know, like it was actually sort of like Steve, right? Like it's continuum, but there's an enhancement that makes it reddish, right? I don't know.
Yeah, the spectral shape is a question to me. I need to review that more, because if you plot like the NO2 spectral shape from some lab experience in the 80s, it doesn't really quite match the Gillies spectrum. So there's a lot to do.
I'm gonna just. I know we got to transition to other things, but to connect the tissue, I want to react to something that Brian just said, which was that the things I put up in the front were literally okay. So you're right. A lot of this is well, okay. At least we know this, but under what conditions do we know it? And when I do citizen science stuff in the general population, people have this funny idea of science in that either it's 1-0, right? Either we know something or we don't. This community understands that that's a gray continuum, all right? And I think we also can do a service for the general public by propagating the fact that it's okay not to know 1-0, but that continuous progress in this is the way that we actually figure things out, and that we're always prepared to change our minds if we find something else going on. So that's frankly a social responsibility that we have. But I think by working on topics like this one, we can actually push that forward into the general community. And I think the world desperately needs that. So it's just it's a more general statement too. And I'm glad you brought that up, Ryan, because I think that's entirely right. At least for the case that you looked at, it's plausible, but it's not necessarily the only one. It doesn't mean we should sit there paralyzed and not do anything.
Yeah, not knowing is job security.
Oh boy. Wait till the comments come.
It's being recorded? I don't know.
Alan is here. Alan
Yes.
is
I think
Hi, Alan.
Josh, doesn't it depend on why you don't know whether it's job
that's right.
security or not?
That's right. That's
To
right.
be
That's
fair.
right. Yep.
Is it really unknown? Or are you just ignorant, or are you incompetent? I
Well,
don't know.
I mean, for our citizen science folks, I once got a review back that said, I believe Eric doesn't know the answers to the questions that he's asking. but the referee felt that the rest of everyone did. So
That's a great story. Thanks for sharing that. I'm going to take that to my grad students when they're feeling really down about reviews.
Was that from a student, Eric, or was that from someone in the community?
No, that was my early days, and it was I actually think it was Bill Lotko. It was on a project that was funded, but it was my first big project, and this person who I'm sure was Bill Lotko, who's a prof at Dartmouth University, Dartmouth College, and he literally said, like, I believe Eric does not know the answer to these questions. and
okay. In the interest of time, I'll be rude and interrupt and pass this on to Emma. Did you want to go up? We're going to transition over to some citizen science input and presentations now. Emma, did you want to go next?
You're mute.
You're muted, yeah.
Oh.
Yeah, let me just find my slides. I was kind of expecting Chris to be speaking next, but it doesn't matter. It's just fine. Fine to do it in this order. Are you seeing my slides?
Yeah.
Yes.
Oh, great.
Great.
Greetings from Finland. So my name is Emma Bruce, and the background image is where I am at the moment. I'm at a summer house or old farm near the Russian border. And I hope my network still holds, because I've had some trouble having it up and running. So please let me know if you haven't heard anything for a while. And my thoughts are that I'm going to tell you a little bit about what's happening in aurora observation seen in Finland and Sweden. And we are located in pretty high up in Northern Europe. And the red line at the bottom of the map shows how far North Edmonton in Canada is compared to the Northern Scandinavia, where we are. And the map, by the way, shows how the community's TIV observations are located. So each green ball in the picture represents a TIV observation. And as expected, the largest amount of them still exists in southern Finland, even though northern lights in general occur more often in northern Finland. But more about these countries. So there's about 10 million people in Sweden and 5 million in Finland, and both countries have active Aurora observers Facebook groups, and the Swedish group is called Norrsken. In Swedish language, it means Aurora Borealis, of course, and the hottest question of the day, how is revontulikyttäjät pronounced? It goes like revontulikyttäjät. Now everybody repeat after me, revontulikyttäjät. So it means someone who is eagerly watching Northern Lights in Finnish language. And both of these countries have also active astronomical communities of amateur astronomers and professionals. And Sweden has 3 associations, one association for young people, one for professional astronomers, and one for amateur astronomers. But Finland has only one association for everybody interested in sky and space. And next I'm trying to describe you what amateur astronomy and astronomy in general has to do with aurora observations in our area. This will be a bit longer background, but let's see if I manage it through. Astronomers have a long history of making documented observations, as we know, first by drawing and making notes, and then by, of course, photographing targets. And some 60 years ago, British astronomy clubs were divided into different focus areas called sections. And this tradition still can be seen in Swedish and Finnish astronomy clubs today. And there are different sections for solar system targets like planets, comets and stuff, deep sky objects like galaxies and open clusters and that kind of objects outside the solar system. And then there is a section for technology and devices, but in URSA, meaning the Finnish side, there's an extra section for atmospheric optics. And this contains phenomena like atmospheric halos, noctilucent clouds, and of course, aurora. And this section has gathered aurora observations since, say, end of 90s, first by email and now by using observation gathering system called Skyward. And Sweden has no such interest group, but amateur astronomers there do follow what is happening in the sun and in the northern sky. And both countries' astronomical magazines, of course, write about these phenomena too, and have some cooperation with each other, regardless of totally different languages. And these magazines are published by main associations of the area. And then there are, of course, these 2 active Facebook groups that exist outside these astronomical clubs, although many of the users are members of the local astronomical associations. So these kind of groups overlap always a bit. In addition to this, most of the biggest cities have their own local astronomical associations. And the local clubs maintain city observatories that often have fireball or aurora all-sky cameras on their top roofs. And some of these cameras even record the night sky 24/7. And there are four clubs that are kind of maintaining good quality cameras capable of recording aurora images with, night sky at the background. Tampereen URSA's camera is probably most popular in the country, and it's used quite a lot when making decisions of when to go outside. But the cameras are, there's maybe 8 of them. The cameras are located close to the main city so they can't record very faint forms of aurora like SAR arcs. But cameras in Jyväskylä Sirius, these two cameras in Nyrälä Observatory and Hankasalmi Observatory are capable of recording very faint forms of aurora. And one of the cameras, I guess, is maintained by Nagoya University. And Jyväskylä Sirius is the kind of home association for Erik Rutanen, who was speaking to us in the beginning of the meeting. And also something to mention about Hankasalmi Observatory. I just realized that the Virginia Tech's SuperDARN radar is probably located in this association's grounds. Yeah. I also wanted to mention the local space physics institutes and research centers in the map. So there's a ASCAT radar network in the northern section of Scandinavia, Tromsø, Kiruna, and Sodankylä being the biggest centers in the north. And all these three countries have networks of magnetometers available. I want to mention this as a background information in case you might need some data for some reason from some of these sources. So, about the observation gathering nowadays in Scandinavia. We are using an observation gathering system called Skywarden. It's located in two web addresses, can be visible. They are visible on the bottom of the screen. One is targeting Finland, the Taivaanvahti FI, and a recent addition, himlakollen.se, is targeting, of course, Sweden. So the site operates in 3 languages and targets all Scandinavian countries. One doesn't need to be a member of some of these astronomical clubs to be able to participate. Everyone can join in, but we are targeting just Northern Europe because the site is working only on volunteer power, and URSA, the founding association, is only located in Finland. So the site was founded in 2011 and by me and Marko Pekkola. We both have our daytime jobs, me as an IT consultant and Marko as an editor-in-chief of Europe's second biggest astronomical magazine. So there's a good chance that if you're an amateur photographer, Marko might contact you and ask for your images to be published in this magazine. Or if you're a researcher, he can contact you and ask for your comments to some article about Northern Lights. That's very typical of him. But Skywarden is his hobby, and nowadays the site has been used by more than, say, 18,000 observers, and 2,000 of them observing auroras. The amount of observations currently is close to 100,000, of which 10,000 observations are of aurora. There are lots of other subjects we are gathering in, like the topics of the rest of the sections, like deep sky objects and solar system objects. So there will be comets as well in the Skywarden site. Skywarden team consists of moderators and subject area specialists. There's an image of us in the right side. We've got several phone apps at the moment. Most of them are just for reading the contents of the system. But there's one mobile app for Windows Phone capable of receiving observations. So in the background, we have open APIs to receive the data as well, and not just the mechanism for fetching the data. Some words about our principles. All saved observation data is available for anyone to browse or fetch for research purposes. And everything sent will be checked before publication. And observers have about 100% control on their data. And this is because we wanted to apply the principle of my data. So if they want to modify their data, their images, their descriptions, they can freely do so. Or if they want to, for some reason, delete their observations, they can do so. But if you want to use the observation data, feel free to ask me some help for that. And I'll gladly provide the data you are needing. But so basically, the users have given us permission to use the data for research purposes, but still, if you are using the data, it's a good idea to inform the observers themselves that your data has been valuable, because it highly motivates the observers to continue on what they are doing and maybe improve in their area. Then a couple of words about the aurora observations we have. We've identified 2 events similar to the one described in paper by Carlos and fellows. The paper describes an event where SAR-arc and Steve can be seen in the sky at the same time. Similar situations occurred over Finland 2 weeks after the one described in the article, meaning 11th of October 2017. There's some older observations, of course, that might be similar cases. Then there is the subject of SAR-arc seen together with green blobs. We got interested in this last autumn after seeing it happen quite many times in a row. And we started asking questions like, what is the relation with Steve and picket fence? And if the same question could be asked of SAR-arc and green blobs as well. And in both cases, there's an aligned green aurora band that can be seen below something happening higher up in the atmosphere. And in both cases, the pair is separate from the rest of the aurora in the north. We've identified 11 nights when this happens. There was a very recent case recorded by Alberta Aurora Chasers in this October, and congratulations for John and Chris about excellent pictures. They were impressive cases of this phenomena. And thanks for Mike Huneko about informing me about the work that you and Liz have been doing by gathering Stormer's old observations about this subject. So there was this high point of observations, which we call a super night, 7th of October 18. And let's take a look at that one. I remember being outside myself that night, but it provided everything imaginable. There was Steve in the sky, a blobby SAR-arc, and even dunes. But this thing got so interesting that I've annoyed quite many people by asking questions of this phenomenon. And I hope I haven't been asking like Eric Donovan proposed. Do you know something of this? Or if you don't, let's skip the subject. We are still very interested, and we'll would like to participate if we can, if this is something interesting you are interested in. Although the cause of this is unknown, we do know the height of these green blobs, because the height is known since the dunes appear on the green blobby auroras, and the height of the dunes on this specific night is well known and documented in the original paper of dunes, and we know it to be 100 kilometers. There's two cases of from the same night where dunes occur in these green blobs, one from Pirjo Koski and one from Matias Takala. So the blobs must appear at the height of 100 kilometers, which is probably the same height where picket fence, of course, exists and can be seen, or about at the same level. So about a couple of associations mentioned, sites mentioned, there's a list available, and thank you for inviting me to join you in this workshop. If you later have questions, my email address is at the bottom of this slide set. Feel free to contact me. This is about it. Does anyone have any questions? Or are we entitled to ask questions at this point?
Yes, certainly. Thank you, Emma. That was fantastic. Questions? Please feel free to speak up or use Slido or the chat.
I just want to comment. Thank you for the talk and say that was wonderful and very enjoyable, and appreciate that perspective. And I guess I just want to make a general statement to the room that I've thought about. We've got these nights, these events where you're highlighting 40 different observations, and I think we've probably anybody who's looked at the ground photography, you'll have these nights where it was just beautiful out, and there will just be so many different perspectives. And I have no idea what to do with that much data. And so if you're, in the back of your head, if everybody's thinking like, how could we leverage that incredible amount of data for a very interesting case study? I think that would be a very interesting approach.
Could I? It's Eric here. Could I make a comment?
Certainly, Eric. Yes.
Yeah. Hi, everyone. Emma, great talk. Thank you. So first, I agree with Bill on one hand, but on another hand, I might say, it's not that much data actually, right? Because if you think about, and one thing that comes to mind is that, like I know some people who are in the business of trying to identify the orbital elements of meteors, fireballs, and so on, like to try to identify their solar system orbit before they hit the Earth, before they enter the Earth's atmosphere. And they have these software that, for instance, processes, like, because sometimes these fireballs will be seen by 30 or 40 security cameras. And they have developed software that will actually take that and the geographic locations and make some assumptions and then give them orbital elements, right? And that, which is kind of cool, right? And then there was a guy, and I want to say Andrew Walsh, I think it was Andrew Walsh in the UK, who wrote some software where he did the equivalent of our SkyMap stuff for our all sky imagers for the movies from the International Space Station. And so I think that it's something, there's so much of this data out there now that there's something that someone could take on in a serious approach to allowing people to take that, bring it together, and do quantitative, like infer quantitative things from that in some automated way.
Exactly.
Can I ask a question on a similar line? So I went to the website that that you share the Skywarden website, and I'm almost amazed to see lots of reports about Aurora and interesting stuff out there. But is there any way to, create a label for Steve or SARX or SARX with Blob like you're talking about? So I see lots of images, but it's so hard to get to the image that you showed. And I'd be interested in, getting a list of events so we can search Starlight Conjunction, the other things. So like, Derek and Bill said, I think it's so rich information in there, but it would be nice if there's any, good way to use, so we don't miss any, important or, even new phenomena that may be in there, but we, still don't know how to interpret.
There are identifications for three things. There's identification for SAR arc, picket fence, and Steve. And on the left panel, there's a search possibility. And there's something that says search identification or something like that. I don't remember how the field says in English, but please put Steve to the field or SAR, and you probably will find what you are looking for. There's only 67 Steve observations from Finland, and the identification for picket fence was added pretty recently, and we haven't had time to go through old observations of picket fence and set the marker to them. But there's plenty of SAR arcs and dunes.
Yeah.
Okay, I'll try.
You can separate that. Yeah, they are beautiful pictures. Yeah,
Carlos, that event, with green patches remind me of the one you're just looking at recently. So I think that's really real, and that's something that we really don't understand. So we really need some precipitation measurement to see what's going on those field lines.
Yeah.
There's a chance to get also these blobby aurora observations, but please email me and I'll get you the link. It's a kind of tricky because we didn't have a name for this thing, so we couldn't add any identification buttons. So there's just a hashtag in the descriptions of these observations available.
Yeah, that would be great, Art, and I'll contact you later. Thank you.
Emma, you mentioned these all sky imagers that these organizations operate?
Yeah.
Yeah, and so I'm curious, how do you make movies or do you save images? How do you save the data?
I'm not quite sure. Of course, it's unpractical to publish those all the material in Skywarden, but I know that Jyväskylä fellows, especially Arto Oksanen, has taken care of publishing these videos to YouTube. So one could probably search by using Hankasalmi or Nyrölä. Sorry for these names again.
No, I've been there.
Use them in YouTube. Okay, so you great.
Yeah. But because one of the things I'm thinking about is like anything that has an all sky imager. I mean, there's ways of summarizing the data that are very compact, and I would like to, if there's all sky imagers in that region that are operating, I'd love to get the summary data into Aurora X on one hand, because we're starting to get things from Miracle, from FMI, and from the Kjell Henriksen Observatory in Svalbard. So it would be really cool to get some of this and have it be searchable by the scientific community.
There's of course a way to fetch at least Tampere observations from cameras, so that you have some kind of time job that fetches just the latest images and saves them. Something like that could be easily done. I know that Tampere saves all their data, but it's it depends on certain people's activity, and the history might not be present.
Well, that's not different in the scientific community. Like it's the
Yeah.
same.
And I don't know how it is with Jyväskylä, but Boris images are not publicly readable. But I guess that if there were a need to get access to those ones, it would be possible.
Well, I like your philosophy that you have when you had your kind of principles or whatever, and you said collect the data before you need it. Yeah. And that describes that's a very, like, that's what our scientific community does, right? Like we go into this mode where we just continually collect data. And then sometimes we find we need that, right? So I really commend you on that.
Yeah, I'm a data consultant by profession. Mm-hmm. And we end up needing having old data quite often in our analysis.
Okay, that's fantastic. This is a really great discussion, actually. To continue on the train of citizen scientist contributions for observations, Michael, did you want to go next?
Yes, of course.
All right.
Just a minute, I have to share my screen. Okay. Okay, can you see my screen?
Yes, that's great.
Okay, fine. Okay, first of all, yes, thank you very much for inviting me to this workshop. I will briefly talk about the importance of citizen-sized data for the research on STEEF. Yeah, I'm a physicist and work on STEEF as a citizen scientist since early 2018, and since a year later approximately, I'm collaborating with the Aurora citizen science project from NASA, and since the beginning I did all my work as a non-funded volunteer and do all my work in the free time I have besides my professional work as a laser physicist. One of the essential parts of my work was the compilation of a list with STEEF observations from citizen scientists. It was more or less the beginning of my work, and in addition I did other works related to STEEF, for example research on possible historic observations of STEEF. I developed a triangulation tool to calculate heights of discrete structures in STEEF. Did a lot of work to identify specific STEEF substructures, and I'm currently developing a mobile spectrometer that hopefully can be used to analyze specific structures in STEEF in the field. A week ago, I got information that my further development of STEEF database will be funded by SchoolStep, so it will help a lot to put more work on that. I will talk a little bit later on that. My talk will concentrate on three topics. First, why citizen science observations are important. I will talk a little bit about my STEEF database, and will conclude with a brief and not complete overview of questions that arise from citizen science observations of STEEF. So first of all, why STEEF observations or citizen science observation of STEEF are so important for science. First of all, there are a lot of observation reports from citizen scientists, and this gives the possibility to search for professional data from on-ground instruments, and of course also from satellites. Steve observations from citizen scientists allow to search for parallel observations of Steve, allowing triangulation and providing information on its optical structure. Some citizen scientists start observation of Steve with very high cadence and short exposure times, and I found that especially this images with very short exposure times could find structures that are overlooked in the more typical long exposures of Steve with exposure times of in the range of 10 or 20 seconds. And also very important, the amount of citizen science sensors, with sensors cameras, there are quite a lot of citizen scientists all over the world taking every opportunity to look for Steve, and this amount of Steve images gives you a very, very extensive database to look for specific Steve events you're interested in. And also very important, citizen science observations of Steve allow you to search and identify rare and yet not known Steve substructures that have not been discussed in the literature so far. So some words to my Steve database. As you all know, citizen scientists often report on their observations in social media, for example, in Facebook groups. And I compiled a list with Steve observations from citizen science observations, and the current version of this list, you can see here a link to the list, contains Steve observations for 150 days with times and even more, including observations without very clear time. And this Steve database will now be further developed into an interoperable database with the help of funding. And what I like to implement into the list is to put in some search tools, some basic statistic functions, and very important information on specific structures observed, for example, picket fences, or if there were any further observations in parallel of other subaraural structures like SAR arc or transitions between SAR arcs and Steve and so on, or the so-called blob aurora. I think this could be very important for scientists to have such tools in the database to look for specific observations. And I'm of course open-minded for any suggestions what is important for the science community to be implemented in an upgraded Steve database. So I will now come to the observations that arise some questions. So you see here an example of a Steve caught with a very short exposure time of less than a second, and sometimes you can see in such images very thin vertical structures in Steve that you cannot see on images with exposure times in the range of a few seconds. And to the best of my knowledge, these structures have not been discussed in the literature so far, and I think it would be important to encourage more citizen scientists to try to image Steve with such short exposure times to look for structures that have not been discussed in the literature so far. And the citizen science images can help to identify the structures. Then coming to the vertical structure of Steve, the question is, how can we explain variations in the vertical structure of Steve? As you might all know, Steve is typically whitish in the lower part and purple or a little bit reddish in the upper part. But there are also some observations showing a greenish diffuse part of Steve, which has also not been discussed in the literature so far. And you can see here 2 examples of images where you can also see that the picket fences are not, in all cases, structures which are clearly separated from the Steve arc above. There are cases where the picket fence rays extend into the upper part of Steve, having whitish upper part. So there's the typical green in the lower part of the picket fence, but in the lower part, in the upper part, the green picket fences change to a more whitish color, similar to the color in the Steve arc. You can see on the next slide these structures a little bit clearer. You can see it if you can see my mouse here. The picket fences clearly extend into the arc of Steve and are not clearly separated from it. So another question that can be where citizen science images can help is the question: what is the latitudinal width of optical structures in homogeneous Steve? And for some, I think 1.5 years ago, I looked for some examples that might be useful for such calculations, and I concentrated on images of Steve where Steve is located very close to the magnetic zenith, to the local magnetic zenith. And you can see here on the images an example that I found in Canada, where Steve was very close to the magnetic zenith, and I use the star background to calibrate the image locally, and also check the intensity of stars in the star field, and was able to do some preliminary calculations of the width of this Steve arc, and I was very surprised because the results show that the width of the arc is in the range of just a few kilometers, and as far as I know, also for such calculations, there are so far no publications reporting on such narrow structures. The only value I know is from a paper from Béat Lagado Lacourt, and I think it's which is reported in the range of, I think, 20 kilometers or so. Okay, next example, I found that here in this example, a very interesting case of a picket fence, which shows a cloud-like structure which is attached to the picket fences and also moved in parallel with the picket fences. And this is a very unique example of a very specific, very rare substructure in Steve. This is the only case I know for such structure, and I think also such subtypes have not been reported so far, and it would be very interesting to understand what these images show. Here's some further examples of what I call torch-like optical structures in Steve. There are some examples where during the development of Steve, there appear quite bright whitish beam-like structure in Steve that reaches down to the height regime of the picket fences and up to the upper parts of Steve, and looks more or less completely white over the whole height extent, even in pictures that are not saturated. And yeah, I think such observations are likely also very interesting to look, because such structures are very untypical for a typical aurora. Here's an example of a very complex, very likely not feed-aligned structure in a picket fence. As you see in the right part, the structures are very, very complex, and yeah, it's also very interesting to have a closer look what might cause these not feed-aligned structures. Another example of a structures not mentioned in the literature so far. I found some examples, and in parallel to me, Alexei Chernenkov from the Alberta Aurora Chasers, also examples of faint pulsating green structures, which sometimes appear in the area between Steve and the main aurora. And Alexei put a lot of work in that to compile such observations, and you can see here a link to one of his YouTube videos where he present a summary of some observations he found. And what's also very interesting in this example is that the picket fence is also here in this case a diffuse structure and did not show clear or discrete structures. Yeah, and I'd like to come to my end. Give only a few an overview of a few examples that might be interesting for scientists, and yeah, I want to thank all the people who support my work, especially on the development and then compilation of my Steve event list. Okay, if you have any questions, feel free to ask.
Thank you, Michael. That was, again, just excellent. There's obviously some really great resources. One of the questions I saw in the chat, Eric Donovan was asking about the database, the Steve database you mentioned, whether or not it would be queried, or one could query it with via an API.
Sorry, I think I didn't understand what you mean.
You mentioned your database, and I think Eric's wondering if one can query it or will be able to query it via an API.
Applications programming interface there, Michael. In other words, could a computer just make some queries as well?
Not yet, but I want to develop this database into a database that can be used to search with tools in it. But at the moment, it's just an Excel list. So you have to go to all the events to look for specific events. So you cannot search in it at the moment.
So it's Eric here. There are a lot of people who would. I know there are a lot of people, us included, who would help you. Because I would recommend, if you're, because you have some funding, and if you make your database so that it can be accessed by other programs, you don't have to design the search engine.
Okay.
Right. I think that's the key. That's one of the key points, right? Because it's a lot of work, and it takes you away from what I think you want to be doing, right? And secondly, I was going to point out that you pointed out that Chernenkov observation of the patchy of the very, very dim pulsating patch just forward of Steve, right? And I'm going to send you an email, a connection to Martin Connors, who's a professor at Athabasca University Geophysical Observatory. And Martin has a low light level camera, and he's been looking, I mean, literally in the last 6 months at just that. And so that would be a really good connection for the two of them to make. Because it's basically what Martin's finding is, if you look south of the, where we all call the equator boundary of the aurora, right? And because we look at it a certain way, and Martin's been looking, in the few hundred kilometers south of that in the northern hemisphere, and finding very clear aurora, but very low light level. And it's invariably pulsating patches. He hasn't published it. It's a really good opportunity for that. Alexei was his name?
Yes, Alexei Chernenkov.
That's a very, very beautiful observation. And Martin's observations look like crap because it's a scientific camera, right? So, like these observations are great.
Okay.
Don't tell Martin I said that.
Emma has your hands raised. Go ahead.
Yes. Okay.
Yeah, I know I probably am getting myself into a lot of trouble by proposing this, but there might be a chance to kind of skip using tons of dollars for building APIs if the data could be placed to Taiwanvahti, Skywarden, because we do have these search functionalities, APIs ready, so the data can be fetched in CSV, HTML, JSON, XML formats, all these possibly common data formats, and searched. But it depends on the data model you are planning to use.
Yeah, I think we should talk about that later offline to look for possibilities to ease that work. That would be definitely helpful. Yeah, I think the most important thing for now is for me to define what data should be in there, and then the next step would be to do the software work to implement it and look for the best tools to do that. To start with my work, it would definitely help me to know if there is some very important information that is actually not in the event list that would help a lot to work with the list. And I think the main difference I like to implement is to put in more information on what have been observed. At the moment, there's just information that there was a Steve, where it was observed, some basic geomagnetic data, but what is missing is was there picket fence, was there any kind of rare Steve subtype, and I think that would help scientists, because in general they look for specific things in the observation and do not only want to know that there was a Steve.
Yeah, that's doable.
If I had, I'm sorry, Gareth, can I make one more comment?
Absolutely.
Okay, so Michael, this is fabulous stuff. I have it's kind of a piece of advice, I guess, which is the data that you have, the information you have is gold. Like it's really important, valuable information, right? And I guess I would just want to make sure or encourage you to not think about functionality and just think about the information, right? Because ultimately speaking, you're going to have a few hundreds of events, right? And then you can dump that, ultimately speaking, you can dump that into any file format. Any of these other systems can take that and use that. But it's putting that information together that's going to be really valuable, right? And so getting the right, like, is there a picket fence, the wavelength of picket fences, all that information, thinking about that and putting that in the right, like getting that together, that's the service that what you're doing provides for the science, right? And it's because it's not terabytes of data, it's not going to be hard to deal with.
No.
Right? It's the information that's going to matter.
I highly resonate with what Eric just said. You're adding the key metadata here.
Yes.
By doing the analysis that puts it in the framework that it can be used. That's the key effort here. We're used to dealing with all sorts of different data formats too, and all sorts of different kinds of things. We can synthesize that part, but what we can't do is the careful work you're doing right now in getting that in that framework, and that's just amazing.
Yeah, and the work you're doing is honestly, and this is not this is true. The work you are doing is the essence of science.
Yep.
Like it's what we do.
Totally.
Okay. If there's no further comments, I'd like to move on to the Alberta Auroral Chasers. Chris, did you want to go first with some slides?
Sure, I can absolutely do that.
All right, take it away.
All right. All right, is that sharing?
Looks good.
Cool. Still? Sorry, I just changed the format.
That's correct.
Oh, you just need to hit the button up at the top that says switch presenter mode and full screen. It's the last button on the, see the X? It's the button just next to that. Yep, that one. You got it.
Cool. All right. Hey, thank you, everybody, for inviting us to this event, to this workshop. It's a really great honor to be participating here. I'd also like to thank Emma for your presentation preceding. That was spectacular. You've done a wonderful job of representing your community, as well as the observations that you've been sharing. I think those have highlighted some observations for myself as well of recent. And Michael, I mean, huge thanks to everything that you've been doing for all of the communities around the planet. You've been doing a ton of work collecting this information, putting it into your database. It's been spectacular. Wonderful job. The Alberta Aurora Chasers, we've been around as a citizen science group since 2011. I wouldn't say we were necessarily a citizen science group back in 2011. It's certainly something that has grown on us. Back then, we were only about 366 members, pretty small. Since then, today, we are now starting to creep in on almost 100,000 members in our community. A lot of that is due to Steve, and a very large chunk of it is actually due to the pandemic in a lot of ways. When the pandemic was at its height in Alberta and everybody was locked down, there were people that were looking for something to do, some way to get out. And a lot of people turned toward Aurora because at that very time, back in March of this year, we had a long string of Aurora events and activity. And that drove a lot of awareness to our community that people could see Aurora from Southern Alberta. And that's really one of the goals of our community, is to help the 4 million people in Alberta at these southern latitudes be able to see Aurora when they didn't realize that it was even possible. So today, we've just had an explosive growth spurt, if you can call it that, in the last really like 9 months, where we've exploded in growth. That spike that is at the end in 2021, that's what our Steve growth curve looked like back in 2016, and we've now dwarfed that. One of the things that I really love about our community are our demographics. So we are sitting, when you compare our community to traditional astronomy clubs, our demographics are dramatically different. We are largely women by about 60%, and at the younger end of the spectrum as well. So we have the majority of our community is sitting between 25 years of age and 44 years of age. One thing I like to highlight about our community is that even though we're so large, we are still majority Canadian. 78% of our membership is Canadian. And of that, 65% of the membership is Albertan, which again is very important because we want to maintain that locality, but we also like to have that exposure, that sense of that ability to reach out internationally. A huge part of our community, obviously, is Steve, and that has really helped to formulate and dominate, I guess, how our community has shaped. And it really stems back to 2016 with Liz and Eric, when Liz visited Eric's team at the U of C, and our community came out in force, and we pretty much took over that meeting, I think, from a population perspective. The majority of the people in that photo are from the Alberta Aurora Chasers community, not from the team at the U of C, which is really quite fascinating. And that evening afterward, we all went out and we ended up talking about Steve. Eric was very clear to us that he didn't know what it was, but that until we figured it out, we gave it some sort of placeholder name so that it didn't influence what the understanding would be, which again really influenced our community. It really started implant some of that scientific processes and knowledge into our community. After that, we played foosball. I think Liz and I won. I'm not 100% sure. And then about a year later,
is a presentation to the European Space Agency.
I think my headphones just, can you still hear me? Okay.
Yes.
Gave his presentation to the European Space Agency on how I met Steve. And shortly later, within about a week, the story went viral. And between myself, Eric, and Liz, I think we spoke to almost every news agency on the planet, which was just ridiculous. And our community is so focused on Steve. We have thousands of photographs of the phenomena, almost every kind of perspective you could possibly hope for of it. I'm going to stop sharing. Let's see. There we go. So just a little bit about our community. Something about how it works. We walk the line on scientific observations and on helping amateur observers from Southern Alberta see the aurora for the first time. We also have a bit of an advantage. We've got 4 million citizens in this province living under a Steve hotspot. They just got to know when to go out and see it, I think is really the key. You got to get out of the city to see Steve. And the vast majority of people don't realize that it's even possible. Within our community, I'd estimate we've got about 100 to 300 detailed scientific observers. These people are taking accurate observations. They've got their camera timing nailed. They know exactly what their location is, and they've got observational knowledge of what they're looking at. These are also a mixture of observational experts, but also educators too. And we promote those educators within the community. We identify them as experts so they can help educate the other members of our community. We've got about 100,000 casual observers within the community. That's a mixture of people who are just here for the pics, people who heard that they can see aurora for the first time in Alberta, and people who didn't realize that they could see aurora at all from here without traveling to somewhere more northern like Alaska or Iceland. What we found though is that people can transition, these community members can transition from casual to detailed observers very quickly. And a large part of that, it's been mentioned a few times today, is when our members are listed as co-authors in the paper, that in other papers, that really serves as an encouragement to others within the community to realize I can be part of this too, I can be part of the science. And that encourages them to start paying closer attention to what it takes to get into a paper. We've seen several casual observers that are now being mentioned in Bill's papers, in Gareth's papers, in Emma's. It's really been quite spectacular. And just a little bit about best practices. What keeps our community going? It was mentioned earlier, at what point do we become too big? Because we are quite large. And it really comes down to a couple of cultural rules within our community. First of all, no politics. It's a hard rule. If anything political gets mentioned, it doesn't matter what side of the spectrum it's on, it gets deleted. If it comes up a little too often, that person gets muted. It just keeps everything clean. And as an extension of that, just be kind to each other. You have to be able to share information and ask questions and inform others without being mean. It's a huge, it doesn't happen very often. Facebook is a hotbed for not being kind. So we work very hard at maintaining that. And in order to do that, we leverage a lot of the tools that Facebook puts at our disposal in a group community. For all that Facebook has its challenges around this area, it really has done quite a bit to give us a lot of content moderation and member moderation tools that allow us to keep things clean, keep things moving smoothly. And it does a lot of automated things that really help clean things up. We keep things, we keep frequently asked questions for being asked too frequently. There's sort of a fine line there. You have to allow people to be able to ask questions, because we are focused on casual observers quite often, but we don't want to lose those grizzled veterans, and they'll go away pretty quickly as soon as they see the same, where can I go to take a photo 50 times a day, or is there going to be Aurora tonight 100 times a day? So we minimize those quite a bit, and we guide those new members toward our guides section. So we've got a lot of educational content, as well as to the announcements in our community, which we keep updated quite frequently. And finally, I think it's really, for us, it's about culture. Our community has a very strong culture, and we've got some seasoned veterans in the community that help to maintain that culture. And the culture is really around sharing knowledge, being precise about your observations, and helping others within the community. And with that, I can pass it on to whomever else, or if any questions, or pass it on to anybody else.
Thank you, Chris. Yeah, questions?
I have a question, Carlos.
Hey, Carlos.
So that nice ensemble of pictures of Steve that you show, are they distributed everywhere, or do you more or less have a kind of a record? So, okay, in this latitudinal range is where we see most of them, or that's because all the people are living there, or what can you say about that?
It isn't that catalog of images. It exists in the community as a gallery. It's called the Gallery of Steve, but it is not cataloged in any meaningful manner at all. It's simply photos that have been shared from community members. Some photos have dates, times, and location on them. Otherwise, there is not much in there. I know that Michael has been digging through a lot of that, both in the gallery as well as comments within our community. So if there's going to be any kind of catalog of that imagery, it's probably sitting in Michael's database.
Great, thank you. Great job.
So on that note, I appreciate, the lots of galleries that you guys make, and Michael's making a list, but oftentimes Michael's list doesn't have links to specific images. So I have hard time in finding the image that Michael has used to make the list. But is there any way to increase the coordination between you guys so that scientists can start with Michael list, for example, but then get easily to or chase us images?
Yeah, I think Michael and I could probably work through that. Basically, add a link back to the content into Michael's data.
Yeah, just a short comment from my side. There are a few links in the current version of the Steve event list, but not all listed events have a link. The reason for that is that I only put a link in the list if I was able to contact the observer directly and get its permission to do that and list his name. So in all cases where was not able to contact the observer or just did not have the time to do that, there is no link because I think it's quite fair to ask the observer in advance and become the permission to use his name in a list. And I don't want to put a link in a name without a clear permission.
And probably to be fair, Facebook does make it a little bit tricky for people who aren't connected to each other to contact each other in messages. So Michael could have easily reached out to somebody, and that message might have ended up in a spam box.
And yeah, that's also a very high risk if you contact an observer who's willing to collaborate, that he misinterpret your message as spam and just don't read it. So it's sometimes difficult, or I had cases where a person who I contacted sent me a message back 1 year later because my message was, as Chris said, in a spam folder, and he just didn't see it.
But Michael, one thing that I can help with in this effort is I can help you reach out to people for those additionals, because as admin in the group, I'm able to cut through the spam filter a little bit.
Yeah. that would help, because I don't want to bother too much people, because there are of course observers who just want to share nice pictures and they are not interested to participate in science. Most observers are interested, but yeah, you don't know it in advance. And if you send hundreds of messages that could get yeah, you might be misinterpreted, and I don't want to do that.
Mm-hmm. Yeah, I think we can work together on that.
This is Phil. For both Chris and Michael, you kind of worry a little bit about scalability if again you're having to opt in here, right? Which means that you do have to ask for permission, and if you get too many people doing this, it doesn't, and you've got to contact them individually, then you've got a scaling problem. And I wondered if you had any thoughts about how to deal with that.
I was thinking about that as we were talking about it. I wouldn't mind the idea of being able to get our community to self-help in that area. So by that, I mean, if we can get people to start looking through Michael's database and get them to add their own links into the database or send them to you themselves, that might help from a citizen science tactic to scale simply by adding more bodies to the problem. I'm not sure what the logistics of that would look like yet, but
yeah, it's unavoidable. You need to. I mean, permissions is also part of being a co-author in a paper. You still have to be permissioned. So it's the same question. It's just that it occurs to me that we have to make sure that you don't go against community grain by doing things and eroding trust, I guess is the point, is that you don't want people to say, wait a minute, I don't know where my images are being used because I found them over here. Oh no, all right, don't use them, please.
Yeah, and the number of times that someone reached out to me and said, this strange guy from Germany keeps on asking me if he can use my images. I don't think it's trustworthy. I'm like, no, that guy's good. But
sure.
So I hope the meeting like this, can strengthen connection between citizen scientists and scientists, so we can trust each other better. And this kind of coordination is real key. We need searchable database, like Eric mentioned. So we need to know precise location, time, and links to images, so that scientists can really use them. So I think coordination between you guys will be an important starting point.
Also, I mean, just on the coordination between on the trust between citizen scientists and the scientific community, I think one thing that we've seen a lot of in the last 5 or 6 years, when scientists actually actively participate in the community, that helps so much too. And we've got several of them that are active members of the community that will jump in and answer questions, or they'll see something interesting and they'll say, hey, I have a thought on that. And oh, by the way, I know a thing or two about this. And that really, really helps, has really helped bridge a big gap, I think, in the last few years.
Sorry, the only thing I was going to say, Eric, is I'm just going to put a forward reference in. On the last day of this conference, one of the things we'd like to talk about is not only what publishing plans one has for this kind of stuff, but where one publishes in the wider media to increase that level of trust, right? To say, oh, these people are serious and they have a good community. If I join that, I'll have a good experience. And that may be getting more articles out in the way that you've done. So I hope we can have that discussion later. Go ahead, Eric.
Well, so, I mean, I think that the trust issue is, obviously it's really important. And I was going to type into the comments, Chris, because the slope of your curve, when your curve ends on the right-hand side of your graph, is a little bit terrifying.
Yeah.
Right? I mean, like, because it's basically vertical, right?
Yeah.
And I think we should shut down social distance and flatten that curve out. But anyway, but the fact is that trust is it's a difficult thing. And one of the things that's very challenging is that to make really good progress scientifically, and for what all and actually in terms of, because I'm a photographer in my personal life, right? And I'm not an auroral photographer. I can't take a picture of the night sky to save my life. But the fact is that you know, when I gave that talk at Banff, and then I gave this press conference that I didn't want to give because I thought no one's going to be interested in this story. Like Isa had tried Bill's stuff and from his talk, and they tried some other things, and no one was biting on any of this, the real core scientific stuff. But I'd given this kind of weird talk, and so I did this 1 hour press meeting with Isa, which led to that media storm. And I had been very careful when I gave my talk. Like I used John Anderson's photos and various people's photos, Song Dupin's photos. And I was very careful, like photo by John Anderson, photo by Song, whatever, right? You know, but there was one photo in my talk. It was the photo that Isa used that I didn't credit the person. And that photo went viral globally, right? Like, I mean, globally, right? And it was Sherwin Caluhan or whatever his name is. I forget his name. Anyway, so I felt horrible. I was horrified, right? And so I contacted him and said, like, I'm really sorry. I'm really careful about this, but I ran out of time. I didn't credit your image, and that's the one they picked up, and you're going to see it on the cover of the Washington Post, right? You know, and I'm very sorry. And he was great, you know, and he was so good. And then I thought, you know, because I benefited hugely from this, and the University of Calgary did. The University of Calgary bought 2 large framed, overpriced prints from him of his picture, and you know, one's in the dean's office at the University of Calgary in Faculty of Science, and one's in actually Megan Gilly's office at the University of Calgary. And I mean, so I think the thing is to accept. One of the key things is to try to create a culture where we accept that sometimes we're kind of going to get screwed, right? Sometimes that's going to happen, and then we work in retroactively to kind of, okay, let's try to undo that. But if we put too much effort into trying to manage credit, it slows things down a lot, right? And people, like, I think I would love to see us build a culture where we trust each other, and we all try to do the right thing, and we make it right if we screw up. And I feel that with Sherwin, we made it right. Like he got lots out of that in the end, but it was a brief, very, very uncomfortable moment for me that arose out of just my kind of running out of time. And I think we're all better off. Everyone's better off that I gave that talk, and that Isa picked up that story, and that Isa included that image. Everyone's better off for that. But, you know.
Yeah, but in general, what happens is you have an event, and 1 or 2 photographers gave you the picture. So that's an automatic or acknowledgement or co-authorship or something. So if we keep that level, I think we'll be fine. So it gets complicated when you start dealing with a bunch of contributions and then crediting everybody. That could be critical. But just reading here the chat, the kind of interaction that we are thinking about putting the citizen scientist data, the scientific camera data on the same platform that you can go and check if a DMSP or swarm was passing by is great. And not to have only the cameras as currently the RIX program has, but then including all these thousands and thousands of images from citizen scientists. That's great.
Yeah.
Okay,
and also sorry, Chris, like, honestly, like, all the Alberta Aurora chasers, like, fabulous job, like, fabulous, seriously, like I mean, gold standard, right?
It is one of my most favorite things, hands down. This community is one of my most favorite things. I love them all to death.
Neil, you had a question for Chris about Aurora earlier?
Yeah, hey. When will the Aurora be out?
Oh,
Go away. Okay. I think are there any other members of the AAC, Alberta Aurora Chasers, that want to give some slides, or?
While,
Neil,
while
Alan?
everyone last weekend was watching the beautiful aurora show to the north, I was in southern British Columbia, and I got to see an unbelievable SAR arc that I don't think maybe Alan saw it, but this crazy SAR arc that because there's a big mountain in my way, I couldn't actually see the aurora. So
You should show it, Neil.
you want to
Well,
see
we
it?
all saw the SAR arc. It was huge.
Yeah,
It was gigantic.
I'll
And
show
it
you mine
lasted
real
for a
quick.
long time too.
And while Neil's pulling that up, I'm going to mention again a forward reference that one of the last blocks we have in this on Friday is a "What was that?" And I hope we can share things that are similar to what Neil is going to bring up there too, which is I don't even know if this is a SAR arc. I don't know what the heck this thing is, but I know
So it started on the horizon as part of a green situation. You can see the red kind of popping in.
We just see a thumbnail still, Neil.
Oh,
yeah,
that
it's still
is?
thumbnails.
It might be on the other screen, or
I'm sharing
bigger.
screen. I'm sorry.
That's all right.
How do I do
I mean,
this?
I still think there's elements of Steve in that SAR arc. I know I've gotten a lot of flack for it, but
Wait for my talk, Chris.
good. I was wanting to.
There are elements of one on the other and vice versa.
Yeah.
Is this still my
You're the one
thumbnail right
person I
now?
wanted to ask. No, it's still
It's-
small,
it is.
Neil.
Yeah, it's still your thumbnails. It's your file browser.
Yeah, Carlos, I've been waiting for this week just to be able to talk with you about that event.
Okay.
Beautiful.
Sorry, I don't know how to make it work. That never came up, eh?
No.
No.
Ooh, you see my thumbnails are beautiful, aren't they?
They are spectacular thumbnails. Here, I will, in lieu of yours, Neil, I'll share mine.
Yeah, go for it.
Let's see here.
Sorry, guys.
Okay.
I had them all ready too.
All part
I
of
mean,
the
the last time the Alberta Auroral Chasers started showing photos to all of us, good things happen. So I say let's let it ride, right?
Exactly.
So this is the part of it that I think looks most like like Steve because of the vertical elements that are in
Yeah,
there.
but it's almost like inverted, like it's like the picket fence.
It's
is
weird.
Red.
Yeah,
and
it's
the-
up, right? It's up on the top.
It's like a southern aurora is what it ended up
That's
looking
all
like because of
wrong, Chris.
The picture is upside down.
Here's where it looked most SAR-ish.
Oh, yes.
But there's still vertical structures in it.
Yes. And
That's beautiful.
those vertical structures had east to west movement in them.
Yeah, they did.
Yes.
Which
Chris, I
that's what-
I
Sorry, go
saw
ahead.
that you have posted a picture which shows clearly vertical structures. I have another one from Alexei Chernyankov, and I wonder about your location. Alexei was located in Rocky Mountain House, I think.
Okay.
So
I was
maybe
about-
maybe there's a possibility to triangulate the height of these structures because they move so slowly. I think there's a good chance to do that.
I think Chris and I
Yeah,
can
I
actually
was-
put ours both together because I was a long way away in
Okay.
British
So
Columbia.
Well, where were you, Neil?
I was in near Cranbrook, British Columbia, and South Kootenays there.
Yeah, but you could probably see what was seen from Rocky Mountain House if it was south of Rocky Mountain House.
Oh, I saw the top. I saw the main top of the auroras. I just didn't get any of the structures that they saw from Red Deer North, kind of thing. So, but I had the SAR and I had the big arcs and those blobs that Chris is showing there. Like that was all in mine.
Yeah, so many
obviously
blobs.
just a very
Yeah,
different.
remember one thing. It's like we call stable auroral red arc, but as I showed in my presentation earlier, there are many instances where there is a lot of structuring and motion and crazy things happening in the arc. So having those kind of striations or that happens in the SAR arc.
This was one of the most varied individual moments that I've seen in the sky. Right, and on October 11th. So yeah, that was really interesting to see all the different types of phenomena.
Well, and then you know, like just a few minutes earlier, we were looking at this, right? These rings with the dunes overhead. It was a ridiculous evening.
I can see.
But then again, when that main aurora structure subdued, that's when we got all the other stuff.
Yep.
Okay, I'm gonna butt in here and remind everybody that we have Friday for the what the heck was that session.
Okay.
And
I'll try to get screen sharing going then.
I'll let Ian take over now to give some slides.
While that happens, Liz has put a pretty important link in the chat that I recommend people check out, which is the data use policy. That's one of the things we've been kind of discussing. And Liz, I agree 100%. You got to think about this very, very carefully.
I also want to briefly thank all the people that is joining us from very different time zones. We have people from Germany, we have Emma from Finland, and Ian is joining us now from New Zealand. So thank you guys. Thanks to everyone.
Okay, kia ora, everybody. Nice to see you all up in the north. Down here in the south, we see auroras too. And hopefully if this works. Share screen. That one. Right, can you see that?
Yes.
Ah, excellent, good. Okay, so I'm just going to briefly talk about some of the work we're doing down here in New Zealand and talk a little bit about the community. Obviously, New Zealand is...
Actually, Ian, before you start, you've got the presenter mode. If you could go up to the top, switch the, yeah, that one right there.
There we go. Sorry about that. Okay.
Perfect.
So obviously here in New Zealand, we're not quite as directly underneath the auroral oval as those of you in the Northern Hemisphere tend to be. So we tend to get a slightly different view of the aurora. We basically see the top of it most of the time, and if the storm gets big enough, it fills out. And despite the fact that we're relatively far from the southern auroral oval, the community down here is rather large. In New Zealand, the Facebook group is about 20,000 people, and Tasmania has got more than 100,000 people. Many of these are very keen observers. They record events pretty much every time they happen. They have decent times on their cameras, etc., etc. The kind of things we get to see. This is a time lapse I shot a few years ago, and of course I want to make reference to the indigenous culture of New Zealand, the Maori, who call the aurora Nakahukura o Hine Nui Te Po, which means the rainbow of the goddess of the night. And this is an example of, I think it's a Steve event, but it just creeps off the side, so I missed it, which is a bit unfortunate. But here we go, there's the picket fence going across there, and just heading off to the side, I missed it. The first Steve I saw was in, I think it was a Steve in 2014, and I didn't really have a camera pointing at it, but this is the kind of stuff we get from down here. And then my particular favorite, Steve, was this event, which was the St. Patrick's Day Aurora in 2015. And I've actually re-rendered this for this particular meeting. I accidentally had my lens set on fisheye rather than narrow angle. So I managed to record the evolution of a SAR and also see a Steve underneath it, which was quite exciting. And this is, as I say, shot on a fisheye camera, ISO 6400. This was about, I think, 25-second exposures. And you can see some of the detail between the SAR and the main aurora front. And it's really, really interesting to kind of study. And I know some people have started looking at this. But in a minute, you'll see the arc gets all narrow and it kind of zips up, which was quite fun. So we're at a latitude of about 45 degrees, and this was more than my zenith. So you can see this aurora was quite a long way north, oh, sorry, of us, which is south for you guys. So it's quite a spectacular display. And here you see the zipping up is just about to occur, and the sort of the red color goes to white. Unfortunately, some clouds came across at the wrong time. And you can see a picket fence appears in a minute as the clouds clear. Oops, wait for it. There we go, and it's slightly, there it go, here comes the white color. It fades away. And then finally zips up. So it's kind of a beautiful thing to watch because you see the whole thing evolve before your eyes. It's pretty cool. And I managed to catch this completely by chance because, as I say, I had my lens on the wrong setting. So you never know what you're going to get. There's the picket fence coming in at the end, and then it kind of zips down to the horizon. So there's quite a lot of data available for the people down here, and I think what we can offer is an opportunity to observe in the other hemisphere what you're seeing up north. The other thing I'll point out to is some stuff that might be of interest to the observing community, to the science community. A couple of years ago, I flew on Sophia out of Christchurch. She comes down here and is based down here for about 8 weeks every austral winter to observe the Milky Way. So I managed to blag my way onto a flight, and this was the flight path. We went way down to 60 degrees south, so we went directly through the southern auroral zone, and I managed to get quite a few images during the flight. This little time lapse I shot, and this flight gave me the idea of actually trying to see if there's interest in running flights down into the southern auroral zone. This is a time lapse. This is a cadence of 5-second image taken every 5 seconds. So we were going through an active region. And it turns out that there is an interest. So we actually did an Aurora charter flight. We hired a Boeing 767 and took 130 people down into the southern auroral zone. So the biggest plane ever to land in my hometown of Dunedin, 767. And that first flight, this was the planned flight plan, which was basically we could go anywhere within that triangle between 32,000 and 40,000 feet. And we took off into an auroral storm, actually. This was March of 2017, and there's a slight aurora that's taken from Dunedin looking south. You see the pink. We flew way south and targeted the southern auroral oval, and that's a picture taken from a satellite at 1306. That's where we were at 1306, and you can see a view through the cockpit window. So we managed to successfully track it down. We time-lapsed the whole thing from the front of the plane, from the left and right windows, and got data every 5 seconds as we flew through the zones. And obviously, the thing was a success, got loads of publicity. And we did it again the next year on a 787 out of Christchurch, and we flew for about 10 hours, and we got 6 hours of auroral coverage, flying backwards and forwards across various active regions. And that's the flight path that we flew. On the 787, the navigation systems are slightly more advanced, and you can turn around a lot more easily. So we basically went forwards and backwards through the active regions over the course of about 6 hours and got tons and tons and tons of data. The next year I flew again on Sophia because they were quite interested in this. And on this flight, I pitched the idea of building a couple of sidecar cameras for Sophia that would sit up in the top deck and shoot as she flew on every mission. And we got permission to do that. So in 2019, we flew on 3 flights on Sophia with cameras on the left and the front. These were high-res Sony A7R3 cameras. We shot an image every 3 seconds over the course of 8 hours. And we got the camera system approved by NASA. So it meets all their requirements. And just quickly go through here because it's boring. So I was on the crew that night and had to brief the crew on the auroral prospects. Obviously, they're doing proper science, they're doing astronomy, not auroral science, but it's a great way of getting some spare data. And that's the system. The lights go off. There's a left camera and a right camera. And we got some pretty good shots and high cadence imagery of lots of auroral phenomena. Different types and locations. That's looking down over Invercargill as we were flying south. We also have flying now quite regularly around the equinoxes. So we've got 2 flights going in March and 2 flights in September of next year. And we flew 2 flights this March. And these are the flight plans, these are the actual flown flight paths that we took on these flights. My point for sharing this is that we are keen to, we have cameras taking images throughout these flights. And if we could get from the science community, idea about where Steves are likely to occur at any given time, we might be able to target the flights towards them because it's good for the people on board to see Steve, but we might be able to get some data that other people may not be able to get. So this is just a brief time-lapse shot from the flight deck heading south from Christchurch. This is in the March the 20th this year. I haven't smoothed this out, so this is pretty raw. But basically, this goes on for the best part of this.
Well, you can
time-lapse
see
goes on.
you can see a SAR arc and a blob while you're just started that video.
So I've got literally terabytes of this stuff now. I've been on. I think I've done 10 flights in all between SOFIA and the Aurora flights that we charter. And on the Aurora flights, the fact is we can target this. The pilots will take us where we really want to go. And what we tend to do is just fly through and, you know, the tourists like it, but we get loads and loads of data. So we've got flights going in March next year. I'll be flying again on SOFIA if she comes down to down to Christchurch in June and July, and then in September 2022. So if there are ideas for campaigns, we know we're going to be in the Southern Auroral Zone flying backwards and forwards. So if folks up north know we're doing it, we perhaps get coeval data of some kind that might be useful. As I say, there's a lot of stuff we do in the community down here. We're focusing on this also aviation type stuff as well. And thank you, that's all I really want to say. This is just, finally, this is a SOFIA time lapse taken in 2019. And it shows you kind of, unfortunately, SOFIA is not a perfect platform because it wobbles for the infrared telescope nods to get data. So we've actually built a more stable platform now that we can take on the next flights. But my point is the system's approved for flights on SOFIA. So in principle, someone up in the Northern Hemisphere could, there's a really nice bit coming in a minute here. There's some really beautiful shapes and structures visible. So this is all high cadence stuff. As Miguel said, we try and take as short exposure as possible so that we can see really interesting features, because you see lots of stuff that you can't really explain. Anyway, I'll shut up now and stop sharing the screen. But that's really a little bit about some of the things we're doing down here in New Zealand.
Wow.
Fantastic. Yeah, thank you, Ian. That's just superb. Questions for Ian?
I guess I would bring up the same thing we were talking about indexing this data. And again, I mean, if you're sitting on terabytes of it, there's a lot of legwork to just get it indexed so that you know, people can poke into it, similar to our previous discussions.
Well, tell me about it. Putting those time lapses together, I mean, I had 10,000 images, each of about 50 megabytes from each camera on each side of the plane. So I'm still processing stuff from the SOFIA flights because I've only got a laptop, right? I don't have access to a scientific computer. Right. So actually processing this stuff, I'm sure there's really interesting stuff in there that I haven't even seen yet. So that's, again, this data is out there if people want it, and I'm very happy to send a hard drive up to someone to play with. But yeah, it's kind of knowing whether this stuff is useful, or actually knowing from the community what kind of cadence would be useful. And again, as an observer, because I class myself as an observer, if on these Aurora flights, you guys can say, well, actually, SARS and this thing tends to form with these auroral conditions in this particular spot in relation to the main aurora, we can probably target the planes and try and see if we can get data. So in that sense, that's something that we'd be quite open to.
So it's Eric here. Hi, Ian. That's fabulous stuff. Wrong hemisphere, but great stuff, and but like one thing is, and this is something like I've actually asked, and Bea has said she's penciled me in for a talk at some point in time, because as I'm sitting here watching all of this, I'm getting some ideas. And so, for example, you don't have a scientific computer, right? And so we spend a lot of time and effort in our community generating data, and what you're generating is data, right? And so, for example, I could get you a better computer, right? Like I really could. I could get you a significantly better computer, for starters, right? Secondly, would you be willing to let all of your data sit somewhere else? And there's no pressure.
Absolutely. No, absolutely. I mean, my background's in astronomy, and I used to work. I used to do the outreach for Hubble, and I really believe that the way Hubble do data, right? All Hubble data is basically released for everybody to play with after a year. And I think this stuff is, I think it's the same. It should be Creative Commons or something.
Right,
so
well,
I have no problem in sending a hard drive.
Well, I mean, yeah. So I'm gonna include. I hope I have time maybe on Friday to give a bit of a talk, because there's I've got an idea forming, and that's fabulous stuff. And honestly, I envy you being able to fly around the waters south of New Zealand doing that.
This is Phil. I'll just say, for those of us who write proposals, you know, it's a really straightforward right to write. We need to, you know, here's an example. We need to burn through all this data. We need some help, some hands, and a couple of algorithms. And as Eric said, you know, a cloud computer or something or another where we can just do this. Those are pretty straightforward proposals to write, folks. Mm-hmm. And there are a lot of agencies that are issuing calls for that kind of thing. So it's like Eric, you got the right idea. I think there's an easy hook here together. You can just literally complete the pipe.
Well, we have a lot of resources for the next 2 years for Aurora X, right? I mean a lot of, more than I can spend, right? And well, I mean, like, because they I mean, honestly, it's there's a lot of room to move there, and we have fabulous computer facilities here. And like, I'm kind of, you know, because Neil Zeller and I are working on one aspect of this, and I start to think about how could we say, like, there's going to be a way of doing this. Let's anyway, I'll make my pitch on Friday. Okay.
But maybe, Ian, what you could take away from this is that there are ideas and there are resources that we could connect here. And so that's what we're trying to do. So, you know, I don't feel like you have to keep on hacking away at your own laptop there, you know, and doing it all on your own. I think the collective could help. That's great stuff.
Yeah. Maybe perhaps we can host this Future Steve workshop on a 787. Who knows? That's what I would like. That'd be great. Go down to New Zealand.
Yep.
Got my vote. Any further comments or questions?
Just to say, if you want to linger later, I will be talking about the event that Ian was showing at the beginning of the movie with more details. So stay until the end.
Cool. And if I can just say one thing, if anybody's got a super duper, you know, science type camera that they want to fly on one of these flights, we're very, very happy to do it, because we've got more window space than we need. So I'll just lay that out there as well.
I have the camera, and I have to be the person who carries it, so I'll be there. And I imagine I have to be there for 2 or 3 months, bracketing.
No, it's just a camera, Eric. Just a camera, no human being.
See, this is the way we really work these things.
Okay, thanks again, Ian. That was just fantastic stuff. Next up, we have Liz. Do you want to go ahead and take over?
Yeah, good evening, everyone. I can almost share my screen once Ian goes away. Thank you, Ian. So nice to see you again. And I can't wait till New Zealand lets NASA back in. So that's exciting. All right. So it is my honor to be invited to talk to you today about citizen science, and shout out the citizen scientists without whom we would not be here whatsoever talking about Steve. All right, is that the correct way? I think not.
Got to swap.
Okay.
There you go.
So I also want to acknowledge that there are many different perspectives on the Aurora. We tend to have a very Western science specific lens on this. It starts at the graduate school level, but there are all kinds of people who treasure the aurora, and it's a spiritual thing, and it's much more than our kind of siloed definitions of aurora. So also want to thank all of our collaborators and citizen scientists around the world, as well as our sponsors and NSF in particular for sponsoring this workshop, and also sponsoring the start of Aurorasaurus, the really big start of Aurorasaurus that helped us have the platform that we built. So way back in 2011, I had kind of a new idea about how people could help study aurora. That's when I got on Twitter and social media and started to learn about what was citizen science, because we really have these beautiful photos and we have a public, and then we can put that together along with a lens of this citizen science methodology that I'm going to talk about a little bit, in which we really focus on two-way science communication and valuing everyone's perspective and everyone's expertise from different levels. So that's what we've tried to bring together with Aurorasaurus. I'm going to go through this quickly because I have too many slides, but I couldn't toss any of them away. So we do have a system that's built to collect observations both from deliberate acts of citizen science as well as scraping Twitter, which has the open API to collect those observations and to put them on a map in real time. So, and it's built to scale with the huge storms and the huge numbers of people that contribute and get the word out in big storms. So we have that. I wish we had an Emma because we do have, software ages, our apps aren't working anymore, but we're continuing to advance the website as well as advance what the next iteration is and build for the next solar maximum, because that's going to be, the last solar maximum was amazing. Steve is amazing, but I really do think that's the tip of the iceberg, and there's quite a bit more to come with this. So it's really exciting. We welcome people to join us and, are committed to kind of some of the best practices of citizen science that are on this slide, including privacy, research use of data, volunteer management. Want to give a big shout out to Laura Brandt, who's been the Aurorasaurus project manager. And without people like her, we really still struggle to meet in the middle and to make this critical bridge between our traditional observations and our graduate study level and above of space plasma physics and public participation and this rich area in between. So this is something like a three-legged stool. NASA has been advancing opportunities for doing citizen science. So if you want to learn more about it, there's some really excellent workshops on that have been happening lately, as well as new opportunities for funding. This is the platform that we built. Since 2014, we've been collaborating with citizen scientists. I'm going to quickly give a few highlights. We've started a session for AGU that is called the MacGyver session, where you can hack and come at this from whatever perspective you want, put things together for studying space physics and space weather. One excellent example is Vincent Ledvina, who's a University of North Dakota senior in physics and has been doing Aurorasaurus for a number of years. Also is an excellent, excellent night sky photographer. He's worked with us as well as with other people in the Live Aurora Network and people who to build this North Dakota dual Aurora camera. And really, this is not a science grade camera, but it is also not just one person going out and taking photographs. It's in this hybrid agile space and in this sub-auroral region. So it's really exciting as well. Let's see, what else? We also have education products and, invite people to join us to help test those and see how we can better scaffold Aurora science to where we can all enjoy it and all work together and better talk to each other. So you have heard about Steve, and I wanted to give this slide for the first paper on Steve and give a special shout out to Nutani Barasa, one of the citizen scientists. I don't think we've mentioned him yet today, but he was really a pathfinder with data for this very special Steve event, because he was taking photographs deliberately, because we were all interested in Steve, but deliberately in a time-lapse mode. And so with that, those observations have captured the way the picket fence evolves, and that was described way back in that first paper as well, as the excellent observations from the ground and from the SWARM satellite. So you heard from Michael earlier. I also wanted to share some of Michael's work that has been published in Space Weather, in which his background actually, partly as an Aurora historian, he recognized that Carl Schormer had collected observations and published observations of Steve 100 years ago in multiple languages and with a kind of proto-citizen science network. And really, those papers are really interesting. He called it Feeble Homogeneous Arcs of Great Altitude. All of us on the original Steve team did multiple literature searches and did not find this. And, you know, it kind of also points to the fact that a lot of our training and focus in space physics in the last, I don't know, my career, at least 25 years, has really focused on what's happened in the space age. So the International Geophysical Year of 1957 forward, and a lot of that also has featured high latitude substorms and longstanding arguments about substorms that we have still not resolved. And so we can now look at this subaurora region and with new cameras and see new things. Back to Norway 100 years ago, though, they could look with multiple cameras, take photographs, look with the spectra, the filters that they had at the time, and note unusual spectra. And so that's really interesting as well, and also reassuring, because it tells us that Steve is not totally new. There are still many questions, and Michael's more extensive database up to the modern times shows, I think, is our best statistics on the occurrence ratios of Steve throughout the year. Of course, we've only had a lot of observations for the last 5 years or so, and we want to continue getting observations and all of that as well. So let's see, Josh covered this paper, his paper, with these tiny little streaks as well. I just wanted to point out that the tiny little streaks were found in a different mode. So they were found pushing the limits of time resolution down to very short times. Whereas the original Steve observations by photographers were found, you know, it was often kind of photobombing the Milky Way in a long sort of 30-second exposure. So both of those, longer time and shorter time than many of our typical automated science grade cameras, kind of really shows how the aurora is so dynamic, and we can see more as well. So citizen science lets us see differently. Steve is this fascinating boundary case. There's so much more to understand with Steve. It's a boundary latitudinally, longitudinally, altitudinally. There's all kinds of like detailed questions about its occurrence. And also, depending on who you are and where you've been, where you're coming from, people have different perspectives on Steve. So we need to figure out how to look from both the magnetospheric view of people who are typically look at magnetospheric data, people who typically look at ionospheric data, and then also whether you're more of a high latitude ionosphere person or a equatorial latitude. Like there's a lot of different boundaries there. And we can miss things in those boundaries because we don't, we tend to say the same thing, but with different words. And so we might be missing other things about that. And we really can communicate better. And people, citizen scientists, have asked some excellent questions. And I want to encourage people to continue to ask questions throughout this meeting. And citizen scientists are coming at this with the view of, oh, that's interesting, and not with like prejudgment of, oh, that's a subaurora this or not a substorm that, or, it's just all connected to the aurora and all really interesting. So we can really increase resolution with the power of people's observations. And I'm super excited about this SolarMax and what that will bring. I think this last Canadian Thanksgiving storm just last week really demonstrated, you've got like a 600-kilometer north-south ad hoc chain here in Alberta of aurora source, people who've gone the extra step and also contributed observations to Aurorasaurus for the research archive. That's just amazing. We really have this kind of ad hoc clear sky network because people know where they can go, and they also know how to take photographs like through clouds and find aurora. And as we're getting more and more satellites looking at aurora, new satellites, this will be very valuable as well. And finally, a shout out to Jeremy Kusub, who's got a background in machine learning, also has made many different creative products with the aurora. He's the software developer who came up with Keogramist. And you can now find that on Aurora X. You can also find that on his website on Capture North. And just the other day, he took some Alberta Aurora Chaser observations and of this ring thing, and came up with this cool little animation just showing the ring from south to north. And people have asked, what is this? I would love to have some references to point to on this particular storm. It had the ring thing, it had the unusual SAR arc, as we've seen, SAR-like arc or anomalous SAR arc, I would actually say, as well as a Steve later in the night. So I hope we have a way to like virtually come up with a timeline for that and virtually put these observations on the table. I know that'll be a challenge in this kind of environment, but going forward tomorrow and the next day. And lastly, welcome people to join us. We have an ambassador network, both of citizen science leaders and scientists who like to do outreach and learn more about citizen science. We have an early career group as well, and we have a postdoc position that's available. So if anyone's interested, I would definitely encourage them to get in touch with us. And that's it. Thank you. I only went 4 minutes over.
No, that was perfect, Liz. And the October 11th, 2021 storm will forever be known as the Canadian Thanksgiving storm.
Yep.
I love it.
Yeah.
I just realized we keep calling it the Thanksgiving storm, and that's not culturally sensitive.
Well, I wasn't sure if Canadian Thanksgiving is culturally sensitive to you guys, but I'm glad you like it. We can all agree on something like that.
It's not like the St. Patrick's Day storm, which is universal.
But which one?
Yeah.
Interesting.
Questions for Liz? Questions, comments besides the one we just made?
Maybe, Liz, I'll ask the same question that came up when Chris was talking earlier, is that when you have a community that's growing, right, you have to manage the complexity as things grow. And at some point, you can sometimes get to inflection points where it has to change to a new state because you've reached a certain level. How do you feel that Aurorasaurus is going in that sense? Do you feel like you are still on the uptick, or you're approaching a point where maybe some different practices have to be thrown into the mix?
Yeah, that's an excellent question, Phil. So Citizen science projects, the scale of the project scopes to the scale of, quote, volunteer management. So you do need to scope for volunteer management as you grow the project. And so that's one aspect of it. Our project, since it does have science funding, is different than what has already been mentioned, which are extraordinary volunteer efforts as well. And we love to collaborate and kind of figure out how to keep doing that. The other thing I wanted to say is about the software. So definitely that's another challenge, because a lot of these platforms are much more modern software than just, what the scientists tend to keep using, which is like IDL code or, Python code if you're cool. And so this is more like a modern responsive website and things like that. So the maintenance of that is a challenge and something that we continue to focus on and evolve. And then also I would say that this question of where do you go from here also intersects with NASA has a growing interest in heliophysics, in citizen science and strategy for citizen science. I'm also involved with that. Right now you want to balance the opportunities. You want to have small, medium, and large kind of opportunities. I would say those larger opportunities are collaborations with missions. And so that's something that I hope that we can have as well, meaning satellite missions, because that is really cool and really exciting for all of us.
Yeah, and Liz, we should explain also that, there are missions and missions, right? I mean, and the large scale full up missions are the ones that often have enough resources, right? That something can be done there. That's a little harder to do with a CubeSat, for example, or a very small kind of mission. So there's a whole portfolio here. And I think you're right. NASA is trying to wrestle also with how to effectively deal with that portfolio, and especially in connections like that one.
Yeah, I mean, I would say the simple answer is that, if you were doing citizen science with a mission, it scales to the size of the mission. So, a huge new mission, there's a mission called GDC that's coming up. That would be one of, something that would have missions that have a whole bunch of conjunctions. People on the ground, as I said, can really beat the clouds and add so much value to these satellite missions as well that, we want to continue doing that.
Excellent.
Okay, excellent. Any final thoughts before we proceed on to, I believe, Carlos and Toshi's presentations? Okay, hearing nothing, I'll let them start up. Just before they go, though, I'd like to say on that Canadian Thanksgiving storm, I was fortunate enough to see it from Fairbanks, from a parking lot next to the airport. It was plenty bright, and a colleague I was with, Alex Chartier, took a cell phone snapshot an hour later, showed me the next morning and said, "Is this Steve?" And I looked at it and I went, "Yeah, that looks like Steve." So we already have a Steve setting from Fairbanks, at least. Nice. Okay, Carlos, you ready? Or Toshi?
Sure. Okay, let me. Sorry. So this is one. Okay. Let me move this from the way. So I'm going to present an ongoing studies on two particular storms. The interesting thing is the two storms are basically driven by citizen scientist data. The first one, as Ian showed, is the storm that he managed to, so the event that he managed to capture while he was driving, that shows a beautiful evolution from a very bright red arc into what we think is a Steve. And the second one that you already saw the results that was published on the storm of 28 September 2017. And why I'm saying that this was driven by the citizen data, because you saw the picture that Alan Dyer had taken from Alberta on that day that corresponded to 27 September local time. So when we started looking at this, the first data that we look, or the period, was 27 September 2017. So I look at Miston Hill satellite data all on this day, until we realized that the citizen scientist observations corresponded to 28 September UT. So nevertheless, this is a very interesting event that I will discuss. So these are snapshots from the movie that Ian showed. There are 3 columns. The top row show the data, the multicolor data. The left panel here, 927 UT, shows this bright red arc. The middle panel was already transitioning to a thinner and white purple arc. And then the last panel to the right is hard to see, but I think you can see a glimpse of this picket fence, that they were very dynamic, moving towards the west. This event was occurred for a few more minutes, and at the end there was only a partial arc here to the western part of the picture. So one thing to notice also in this first image that is multicolored, you see this blob of green. So this is real, as you can see here in the bottom, separated the images in 3 different colors. You have the red color, very strong red emission. There is nothing in green, but in fact, there is like a depleted arc at the same location that you see the red, but you see this blob, very bright, that happens, I will show you a movie later, for 10 minutes coinciding with the substorm. So in the middle panel, different colors, you see in contribution from the different channels, the red, the green, and the blue. And finally, when we identify these picket fences, there is some red contribution on the western part of the arc. As you can see here, there's some red also there. It's strong emission on the green channel and no emission in the blue channel. So these are movies. So once one of the things to point out is here is this is an all sky image, if you want, that is not pointing upward. So it's very challenging because the zenith of the sky doesn't coincide with the center of the image. So we managed to unwarp, or basically convert this image in a way that you could assign or give a latitude or put latitude and longitude grids just to geolocate this arc. So we composed the images, we did the unwarping, and we made these movies. So I will quickly show. So there are a lot of clouds, as Ian mentioned. You can see here aurora activities here. All this dark part corresponds of the part of the pixel that is not sampling anything. Remember, we are not looking straight up. So there are clouds in the middle, but the red is there basically all the time. You can see the red arc there, also there. And at the end, you see that there is only a portion of the overall arc just extended towards the west. Now, when you look at the green, you start seeing those blobs occurring everywhere for the first initial 10 minutes. And interestingly, there is a depleted region here on green that I have no idea what it represents. But as you can see, there are clouds. Of course, they obscure a clean transition from having a depleted channel to a more, I'm just speeding up here. This is, let's see, somewhere here. You start seeing a glimpse of a thin arc behind the clouds. There too. And almost at the end, you see also there is some change in brightness here. And this is the arc that we think is related to the SAR arc. Similar thickness is observed in the red channel. So on the top, we have 2 images from one of the instruments that we have belonging to the network of Boston University, located at Mount John Observatory. These are, I think, around 200 kilometers north of the observations from Ian. And these are images in only the red line, 6300 angstrom. Sky conditions were worse than when Ian was, so we don't have any data after 9:40 UT. The event that started around 9:20 UT and lasted until 10:15 UT. Unfortunately, the cloud coverage was awful over Mount John. So the last image that has some data was here 9:30. You can see there is a glimpse behind clouds of an arc extending from east to west. Same thing here. This brightness, I think, is just scattering from clouds. One interesting thing here is, I don't know if you can read the scale here, these are calibrated data, and this brightness of this arc is around 6 kilorayleigh. This is extremely bright for a typical SAR arc. So this helps, assuming that you take into account scattering, so it's not totally 6 kilorayleigh, you can still say that this is very, very bright and can explain why you could see with your naked eye, or as easily as you could see the picture in the bottom. And what I'm showing here is almost at the same time, just to geolocate the arc to see that basically the altitude that we are using is the right one. At zenith is just a little bit above 45 degrees latitude. And in this, I think is 175 degrees longitude. The arc is just intersection of 45 degrees and 175. And the height that we are measuring is 425 kilometers. If you add an uncertainty, this is the typical height of a SAR arc. Moving on, we were lucky enough to have during this period a satellite path, Swarm B, that was moving northward. So here, again, one of the pictures, unwarped, the full color image. This is the trajectory of the satellite moving northward. And to the right, the plasma parameters measure, as was shown before, electron density showing a depleted region, electron temperature showing very large values, reaching to 8,000 kelvins, and even some points around 10,000 or 11,000. And interestingly, when you measure the horizontal cross-track velocity, basically the westward velocity, there is a channel that reaches all the way to 6,000 meters per second. But as we will see later, that peak occurs inside a wide channel that is peaking around 3 or 4 kilometers per second. So it seems that this is like a thin embedded structure inside this wider channel. Now, as the satellite was moving northward, it reached the northern hemisphere, the magnetically conjugate location. That means that point that at 425 kilometers, if you bring a feed line from the northern hemisphere to the southern hemisphere, will get inside the region that the citizen scientists there are being measured. So what we show here is the path of the trajectory of a swarm as it was mapped from the northern hemisphere to the southern hemisphere. So the path is going from this location to higher latitudes. Again, this is magnetically conjugate location. And here at this point, you see there is no evidence of an arc in the central part and the eastern part, but there is evidence of a thin kind of greenish, whitish structure towards the west, plus a kind of wider red structure, and something that we think is evidence of some diffuse aurora. So this is a very interesting region to focus. But one of the important things to notice here is that these points that are marking the trajectory, you can see these are symbols that were shown or were indicating the peaks of electron density variation, the decrease, the peak in electron temperature, and the peak in the plasma flow. But those points are not exactly reaching the location of these thin arcs, that, by the way, these are less than 0.2 degrees in latitude thickness. So this is evidence that whatever structure is happening here is not occurring at 425 kilometers, it's occurring at much lower altitude, in agreement with the typical values that we say, Steve's, are occurring below 300 kilometers or around 300 kilometers, as I will show later. Another thing to show here is that the plasma parameters are more extreme. Here you see electron temperatures that are reaching 10,000 and some points that from the flags on the instrument are reliable. They're reaching 12,000 Kelvin. And the channel now for plasma flow westward is much thinner and is reaching 10 kilometers per second. So we are seeing what we think is a SARAC evolution to a steep that seems to be associated with fast SAPs or a very wide SAID changing into a very, very strong SAID. So this is a zoom-in view of those channels of plasma flow. This is the Southern Hemisphere pass. So you see this wider structure peaking around 3.5 or 3 kilometers per second, and then it's embedded here, a thinner structure that we say, okay, is evolving to SAID, reaching almost 6 kilometers per second. And when we're in the Northern Hemisphere in the conjugate location, we see a much narrower structure peaking around 10 kilometers per second. Okay, no, this is just to show the picket fences. It's an extra. So finally, the second event is the one that we discussed and Bea also showed. This is the 27 September 2017 event that was cataloged as a STEVE. So we look at this data and it caught our attention and said, okay, look, this is a long-lived structure, around 3 hours. It's wider than the typical STEVEs. So what's going on? So we say, okay, we look at the data from Miston Hill. This is the field of view of Miston Hill. This is Lucky Lake. And I thought, okay, we can see if what we see at Miston Hill can be related to what we see at Lucky Lake. And as I showed in my earlier presentation, Bridger data from the SRI network was available. And Bridger and Lucky Lake are very, very close. So you can use the data just to see the altitude of the structure we are seeing. By the way, here you see at Miston Hill, there is an arc. These are images and work at 400 kilometers, assuming that this is our arc. So this is what you get. And you think, oh, this is pretty cool, very similar. It seems that they are aligned. There are a lot of striations or beaded structures on the arc in Miston Hill, something that you don't see in the other two images. But interesting also, you see that the western part of this arc seems to be much brighter than the eastern part. So this is part of this lack of uniformity if this is a typical SAR arc. Now, what we have here, the top right, is a crude representation, what we did just to get this altitude. So you have Lucky Lake is observing the SAR arc there, or the STEVE there, and Bridger observing there. So if we assume 400 kilometers, that would say, okay, this is a SAR arc. This is what you get. This is an image at a given time, and we are just taking a cut at different locations, and you see there is an offset in the peak of the arc if you take 400 kilometers. Mathematically, we did the calculation and we got a value of 284 kilometers. So we use that altitude shown here, and you can see that the peak of the two arcs pretty much coincide along the entire length of the arc. So whatever structure this is too low to be a typical SAR arc, and also we consider the kind of too high or at the border limit of high altitude for a STEVE. So using 284 kilometers and 80 degrees field of view, well, this is what we see. And you can see very nicely how the Bridger 6300 image shows the arc here, and how superimposed or very nicely continues the Lucky Lake that is seen in the back. And to the right, you see what is happening at Miston Hill. So this is evidence of a large longitudinal arc that if we increase the field of view just to get 85 kilometers, the arcs more or less touch each other. But the question is, what is this? What is happening? If this is STEVE, then what we are seeing at Miston Hill is also STEVE? Well, we have satellite data. This is a DMSP, 3 consecutive passes, 8:30, 10:09, and 11:55. And on the three passes going through the field of view of Millstone Hill, or here Lucky Lake or Bridger, and then in the margins west of the field of view, you see the typical signatures that you will observe on a SAR arc or on a Steve. We also have a swarm data. Again, this is 8:30, 10:01, and this is outside the field of view, 11:30, but we see the same things, large values. And the question here is a question of interpretation if we decide that this is a Steve or a SAR arc, considering that we don't have other wavelengths to measure. But at these longitudes, when Lucky Lake and Bridger, but at Millstone Hill, we had other wavelengths. They didn't detect any structure. And we also have a spectrometer. And the spectrometer on this night showed enhancement only on 6,300 angstroms, verifying confirming the theory that at least in the eastern part of the United States, what we are seeing is a SAR arc. But I show you also that there were the BD structures. So this is work with Sebastian Marac. He was a student from Josh Demeter. And he took one of our images. You can see the BD structures here. You see the arc here. And we look at GPS data. And for different passes, we look at what was the signature of TEC. So depending where you were, if you were outside the BD structure, we will see a decrease in TEC. This is coinciding with the location of the SAR arc inside the ionospheric trough. And when the pass of the satellite, the piercing point, was along these beads or touching those beads, that if you remember in my initial talk, we were saying this was due to particle precipitation that created ionization, and that's why you had an increase in TEC. Well, that's the thing is happening, at least, for example, for this G16, that's the satellite going through here, in which you see an increase in TEC coinciding with an increase in the emission from the imager. And finally, we looked at data from SuperDARN. This is a job that Simon Shepard did at giving us some results from to see if there were subs channels. And event, this is at 8:03 and this is at 8:26. And you see evidence very kind of well structured, if you want. I'm not an expert on SuperDARN interpretation, but I can see that here the channel seems to be better behaved, if you want, than the channel of the observations occurring in the eastern part of the US. So the question here is if this is evidence that we are measuring a wide arc, or sorry, a wide channel that is related to a SAR arc, or if it's a Steve that is very wide. And I think with this, I stop and I'm happy to answer questions. Thank you.
Thank you, Carlos. Questions?
So then, Carlos, it is a Steve. I'm kidding. So,
oh boy,
have you think about the possibility in the same way that you were seeing in the first event, a SAR arc transforming into Steve in time, that we could have that transformation in longitude?
Yes, that's why I'm saying that perhaps by combining the data from the western part, the SuperDARN, where you see those plasma flows kind of more uniform, and then the patchiness that you see on the eastern part, that I don't know if that's geophysical or is due to the different instruments. I don't know. Perhaps that could give some hints. Because the other thing is you have this long-lived structure, more than 3 hours, and it's really covering a large swath of longitude.
Looks to me like you capture the beginning of develop. Did you follow the AE index to see whether you are at the beginning or you are in the, or during?
So you're talking about the first event, the 17 March 2015?
Yeah, where you have this transition. I didn't.
Yes, we look at we are in the middle of the substorm that is in the recovery phase. So those pockets of green emissions that I show that they occur for 10 minutes, they are happening in a very strong substorm that is only 20 minutes long. After that period, from 9:30 to 10 UT, we are going through the recovery phase of a long substorm. At that point is when this arc is transforming into Steve.
Given the timing, well, basically when you have, I mean, when you look at the in situ data, so you should have a clear azimuthal dependence, right? If you look at the same position, at the same location, then you can get, and given that, you know, you have feedback, atmospheric feedback in terms of chemistry and density, etc., right? So with time, when you look at the satellite data, for example, couple of satellites, you know,
yes,
then you see that, you know, your initially wide structure and not very deep,
yes,
in terms of electric field, not very strong,
yeah,
narrows and deep, and the trough deepens and the electric field increases. So
that's
what you probably see, no?
Yeah, that's a good point. In fact, that's something that I didn't do yet for this 27 September, because we have 3 consecutive passes, like a long period of time, and each one is carrying different regions of this, the whatever structure we are sampling. So it'll be interesting to see how is that evolving.
Okay. If the MLT or local time difference, not like more than 3 hours, for example, if it's within 2 hours local time, I mean, so it's 2 hours times 100, you know, 30 degrees, right, in longitude. So you are basically at the same, in the same channel.
Mm-hmm.
Yep. Channel. Then you can compare and see whether it works or not.
Yeah. Yeah.
Also,
thank you.
Long ago, we found that, you know, there is a specific trough formation just due to high electron temperature. Not, you have, you know, a situation when you have SAPS wave structure, and at the equatorial part, like 100 kilometers apart, you have huge peak in the electron temperature and almost no electric field or no drift.
Mm-hmm.
And that's due to ring current, you can say ring current. I would say hot ions in the plasma sphere. At the equator edge of this, you know, there is a huge diamagnetic current at this edge, which produces a lot of turbulence and a lot of suprasonal particles.
Yeah.
And that directly connects to this, might be,
mm-hmm.
you know.
Yeah.
And it's rather narrow,
thanks.
basically, not very wide.
Yeah, thank you.
That's kind of common.
Great. I think, Carlos, there's a nice comment by Liz in the chat, which is, you know, and Evgeny, you could perhaps respond to that too.
Yeah,
like,
basically, that's a good point. Sorry to Steve or vice versa. I don't think it would be, it might be, yes. But it will take a very late time. You know, initially it should be wide, narrow, and start to
some more information I didn't share here is that yes, the conditions were cloudy over Mount John after 9:40 UT, but then around 11:30 or quarter to 12, it became clear, and suddenly the magnetic activity peaked, and another arc showed up. That I think that's a SAR arc. So I don't know if, as the SAR continued during those periods we couldn't measure, and there was a very short period of time which Steve evolved, or those are different things. But I think the key thing here is the Steve is short-lived. Steve from 3 hours long, I think is hard to explain. I might be wrong, but I think it's open question here.
I'd be curious to know what the simulations can show us in terms of time. I'd be curious to know Brian's opinion on that.
Well, that's more of a question to the drivers, which I don't know much about. So I'm going to kick that question to people doing ring current modeling.
We're going to have a whole modeling session tomorrow, and that's an excellent question to ask everybody.
Okay.
I wanted to make one comment, maybe, Carlos, and it's about just what we call SAR-arc versus Steve. And I wonder if we're kind of maybe hamstringing ourselves by making a distinction, because I don't think we really know what is the photochemical mechanism leading to these emissions we're seeing in the red. The historical SAR-arc mechanism is just heat conduction. And I think you've shown through all of your observations and the Mendillo paper, that's probably not what's happening with these things that we're calling SAR-arcs these days.
Right. So that's a good point, because one of the things that I think is happening also, as Stan Sazikin showed in one of his papers, you can still excite 6300 by doing this frictional forcing. So I didn't mention this in this event I'm showing. When you have DMSP, the electron temperature is, I think, 6,000. At the same location, but with swarm, the temperature is around 8,000. So we could argue about the difference in the measurement, or it could be that you're at lower altitude and you have an additional mechanism that is producing more electron temperature, and that would be the local effect that we think that is what's happening with Steve. But it could also be happening with the SAR-arc.
Yeah, and anytime you get elevated electron temperatures, you'll get red emission. I mean, one of the questions that Evgeny asked in his paper was why isn't Steve even redder? It should be brilliantly red, but it's not because of vibrational nitrogen.
You should pay attention to papers, to others' papers. It's explicitly known from, from heating experiments, for example. It was motivated by the heating experiments to explain red and green, combination during heating. And this has to do with vibrational barrier, And vibrational barrier, due to N2 nitrogen, right? It cuts off the thermal Maxwellian tail because you have very sharp and huge cross-section of vibrational excitation, electron by electrons, starting at about 1.7 eV and maximizing like 2 orders of magnitude at about 2.5 eV. It's a broad, like 2 eV width of this barrier. And it kills all thermal electrons, unless you have very strong turbulence, which, unless it's not collisional heating, not ohmic heating. And when you look at the just calculation, you will see that you need sufficient plasma density. There is a threshold. And this is determined by the ratio between plasma density and nitrogen N2 density. So if it exceeds certain value, then you have strong cutoff, strong bite out of the thermal excitation. And comparing Steve and SAR-arc, in SAR-arc, it's not so dramatic, But in Steve, it's really dramatic because it's very, very deep trough.
I thought your 2019 paper had a really nice example of that exact point. And my point is just that it's pretty easy to excite the red emission. And so calling these things SAR-arc and Steve, even if it's the same mechanism that's exciting the red, is maybe not a fundamental distinction. It has a lot to do with what the electron density to electron to N2 density ratio is.
Yeah, you're right.
Yeah.
Physically, there is no physical difference. It's just numbers, you know.
But I thought it's Eric here. I thought that one of the key results of Megan Gilley's paper on the spectrum was that the red line is like the red line is present, but not differentially so within Steve. Right?
Yeah.
Like,
sorry, go ahead.
Yeah, and so I mean it's Steve is not red.
No, of course.
Because
yeah,
of red light.
Right, of course. Yeah.
But we are talking about the mechanism of the red.
Yeah,
The
Carlos.
mechanism of the red emission is basically the same for both.
Yes, right. But the red emission is not special in Steve.
No,
except it's better observed.
Right. But I mean, Dave Knutson, who he might get mad at me for this, but he claims to have worked in. He worked in a cafeteria when he was in high school, and he said that at the end of lunch every day, he and his friends would stir all the food together in a pot, and it would always be pink because pink was what you got when you mixed all the colors.
Yeah.
And I always think come back to Dave saying that like
Eric,
Steve is pink because it's what you get when you mix all food together.
Yes, Eric, the question, the fundamental question, the physics question really is what creates the continuum? And the continuum,
so what created the
continuum in Steve?
Yeah, well, oh God, yes, of course, right, and that's
so I think we agree with Brian that this is due to vibrationally excited particles, namely nitrogen and oxygen as well. I mean O2 as well. The mechanism for excitation, that might be first of all electrons, and good idea ions as well. For electrons, you should have suprathermal electrons. There is, if you look at the cross-section of the vibrational excitation, you'll find that there is a thermal part, which is vibrational barrier, right? Mm-hmm. And which is suppressed because you don't have tail, Maxwellian tail.
Right.
But there is a significant part, though smaller by a factor of 2 or 3, but not order of magnitude, from the suprathermal part. So suprathermal electrons, like 10 eV, 15 to 20, I think eV, it's still significant, can efficiently excite N2 as well. And there are plenty of suprathermal electrons in this area.
Yeah.
So that, I mean, it should work. And also, what is important is that you have high abundance of N2 in this area because you have uplift of the thermosphere or neutral density here by at least a factor of by at least one scale length, 50 kilometers or so. So that 2 factors work to explain Steve.
Yeah, I totally agree. My point earlier was simply that when we're interpreting redline images, using terms like Steve and SAR arc might be confusing. But you really need to know if the continuum emission is there to call it Steve, I think. That's just my opinion.
I would fully agree with that. And I think, and I also take, I kind of, you know, so people at the earlier phase of the Steve saga, right? You know, people had said that the cameras that we were deploying were not sensitive enough to see Steve, and actually, you know, the key point was that Steve was a continuing emission. So when we deploy a red line camera, we were only capturing a tiny amount of the light that comprises Steve, right? And that's a really important point.
Yeah.
Oh, okay. It's now 9:03 Eastern, which is a few minutes past our scheduled time. So Toshi has graciously agreed to go first up tomorrow at 2 p.m. Eastern. So unless there's, we've had a really, really rich discussion, several discussions. My mind is absolutely fried right now trying to keep up with everything. So are there any other comments from the organizers? Am I forgetting to say something? I feel like I am.
No, we're going to try to maybe very briefly at some point after Toshi talks, we could probably spend 5 minutes just trying to summarize some of the key themes that we've heard today. And an overnight subconscious will help some of those come to the fore. We've been taking some notes, but we will do that before we shift tomorrow to modeling, which we've already referred to at least once today.
Yeah, Phil, I have a request. I have a meeting tomorrow, right at 1 p.m. in our time.
Yeah.
And I don't know when it will be. It's some important stuff. So if you put me at the very end, or at least until I show up, okay?
Okay. So in other words, you would want to do your stuff when again?
At the end.
Oh, at the end. Okay, thank you.
Yeah,
We'll factor that in. Thanks for letting us know.
I would summarize that, Phil, as Evgeny saying he shouldn't give his talk before he's there.
That would be a I like that tautology, Eric. We'll try to get to that.
Can we do that?
It may not be very good. It may not be very good if he gives it when he's not there.
I mean, he is really good. He could probably do that, but we won't ask him to do that.
Okay, yeah.
Great.
Thanks.
I just wanted to thank everybody for a fabulous discussion. This was great.
I'm really impressed. I'm really energized by this, honestly.
Definitely.
Yeah, thanks for making it happen. It's exciting.
Yeah,
That's
thank
exactly
you,
what we
Dea
wanted.
and Phil and Gareth. Seriously, thank you.
And Barat too.
And
Yeah,
Barat.
absolutely.
Right, sorry,
And Carlos.
Barat.
Yeah. And come back if you can. There's more.
2 p.m. Eastern time tomorrow. We reconvene.
Bye, everyone.
Good night.
It's really good.
Terrific.
It's great to see everybody.
See you soon.
Bye-bye. Bye.
Bye.
Bye-bye.